All right, welcome back, and we're on the next lecture. So now what we're going to do is start doing the Blackboard work here and kind of work through the transistor models and just kind of do some math and different little configurations of transistors and kind of work through how to analyze those, all right? So this will probably, I don't know, take 2 or 3 lectures, we'll see. And then we may or may not build something in this lecture. We'll see how it goes, all right? So let's get right to it here. All right, so the first thing is, let's go ahead and let's talk about some of these rules with the transistor, all right, so that we have been discussing. All right, so the first thing is, let's give ourselves some room here. So we've got our transistor here, and we're going to be dealing with NPN transistors, all right? So that means there's this arrow going down here, all right? And then we've got these 3 nodes right here. All right, so I'm just going to kind of put a dot here, and I'll put a dot here, and I'll put a dot here. All right, and obviously this is the collector here, this is the emitter here, all right, and then this is the base. These voltages at these 3 points, we can kind of come out here and we'll just put little probes on there. We can call this V sub C, we can call this V sub E, and then we can call this one V sub B. All right, so we've got these 3 voltages, we've got these 3 points, and then here is our transistor. And of course, this is an NPN transistor, right? So this is an NPN transistor, all right? And remember, PNP is the same, but everything is just reversed. So we're only going to analyze one of these. Okay. So let's start playing with this. So the first thing is one thing that that we have here is, let's look at these currents, what they're called. So the current that goes into this base here. So when this thing is on, in one way or another, we've got a current into the base. That's called I sub B. Then there's a current that's flowing through the collector here. This is I sub C. All right, and then a current that's going out the emitter here, and that's called I sub E. All right, so we have these 3 kind of currents here. All right, now, so let's try and relate these things together. All right, so to relate these things together, one of the rules is that I sub C equals what's called H sub Fe times I sub B. So this H sub Fe is called the beta, or the gain of the transistor, you know, beta. And there are 2 versions of it. One is H sub kind of capital FC, and that's kind of the DC gain. And then there's H sub little f E, and that is the small signal version of it, small signal gain. So there's H sub Fe, let me make this properly, H sub Fe, and this is the DC gain. And then there's H sub little f, little e, and this is the small signal gain. Now, so what's going on here? Well, what's going on here is we have models that we use to model this transistor, and these models are only accurate, you know, depending on what you're doing. And so if we want to use a simple model, this simple model right here, which says that this is basically a current amplifier, then we have this value here, this beta, and that kind of says for any given base current, you have this collector current, but it's not actually true. It's just a model, and it's only accurate depending on certain conditions. And this beta typically ranges between, these betas for the transistors we're talking about are like 50 to 250, and maybe an average might be 100. But depending on how much current is flowing through the collector and so forth, this will actually vary, or the temperature, so it can kind of be all over the place. You got to be careful of this. All right. So, but for now, we're just going to keep this as a simple model. All right. And then there's other models which we're not going to talk about. One is called the Ebers-Moll or Mall model. And this uses more of the diode model of the junctions, and it's much, much more accurate. All right, but right now we're just going to use a simple model. All right, this will get things done for most of what we want to do. Okay, so I'm gonna rewrite this as just beta times I sub b. All right, so I sub c equals beta times I sub b. Okay, so that's easy enough. Now remember, you can't get something for nothing with a transistor. So if you've got a power source up here, you can only supply so much current. So I can't make this thing give me more current than is possible, right? So this is just a model. Everything has to stay within operating conditions, otherwise it's not going to work anymore. All right. Now, let's look at the relationship between I sub B, I sub E, and I sub C, I sub C, I sub E. Let's look at that relationship. So that relationship is this. I sub E equals, so I sub B equals both the sum of I sub C plus I sub B. So the little I sub B comes in here and combines with I sub C, and the result is I sub E. Now, because I sub C, right, I sub C equals beta times I sub B, I sub B is very, very small, right, very, very small compared to both of these. So if we want, we can actually say this. We can get rid of I sub B, and we could say that I sub E is approximately equal to I sub C. That's okay. It's going to be off just by like a percent, right? But let's see what it actually is. All right, so now look at this right here. So I sub C equals beta times I sub B, right? So I'm going to just, let me do this with a different color so you can see. So I'm just going to plug this in right here, all right? So this equals beta times I sub B plus I sub B. So I just rewrote this, replacing this I sub C with beta I sub B. All right, so now what I'm going to do is I'm going to factor out the I sub B. And what am I left with? I'm left with 1 plus beta equals I sub E. So I sub B equals 1 plus beta times I sub B, and then I sub C equals beta. Well, we can write it this way. We can say equals I sub B times beta. All right, so they're very, very similar, and that's it. So if you want to be a little bit more accurate, you can write it like this. All right, so these are these kind of little modeling equations here. Now, what's something else that we know? So when the transistor is on, here's something that's interesting. So when the transistor is on and current is flowing into the base, we're going to turn on this diode right here that's inside of this base emitter junction here. So we're going to turn that on. It's going to turn on plus to minus, all right? And as a matter of fact, let's draw this a little bit bigger. Let's draw this a little bit bigger real quick here. Let's draw this bigger so we can see what we're doing a little bit better here. All right, so let's come here, go like this. That's better. Okay. All right. Okay, and again, what do we got here? Let's draw everything. We've got our collector, we've got our emitter, we've got our base. We're calling this the collector voltage, we're calling this the emitter voltage, and we're calling this the base voltage. All right, and then we've got a current here. This current here, we're calling this the base current, and then there's a current that goes down here. All right, that's called the collector current, and then this current here, which is called the emitter current. And what I'm saying is the collector current and the base current combine to make the emitter current, and they combine like this. The emitter current is I sub B times 1 plus beta, or the emitter current is the collector current plus the base current. So again, all these little things help us so we can figure stuff out. Now, what's the other interesting thing? So there's a diode here-ish, and when it's on, it's going to drop a voltage from the base to emitter, and that voltage is going to be approximately 0.6 to 0.7 volts. All right, so when the transistor's on, it's going to drop 0.6 to 0.7 volts. Okay, so now we have kind of everything we need to figure out what the transistor will do in different situations. So for example, let's build a little circuit and let's kind of see what happens here. So let's build a circuit, and so let's go here. Let's use this color. All right, so here we go. Let's build a little circuit. and let's see what happens. So I'm going to put a resistor here, and I'm going to put our emitter here, and then let's go ahead and put another resistor here. So I'm going to call this the collector resistor. I'm going to call this the base resistor. Now I'm going to put this up at some V sub cc, which in this case I'm just going to call 5 volts. All right. And I'm also going to say we only have 5 volts to deal with in the circuit, so we're going to apply 5 volts to the base here. Then I'm going to put this straight down to ground like this. All right. And now let's start doing some calculations and seeing what's going on here. Let's say, so and this is kind of how you do transistor circuits. So you set up your circuit, and then you kind of assign things, and then you do the calculations, and if you don't get a conflict, then it's okay. If you get a conflict or a paradox, then you have to change something, all right? So let's say that we want 100, so we want a current here to flow, all right? And so I'm going to draw the current like this, of like 100 milliamperes, all right? And let's also say that I want to have a resistor here that is, say, 100 ohms. Okay, so 100 ohms is my RC, and I want 100 milliamperes to flow. Okay, all right. So if you're paying attention, you'll know that there's a problem already. But we're going to pretend we're not paying too much attention. Okay, so now we know the transistor is on, so we have some I sub B. All right. We've got some I sub B. We also know that because the transistor is on, there's going to be a voltage drop of plus to minus of, let's just call it let's call it 0.6 volts. All right. So the emitter is at ground. This is at 0 volts. All right. So if this drops 0.6 volts, then that must mean that this point right here is at 0.6 volts. All right. That is the worst 0.6 I've ever seen. There we go. All right. So this point right here is at 0.6 volts. So if that's at 0.6 volts and this is at 5 volts, then that means that 4.4 volts is dropping plus to minus over this resistor right here. Now, what do we want? So we want 100 milliamperes to flow in this collector circuit, 100 milliamperes. So let's go back over here. Is there something that can help us here? So we see that I sub E equals I sub B times 1 plus beta. And we also see that I sub C equals I sub B times beta. So these are very, very similar. So if we just want to, for a second, forget the 1 plus beta part, we can come back to this and say I sub C just equals beta times I sub B, and we're just going to assume that I sub E and I sub C are close enough together. They're just, one part in beta different, right? So we'll just say that I sub E equals I sub C. So this 100 milliamperes, we can come back to this, and we could say this. We can say that I sub C equals beta times I sub B, right? So let's we'll put it right here. We'll put I sub C equals beta times I sub B. All right. And what's I sub C? It's 100 milliamperes. It's 100 milliamperes. What's beta? 100. And I sub B is what we're trying to find here. All right. So how much base current do we need to turn this thing on this much? So we just take 100 and divide by into both sides. So we get I sub B, I'm just flipping it around now, not I sub beta, I sub B equals 1 milliamp. Okay, so we got 1 milliamp there. All right, cool. So we know that we need 1 milliamp to flow in this base circuit here, 1 milliamp. All right, we know that the voltage is 4.4 because we know the transistor is on, and it's dropping 0.6 roughly over this base emitter junction. So we got the voltage, we got the current, we can figure out what the resistance is. So remember, V equals I times R, Ohm's law. We want to find R, so what does it equal? V over I. So what's our V in this case? It's 5 minus the 0.6, which is the 4.4, right? So it's 4.4 volts over, and what's our current here? What's this I sub B? It's 1 milliamp, right? We just calculated that right there. It's 1 milliamp. So it's 1 milliamp. All right, so let's get our calculator out and figure that out. But we knew volts divided by milliamps are K, right? But let's do it anyway. 4.4 divided by 1 milliamp equals 4,400 ohms, or 4.4K. All right, 4.4K, or it's a really cool sci-fi show that ended abruptly. All right, so we've got 4.4K. So RB is 4.4K. All right, so now if we build a circuit where RB is 4.4K and we put a 100 ohm resistor up here in the collector, then we should get 100 milliamps out, right? Let's check that. If we get 100 milliamps out, what's the voltage drop plus to minus over this RC here? All right, so let's come over here and we'll say, let's get a different color here. We'll say that V over this RC, all right, equals, what does it equal? So V equals I times R. So what's the I? 100 milliamps. And what's the R? The R is, we said it's 100 ohms. All right, so 100 milliamps times 100 ohms. All right, so let's see what we get here. 100 milliamps times 100 ohms equals 10 volts. Okay, equals 10 volts. Equals 10 volts. What's the problem with that? The problem is we've only got 5 volts to source, so this is wrong. So what happened here is we weren't paying attention when we were picking our current here or our collector resistor so that we wouldn't violate the circuit, the circuit's function. So the whole idea is, as we did this, everything was working out, but this is a violation because we can't have a 10 volt drop from a 5 volt source, right? So what do we need to do? What we need to do here is we either need to decrease our current, right? Decrease our current, or change this resistor and so forth. So why don't we just decrease our current? So instead of 100 milliamps, let's just do 1/10 of that, all right? So let's just come here and let's say that we want 10 milliamps. 10 milliamps. So we want 10 milliamps instead. So if we are going to flow 10 milliamps and we have 100 ohms, let's try that. So instead of 10 volts, right, we'll get, if we say at 10 milliamps, we're going to get 1 volt. We're going to get a 1 volt drop over that, which is okay. If we get a 1 volt drop over that, 1 volt, then we've got 4 volts here at the collector, which is definitely above the emitter, right? 0.1, 0.2 volts, so that's okay, so everything's good there. Now, we need to come back here because we don't need all this current. So now instead of 1 milliamp, we need 1/100th of 10 here, right? So when we did this calculation here, we said 100 milliamps divided by 100 equals 1 milliamp, right? This is, and remember the 100 was the beta. So now instead it's only 10, so we want 10 milliamps, so instead we want I sub B equals, instead of 1 milliamp, 0.1 milliamp. So we want 0.1 milliamp. It just goes down by 10 times. If that goes down by 10 times, then this resistor here is going to go up by 10 times. So now we need 44K. So now we need R sub B to be 44K. All right, so if R sub B is 44K, everything is going to work in the same way. So we just change R sub B to 44K, and now the circuit will work, and we will get this current out of here, and we won't violate anything. Okay, so basically that's working through using the laws of the transistor model, which is here. So I sub C equals beta I sub B, I sub E equals I sub C plus I sub B, they combine. And if you want to look at them, I sub E equals I sub B times 1 plus beta, and I sub C equals I sub B times just beta. And the reason why is that I sub B adds in just a little bit, right, because there's the combination of the two currents. But if you want, you can just say I sub E equals I sub C. They're within a 1% error, right? And then if the transistor is on, the base emitter junction is going to be about 0.6, 0.7 volts. It will change slightly as the current changes, right? But you can just pick 1.6, 0.7 and go with it. And the collector always has to be above the emitter by somewhere between like 0.01 to 0.2 volts, right? And then everything will work out, as long as we don't exceed the maximum current that the transistor can flow, and of course violate what the voltages are in the supplies themselves. All right, so this is kind of that analysis right there, right? So that's kind of how you work through these things. All right, now let's go ahead and let's move to a simulation. And I built a big simulation with all kinds of stuff in it. Hopefully it doesn't crash. If it does, I'll try and edit it out so you won't even know. But we're going to kind of go through this a little bit, and then I think we will go through one other model, and then we will go to the bench and play with some stuff, and then come back for some other lectures. All right, so let's go to the simulation now and take a look there. So here is the simulation. All right, so the simulation file is crash course EE transistor 01. It'll be inside of the materials. All right, so don't worry about that. All right, so here is our first, the model that we're kind of looking at right now. So in this case right here, so we've got a lot of sensing going on in instrumentation. So again, we're using this as Proteus, right? This is Proteus because it has simulation. And the free version you can do this with, but you just can't save anything. All right, so what do we have? We've got an NPN transistor here. We've got a 2N222. And then what am I doing here? I've got a 5-volt supply, just like in our example. And then I've got a 10K resistor here, setting up some base current. And then I've got this 0.1 ohm resistor here in the collector. So this is just acting as a current limiter in this case. So what we're doing is we're using this just as a current generator. And basically we're saying we're going to set up some base current, and then we're just going to dump the current out of the emitter here, and you could do whatever you want or put a load right here. All right, so in this case right here, we've got a voltmeter here, we got a milliamp meter here, we got another voltmeter here, we've got a milliamp meter here, and we got a 10K here. So the question is, what's going to happen when we turn this thing on? So let's just go turn this thing on. All right, and then I've got some oscilloscopes over here, which I'm just going to move off here for now. We're not using these for now. Okay, so let's see here. So we've got 0.42 milliamps running through the base here with this 10K resistor. Now, look at what the base voltage is. It's at 0.8 volts, right? So it's not exactly 0.6 or 0.7. In this case, it's 0.8 volts, all right? All right, fine. And then in this case also, what is the voltage right here? It's 4.99, so just barely above the zero voltage of the emitter, right? And then we've got this 0.1 ohm resistor here, which is causing this tiny little voltage drop over here. All right, so this transistor is on. It's probably saturated. And so now here's an interesting thing. So we got 0.42 milliamps here. So what's the beta of this transistor? Well, what's the current here? It's 56.8, right? So let's just do that. So we take 56.8 milliamps divided by 0.42, right? And what do we get? 135. So it's saying the beta is about 135. So that makes sense. The beta is 135. So the question is, so now let's also do this. Let's also do this. So instead of this 0.1, so let's stop the simulation. So instead of this 0.1 right here, let's go ahead, and I think we can make these 0. And I should have tried it, but let's make it 0, and we'll save that, and we'll run it. Yeah, not a number. See, that doesn't like that. All right, so let's undo that. What we're going to do instead is we're just going to short across this. We'll just short across this. So I'm just going to put a wire here and short right across this resistor. All right, so now we don't have any resistors, so we're just turning this thing on with no resistance, and we'll see what happens here. All right, so notice that the resistor is not limiting the current. We're still getting the same kind of current out of here. So what's limiting it is the impedance of this collector-emitter junction. So, so this is a safety measure, this little resistor right here, but it's not impeding anything actually, all right? So let's stop that simulation, and let's get rid of this. Okay, so now we just computed that at a small base current, we're getting about 135 for the DC gain, right? The beta is about 135. Okay, well, let's change this. What if we make it, let's try this. What if we make it 5K? So we're going to try and put twice as much current into the base. So do you think that we're going to get twice as much current out of here? Let's see what happens. So now we get 90 milliamps out. So now watch this. So now we take 90, which is our output, we divide by 0.83, and now we're getting 108 as the gain. So now do you see as this current changes, so the higher the current, the lower that beta starts going. So it was at 135, now it's at 108. So it's actually decreasing. So that's why this model is not completely accurate over as this current changes, right? Because it's just an approximation. Let's go in the other direction. So instead of 5K, let's decrease the current to 20K. All right, so now it's 20K. So now we were at 135 when we were pumping the half a milliamp through. So let's see what happens now. Do we get more gain. So now we have half the current roughly, right? So we went down to 0.21, and now we have 33.7. So let's do this division, see what happens. So 33.7 divided by 0.21. Now we have a DC gain of 160. So you see we went from 5K to 20K. We went from the 0.21 milliamperes to whatever it was at the other end, but our DC gain has gone from 108 to 160. That's basically a 60% deviation. So that's why these models are not very accurate, especially for DC. But what's good about them is this model is pretty accurate for small signal AC. And what that means is once we set the operating point of the transistor and set it like this, just set it someplace, then if we inject a small signal into the base, we'll see a signal out of the emitter or out of the collector, depending on how we architect this. And because we're not changing the DC operating point too much, this model will hold, and we'll get our amplification kind of behavior out of it, and the model won't fall apart. All right. So anyway, so this is how you can use this this transistor, kind of as a current source here, right? So we basically set up a current here in the base, and then we get that times beta for the output. All right. So all right. So that's one example. Now another example that I want to show you here, and is this. So remember that whatever voltage is on the base, the emitter is going to follow that basically by a deviance of 0.6 or 0.7 volts. In other words, whatever the base voltage is, subtract 0.6 or 0.7 volts, that's what the emitter voltage is going to be. So in other words, the emitter follows. This configuration is called an emitter follower because the emitter always follows the base, and so that property is very interesting. So whatever you put on the base as the voltage, you get that same voltage out, just shifted by 0.6 or 0.7 volts, depending on how much current is flowing through the circuit. All right. So if we build this little circuit right here, which is composed of a 5-volt supply right here up at the collector, all right, then we're just injecting a signal here. And we're gonna inject an AC signal, all right, and then we're measuring it here with this voltmeter so we can kind of see what's happening. So we're just putting a slow signal into the base, all right, and now this is never going to go negative. So this is going to be an AC signal, but it's going to always be positive. It's never going to go negative. So we're going to have a slow signal, and I'm going to show you that in a second. What we want to see is, does the emitter follow it, and what does it look like, and is there any loss, and so forth. And there's not. It looks exactly the same. It's just shifted by the 0.6 or 0.7 volts, and we've got all these different instrumentations to watch this. And then here's oscope 1, which I'll drag onto the screen so you can see this. So again, what we're trying to show here is whatever you put on the base as a voltage, you're going to get that same voltage out of the emitter, except it'll be shifted because there's going to be a voltage drop base to emitter of 0.6 or 0.7 volts. Now, what's this slow sine? Let's take a look at this. This is one of these generators in this Lab Center Proteus program. So I'm saying it's a DC, it's an AC sine wave. I want it to have a period of 3 seconds, so it's going to go really slow. And then I want it to have an amplitude of 1 volt. And then I want it to have an offset of 2.5 volts. So I'm offsetting at 2.5 volts and shifting it up off of ground because I don't want this thing to go underground, right? Okay, so when we turn this on, let's see what we get out of this. All right, so I'm going to turn it on. We're going to take a look at oscope 1. Okay, so here's oscope 1, and we can see the sine waves here. Now the yellow trace is the input, so that's showing us our signal. Now if I go here and I move this, you can see this. Well, it's hard for me to point on the screen, but here is the ground line, and I'm going to line that with that red line. So that's ground, all right? Then the blue signal is right here, and this is the second channel of the oscilloscope. That's showing us the emitter voltage, the blue, all right? And so again, I've got that aligned. So now here's the interesting thing. So both of these waveforms are tracking with each other, but they're simply shifted by this amount right here. And if we look at this, right now we're at about 0.5 volts per vertical division. So they're about 0.6, 0.7 volts off from each other. Now it's moving really, really, really slow because the simulation's having trouble. And also we got the slow sine wave. So let's just speed this up. So let's make this a little bit faster. So we'll make this period, let's make it 3 times faster. See how that helps us. All right, let's run it. All right. And again, these it takes it a second sometimes for it to start drawing these traces, so you got to kind of bear with it. So hopefully it'll draw in a second here. Okay, so let's go ahead and let's run the simulation, but first we're going to speed this up a little bit. So instead of the period being 1 second, let's just change the frequency, and we're just going to make this like 10 hertz. So this thing kind of goes a little bit fast. The oscilloscope is not cooperating, or oscilloscopes are not cooperating. The simulation takes a lot of work to get it to run, so it kind of goes slow sometimes. All right, so here is the oscilloscope 1, and so what are we looking at here? So channel A is the input, channel B is the output. So channel A and channel B should be identical voltage-wise, except there should be a shift of roughly 0.7 volts. The output, or this V4 here, should be 0.7 volts smaller than the input, all right? And now we can also see these meters here, these instruments, these voltmeters and milliamp meters are changing in real time, reflecting the changing signal. Now, as you can see here, these oscilloscopes are a little bit tricky, and sometimes they don't update and whatnot, and so you got to kind of play with them. So anyway, so we can see our 2 signals here. Now let me change the sweep frequency a little bit. All right, so there we go. And now one thing we want to make sure is we're both in the same scale. So channel A is yellow, there it is. Channel B is blue, and its scale is 0.5 divisions, vertical divisions per volt, and the other one is also 0.5. So they're both 0.5, so we're looking at the same thing. So we'll notice that these signals are following each other identically. All right, but they're shifted by like 0.7 volts, all right? So if we sit here and we measure these, we'll see that they're shifted by that much, all right? And if I grab this, here's ground here, so you see that dotted line right here? That is the ground reference, so I'm gonna get that on top of the red reference if it'll come back up. And again, there we go. So I'm just using the red line as a ground. And then here's the blue one, and let me line that. There we go. So now they're perfectly lined up for the ground reference. Let me change the sweep frequency. Maybe that'll help us a little bit. And there we go. There we go. Come on, come on. So if we were to measure the blue to the yellow, we would see that that's about 0.6, 0.7 volts, because we're at 0.5 volts per division. All right, and it's exactly 0.6, 0.7 volts. So this emitter, so let me stop the simulation. It's just killing the computer. So this emitter follower configuration allows us to take a voltage and get that same voltage out, which is useful. All right. Okay, so those are those 2 configurations right there. So in one case, we show that the transistor is simply a current amplifier, right? As long as we don't violate anything. And then we also show that this emitter follower is a useful configuration because it allows us to put a voltage into the base and get that same voltage out here, but we get it with current amplification. So if we take this emitter follower, all right, we can actually make a amplifier out of it called an emitter follower or common collector amplifier, right? And we're going to talk about that in a moment. But right now what I'd like to do is let's go back, and what we're going to talk about is current sources, which is going to kind of be based on this emitter follower example a little bit. Let's talk about current sources first, and then we'll kind of swing back to this. All right, so let's go back to the blackboard and talk about those. So we're back here, and let's go ahead and get rid of all that. Okay, so now what I want to talk about is using the transistor as a current source, okay? So let's go ahead and let's put one of our transistors up here. All right, and then how we're going to kind of draw this is in this manner. So we're going to put a resistor right here, and we're going to call this resistor, we're going to call this R sub E. And remember, this is the emitter, obviously. This is the collector here. All right, and then we are going to put a, let's do this. We're going to put a box up here which represents a load. All right, so I'm going to call this R sub L. It could be it's a resistor probably, but this is our load. All right, and now what we're going to do is up here we're going to have, this is going to be V sub CC. Okay. Okay. So now what we're going to do is we are going to program this transistor for a certain current, and then no matter what, this load here, right? No matter what the load is, we'll always get the same current through it within reason. All right, and this is a really cool thing. It's called a current source. All right, so we'll set this equal to 5 volts. All right, now let's make it, maybe let's make it a little bit bigger. Let's make it 10 volts. Okay, all right. Okay, so now we've got this system right here, and then let's put another, we'll put another resistor right here. Okay, and we'll always call this 10 volts right here. All right, so that's the voltage we're going to put in here, and we've got this R sub B right here. Okay, so for example, let's say that we wanted to have 1 milliampere flowing in this circuit. All right, so I want to have 1 milliampere flowing in this circuit. So I want a current of 1 milliampere. All right, no matter what this load is, I want 1 milliampere. All right, so to do that, let's see what we can do here. So the first thing is, if we want 1 milliampere flowing in here, let's go ahead and we'll pick a resistor for this emitter resistor, right? So let's just pick a resistor for this emitter resistor. Now, the problem is we need to make sure that whatever this resistor is, we don't pick it so low or so high that we can't get the kind of currents that we want out of here, right? So what I'm going to do is I'm going to pick this, let's say at, we'll pick this at, well, let's do this instead. Let's do this instead. Instead, let's do this. So let's look at it from this point of view. So we know that this is going to drop plus to minus over here, right? Okay, and it's going to drop plus to minus over here when the transistor is forward biased. We have I sub B here. We're going to drop this over. So we know that this is going to be approximately 0.6 volts, right? So that means that we want this base to be at like 1.6 volts. All right, so if that base is at 1.6 volts, this will forward bias it, and then we'll get 1 volt here. So what's nice is we get 1 volt here in this situation, all right, as long as this is 1.6 volts. So we get 1 volt here. All right, so if we got 1 volt here and we got 1 milliamp here, then we know that, again, you know, V equals I times R, right? So R must equal V over I, which equals 1K, all right? So if we put a resistor here of 1K, all right, now we have this going, and then now what we need to do is we just need to set up this current right here. All right, so we just need to set up this current right here. All right, and we know that I sub B, in this case, is going to be 1/100th of this current right here. All right, so a couple ways to do this. So we've got 10 volts, and we've got this 1.6. All right, so what the voltage is over here, plus to minus. So we want V R sub B equals 10 minus 1.6 volts over, and the current that we want over here, right? The current, excuse me, here, this is the voltage right here, and then the current that we want going through here is going to be whatever this beta is of this transistor, which we're going to assume is about 100, right? So we need 1/100th of that. So here we have 1 milliamp, right? So if you recall, I sub B, we can write it like this. First, we can say that I sub E equals beta times I sub B, right? Therefore, I sub B equals I sub E over beta. And actually, it's beta plus 1, but this is close enough, right? So whatever this is divided by 100 is what we want. So this is 1 milliamp divided by 100 is the current that we need for the base, all right? So we'll take, and that's just 0.001 milliamp, right? Or that would be 1, 2, 3. Excuse me, that would be 0.01 milliamp, right? 0.01 milliamp, right? So that's going to be the resistance, And we're making all kinds of mistakes here, so let's slow down a little bit. So here's the voltage here. So we want the resistance. So we've got V equals I times R. So we want R. That's going to equal V over I. Our V is this 10 minus 1.6, right? So this is 8.4 volts, and the I that we want is going to be 1/100th of this current right here, which is going to be 0.01 milliamps. Okay, that's what we want. So let's do that calculation right now. So we get 8.4 divided by 0.01 milliamps. .4 volts divided by 0.01 milliamps. Okay, and that's 840K. So 840K would be this RB. So if we have an 840K resistor here, this is going to set this up so that we get this 1 milliamp here, and whatever our load is, it's not going to matter. All right, so okay, so if we so for example, let's try this. Let's go ahead and instead of doing the math here, let's go ahead and let's set our load for a couple different values. So we'll set our load for, let's set it for 10 ohms, 100 ohms, and 1K ohm. Then the question will be, does this current remain 1 milliampere, right? So what we're trying to shoot for is a current source here where we just want to set this current, program this current to 1 milliamp. No matter what the load changes, right, the current will stay the same, 1 milliamp. Of course, the voltage over the load is going to change, right? So at 1 milliamp. So let's figure it out. So if we've got 1 milliamp, right, then V equals I times R. What's the voltage drop over the load if it's 10 ohms? Well, that's just 10 times the 1 milliamp, right, which is 10 millivolts. Okay, that's fine. What if it's 100? Then it's going to be, again, it's V equals I times R, so it's the 1 milliamp times the 100, which is 0.1, all right? And then times the 1K is going to be 1 volt, and then times, let's say if we put this all the way up to, let's say 5K ohms, right? 5K ohms, then it's just going to be 5 volts, right? So we can try these different loads, and the question is, will this current maintain 1 milliamp, right? Stay at 1 milliamp. Okay, so let's go back to the simulation, and let's give this a try. Okay, so the circuit that's closest to it is this one. Now the simulation is getting pretty big right now, so what we're going to do is we're just going to take this little piece right here, and I'm going to copy this to the clipboard, and then what we're going to do is, as a matter of fact, we'll grab everything here. We'll grab the entire system here, and we're going to delete it all, and then we're going to paste this back. Paste this back. All right, so we got that. And then what we're going to do is we're going to save this one as transistor number 2. All right. All right, and so now let's rename what this is, and what's this going to be? This is a current source. Okay. All right, and what we want to do is we want to set this thing up like our math. We're trying to get 1 milliamp here programmed here, and then we want to see if, as we change the loads, does it maintain that 1 milliamp? That is the question, all right? All right, so the first thing is, what was this? This was about 840K, right? Oops, 840L isn't what we want 840K. All right, this 0.1, for now, let's make this really, really small. 0.001, so it's non-existent almost. Now, let's open this up to put our emitter resistor, which is going to program our current. All right, and here it is here. I'll just copy a resistor, and just like any Windows app, it's just kind of, you know, drag and drop, cut and paste. That's all I'm doing right here. Okay, all right, and we're going to set this for, I believe it was 1K ohm, right? 1K ohm, let's go take a look. 1K ohm, all right, so let's go back here. All right, so if we run this, the question is, will this get our 1 milliamp here? So let's find out, so we'll run it. All right, so it's pretty close, we got 0.86. So what's happening here is the model is not matching reality. So we need to drive a little bit more current in here. So let's put this down to 800K ohms, all right? 800K. All right, there we go, 0.9, see that? And you gotta, you gotta play with this a little bit. So let's try 750K. All right, and almost perfect. Let's just try 700K, and good. All right, so 700K gets us 0.99 or almost perfectly 1 milliamp, all right? So now the question is, and that's with no load here at all, all right? So the load resistor is basically 0. Okay, so let's make it 10 ohms. All right, and here we go. So we make it 10 ohms and we still have 1 milliamp, right? The voltage here is 4.99, right? That's fine, okay? So let's go change our load. So now it's 100 ohms. So does it maintain? Yeah, it's still 1 milliamp, 0.99, right? And now the voltage is dropping here. That's fine, don't care. So basically we've got a current source here and it's sticking to what it's supposed to be sticking to. All right, let's keep going here. So let's make this 1K ohm. And sure enough, it's still working. We dropped just a teeny tiny bit, 0.02 volts, right? But it's pretty close. It's within now 2% of where it's supposed to be. And now let's go to 5K, right? 5K. And at 5K, we dropped, 20%, 19%. And the problem is this voltage is getting very, very low, and we're pushing this transistor, into saturation at this point, and there's not enough headroom here for the collector. So, but the bottom line is from 0 load all the way up to 5K, we deviate by 20%, and up to 1K, we deviated by, like 1%. So this is basically a programmable current source, all right, at 1 milliamp. All right, and then again, we'll stop the simulation and we'll put this back, say at 2.2K. All right, and then we'll run the simulation and we get almost our 1 milliamp. So if you need a current source, the transistor is good at doing that. All right. So anyway, that's another use of the transistor as a current source. And why that's important is we're going to use that feature for an amplifier, which we're going to kind of work out in the next lecture. So a type of amplifier we're gonna kind of work out. But the whole idea is we wanted to show that we can basically amplify a current. So we can put in a very small current, we can get out a very large current. In this case, it's 1 milliamp, right? And we had microamp. And the 0 right here, in this particular tool, see it's in milliamps, so I can put it in microamps. I should have done that so you could see it. So now when we run it, see, it's 4.82 microamps. There we go. All right, so you can change what the scale is of these things. So anyway, that is using the transistor as a current source. So what we wanted to do was we wanted to set this base voltage here so that we can get a voltage on the emitter and program the current through this resistor right here. So we did it in this crude way where we used a resistor, right? But that's not very stable. So there are better ways to set the voltage at the base rather than just using this one resistor. We could use a voltage divider, because what we really want is to set the voltage, right? So what we're doing here is we're basically assuming the current, then going backwards and saying, well, what's the current here, then setting a resistor to do that, but it's not very stable. What we'd rather is just set that voltage there, exactly what we want. Right? If we do that, then we can have more control over programming the current that's going through this, and then the transistor action will maintain the current no matter what this voltage is here, and that's what we want to do. All right, so let's stop here. We'll come back in another lecture, and we're going to kind of talk about biasing techniques to kind of set this voltage more accurately than just using a single resistor here. All right, so I'll see you in the next lecture. All right, welcome back, and we're on the next lecture here in our transistor lecture series. So if you take a look at the screen, what we're kind of working up to is building amplifiers with the transistors, just a couple simple amplifiers, one that amplifies current, one that amplifies voltage. And so what we're trying to kind of hone in on is what you see right here is this is a common collector amplifier, and we almost have all the elements of this. So One part that we need to talk about now, and that's what we kind of reviewed last time, is we went over current sources, and we figured out we could bias the transistor and get it to turn on and drive current through this. In this figure here, it's called RL. It's the load, but we would call it RE in the previous discussion. But there was no R2. So what we kind of had to do is we'd kind of say, what current do we want? And then we'd have to backtrack and figure out what I sub B current would be required to generate the I sub E current in the emitter circuit. And it's not a really good way to do things. It's not very stable, and it's not very precise. So what we want to learn now is kind of ways to bias transistors so that we can force the base to a voltage and set the transistor to an operating point. And this is one kind of bias. This is called voltage divider bias here. And by picking R1 and R2, we can set the base voltage. All right. So again, you're gonna read through this material, section 3.9 of the book. But anyway, I just wanted you to see this picture. So let's go back to the drawing program, and let's work from there. All right. So what we did last time was we were making current sources. All right. And we can look at the simulation. I think we have it up here. Yeah. So here's the simulation. And in the simulation, we had a 700K into the base, and then we had a 1K resistor here in the emitter. And then we could put different load resistors here, and we were varying them. And depending on the load resistor, regardless, the emitter current was always about 1 milliamp as we vary this resistor right here. And that's what we want. We want it to be a current source, and no matter what the load is, within reason, it will generate the 1 milliamp through here. Okay, so that's what we were doing last time. So basically, we got a resistor, resistor, resistor. This is a load that is you can change, and then this is a fixed value that programmed or sets the current. All right, so let's go back here, and let's kind of draw what we have here. So we've got our transistor, and we've got our emitter here, and we've got our collector. All right. And then we've got a load resistor here, and then we have V sub CC, and we're going to call this RC, or this is a load of some kind. All right, and then down here we have a emitter resistor, which is RE. In the previous example, we set it for 1K just because it's a good value, and then that allowed us, if we said that, hey, we want 1 milliamp flowing through here, 1 milliamp, and 1K means 1 volt would drop off of here, and then we could work backwards to the base. All right, so if we want 1 milliamp of current to flow through here, so 1 milliamp, and remember, let's be very precise. This current here in the collector is not equal to the current here in the emitter. So, IC is not equal to IE, but it's almost equal, right? So it's approximately equal to it, all right? 1 part in 100 usually, all right? So be careful of that. And that's why we make that assumption. We can just say IE and IC, IC and IE are the same. All right, so now what we have here is we want to say, okay, let's set 1 milliamp as the current in the system. If there's 1 milliamp and 1K, then that means that this is going to be 1 volt, all right, from ground. If that's true, we know that if the transistor is on, this is going to drop about 1.6 or 0.7 volts. It'll drop 0.6 or 0.7. So that means that up here at the base, right here, this voltage base, this will be at like 1.6 volts, all right, because 0.6 volts drops over this base emitter resistor if this thing is on, if the transistor is on. All right. Then what we did was we said we'd put a resistor here, and then we try and figure out what resistor we need to inject enough current. The problem with that is it's not very accurate, and it's not very controlled or precise. So instead, what we're going to do is we're going to look at different ways to do this. All right, so this method is basically voltage divider bias. All right, so what we're looking for here, and I'm just going to kind of leave this open so we could put an input in there if we want. We want 1.6 volts at this base node right here. We want 1.6 volts. We have 2 resistors here, so we want to set the voltage so that we get 1.6 volts. So there's a lot of ways to do this, all right? So let's start off and let's set V sub C equal to 5 volts. So we got 5 volts up here, right? 5 volts. Okay, and we want to set this voltage here to 1.6. All right, now we've got two resistors. It's a voltage divider, and remember, if we want to look at the voltage divider equation, then we could say that V sub B equals, so this voltage right here is R2, right, is R2 over R1 plus R2, and then that's times whatever the voltage is. In this case, it's 5 volts. So this little modeling equation right here, basically we've got one equation and two unknowns. So we've got a little bit of a problem. We're going to have to pick one of these values, all right? So we're going to have to pick R1 or R2, or we're going to have to pick something that relates both of them together, all right? So why don't we do this? Let's just start off and let's do something simple. So let's say that we want the total resistance, let's say that we want the total resistance, R1, R2, to be 10K. All right, so 10K equals R1 plus R2. So that means that we want the two resistors to be selected such that we get 1.6 volts over R2, and then we get the rest of it over R1. All right, so that's what we're trying to figure out right now is what that would be. All right, so R1 plus R2 equals 10K. All right, and we have 5 volts right here. So there's a lot of ways we can run through the algebra, but one way to do it would be something like this. We could do this as a percentage. So since this is a linear, right, whatever voltage drops over here and whatever voltage drops over here has to equal up to 5 volts. So I can just figure out what percentage of the voltage drops over R2. Okay, so let's figure that out. So R2 is, we know that it's 1.6 volts, right, because we're going to set it at that. 1.6 volts over 5 volts is what? All right, so 1.6 divided by 5 is 0.32. All right, so it's 0.32. So 0.32. So that means that we just want 32% of the voltage to drop over R2. All right, so that means that then we want, so we'll say 32% of the voltage drops over R2, then we need to have what, 68% of the voltage drop over R1. So the voltage is 5 volts, so very simply it's 0.32 times 5 volts is going to equal this R2 value here. Well, excuse me, 0.32 times the 10K, right? So 0.32 times the 10K equals 3.2K, right? Then we want 68%, so that's 0.68 over the other resistor, all right, times our 10K total. So that's going to equal, obviously, 6.8K, all right? So if we set those two resistors to that value, that will give us the voltage. Now let's go back and plug this in, and we'll see if it works. So now if we take these values here, so this 3.2, this is equal to R2, and this 6.8 is equal to R1. So if we take this and we plug this back in here, let's see if everything works out right. Okay, so this is saying that VB, so VB equals R2 over R1 plus R2 times the 5 volts. Let's check that real quick. So R1 is 6.8K, and then R1 plus R2 is 6.8K plus 3.2K, and then that total value times 5 volts. This should be 1.6, right? So let's figure it out. 6.8K divided by 6.8K plus 3.2K equals 0.68 times 5 equals 3.4. And let's see here, R2, yeah. Oh, we made a mistake here. We plugged in the 6.8. We didn't want to do that. That's backwards. We plugged in the wrong value for R2. Let's do it again. So this is R2 over R1 plus R2. So R2 is 3.2K. And that, and this is why you do this on the calculator and check it. Obviously it's really easy to make a mistake while I'm doing this on video. and talking at the same time. But you know, you do it, you write it down, do it on the calculator, and if something doesn't come out, then you catch yourself. All right, so 3.2K divided by 3.2K plus 6.8K. Okay, that is 0.32 times the 5 volts is, of course, 1.6. Okay, so we've checked this out. This is all working right, and that's it. So this equation up here, you could set, and now another thing we could have done is we could have just said, hey, let's set R1 to 10K and find what R2 is. Well, we could do that too. So again, we have our equation here, and let's write it down. So we have VB equals R2 over R1 plus R2, and order is not important here, right? Times 5 volts. All right, and let's just say, let's set one of these values, right? So let's say we set R1 to 10K. R1 is 10K, okay. So VB equals R2 over, and we're setting this R1 here to 10K, right? So 10K plus R2 over that, and then times the 5 volts, and that whole thing equals VV, which we know is 1.6 volts. So what we have here is this. Let's write this down one more time and try and not get so crooked. So R2 over R2 plus 10K equals 1.6 volts. And I'll leave that as an exercise for you to solve for R2. All right, so again, we've now, with this voltage divider, we've actually set what this voltage is. And so now we have a better control on this because now we're not playing with current anymore. We're actually setting the voltage now. So that's fine and dandy, but you know, it seems like we're missing something, right? And we are missing something. And what the something is this. The impedance looking into here, right? So the impedance looking into the base is going to have an effect on R2 because these things are in parallel. So R2 is in parallel with RE, right? So R2 is in parallel with RE, and I'm going to put RE star. It's not the RE, but it's the RE seen through the base, or what's called the reflected RE. So RE star is the reflected RE, and remember that anything through the base is basically the beta, the gain, times the resistance. So it's really R2 in parallel with RE times beta. And what's beta? About 100. So it's 100 times bigger. So in most cases, you can just forget about it. So this is 1K. And so 100 times 1K is 100K. So this resistor here, this R2, what did we figure it out? R2 is what? It's 3.2K. So it's 3.2K in parallel with 100K, all right, is going to really be what this R2 ends up being. So we can call that, let's call that R2 primed. So R2 prime is really what this final impedance is going to look like, and it's 3.2 in parallel with 100, right? So it's just a couple percent going to be modified. But let's figure it out. So it's the product over the sum. Remember, parallel resistance is a product over the sum. So what's that going to equal? It's going to equal 3.2K times 100K over 3.2K plus 100K. All right, so let's figure that out. 3.2 times 100K equals divided by the sum, 3.2K plus 100K. Now, we're expecting it should always be a little bit lower than the 3.2K, but because the 100 is so large, it won't be much different. Maybe it's going to be 3.1. All right, let's see what we get. And it's exactly, it's 3.100775, but we'll call it 3.1. So this approximately equals to 3.1K. So the point of it was, you could have just hand waved and said, hey, this is like a 1K resistor. It's going to be about 100, maybe more K after the impedance is seen through the base, because even at a minimum of 100 beta, it's going to be so big, it's unnoticeable. And it only modified it a little bit. But this is where our calculations would be a little bit different. So because it's looking like 3.1K, the voltage over R2 here will not be are 1.6, maybe it'll be like 1.5. And because it's 1.5, this voltage will be different. We'll have a different current through here. And this is why you got to kind of be careful here and make sure what you're doing is correct. All right, so this is one kind of biasing, voltage divider bias. Now, let's go take a look at a simulation based on this, and let's see what happens there. And I know we're doing a lot of simulation because this material is fairly complex. And when we build it, we're going to, probably have a lot of problems. You always do when doing this. So I want to just first do it here, and then we'll do it over there. All right. So what do we have here? Let's just modify this thing. So I'm going to leave this this current probe here, and I'm going to detach this resistor R1. All right. I'm just going to kind of put it right there. And we'll move it over here, good. And then I'm gonna just replicate it. There we go. All right, so far so good. And then I'm gonna put a wire here. I'm gonna grab this ground and I'm gonna copy it over here. All right. And we've got this 1K, that's good. This 2.2K for now, I'm just gonna put that again at 0.01 ohms. Like there's no load at all, just 0.01 right now. All right, and then let's fix these two. And what did we say they were? They were 6.8K. And this one was 3.2K, but we saw that it's actually going to be 3.1K, which is going to give us an incorrect value for our voltage. But we'll just leave it at 3.2 so you can kind of see what happens here. And that's why we have to modify things. All right. Okay, and let's connect this. And again, we're using Lab Center Proteus for simulation. It's the eval version you can do this with, you just can't save anything. All right, I'm not going to save this. I'm going to just leave this as is here. And you can make modifications to this version too if you like. All right, let's go ahead and run the simulation. All right, and sure enough, look at that. We've got 1.6 volts, almost 1.6 volts, so it's almost perfect. And then we've got 0.94 milliamps here in the emitter. All right, and so this is really nice because now instead of messing around with currents in beta, we just kind of do this voltage divider, all right? And we get to what we want a little bit better. Now, because the 3.2 in parallel with the 1.K is really 3.1K, so we got to increase this a little bit. So after it gets paralleled with the reflected impedance of this 1K, it's going to be 3.2K. So why don't we pump it up to 3.3K? So in other words, now 3.3K in parallel with the reflected impedance of the 1K will be more like 3.2K, and we'll get our more accurate 1.6 volts. But we were pretty close. See that? We're so close, we kind of just went over it right there. But nevertheless, we drove this a little bit harder, and we got a little bit closer to our desired 1 milliamp. So let's go a little bit farther, and we'll go to 3.5K. Oops, 3.5K. Be careful of that too. In these simulations, if you leave off a K, then it's just going to be 3.5 ohms. What does that get us? All right, that went a little bit too far. And let's go back to 3.4K. Close enough. All right, 3.4K, and there we go. So we're exactly what we want. We've got 1 milliamp of current, we've got this 3.4, and this sets this up nicely, all right? And again, we've dropped about 0.6 volts, in this case 0.66 from the base to the emitter, and this is what we want. So this kind of biasing is called voltage divider bias because there's a voltage divider here. And now the question is, these two resistors, can we make them anything we want as long as the ratio is correct? Well, yes and no. So the smaller you make them, two things are going to happen. One, you're going to burn more current, right? Because forget about the base current, it's very small. If these resistors are small, then you're going to have a lot of current going through here. But the lot of current creates a very stiff, it's called stiff, S-T-I-F-F, stiff voltage divider. And what's nice about that is that this reflected impedance over here, when it commingles with this resistor right here, it'll have no effect on it, because say this was 340 ohms, or say it was 3.4 ohms, and this 100K is going to have no effect on it, right? And we can do that. So will it still work? Let's just take the K off. All right, take the K. Let's not take the K off. Let's just go down by 10. Let's go 680, and we'll go 340. All right. So now this is really, really stiff, and because it's stiff, this 1K is not going to affect it so much. Now we're going to probably set this voltage a little too high, and then we'll get a little bit too much current. All right, and look at that, we got 1.01. So let's back it off now. Now that it's so stiff, we can back this off more to our computed value, and there we go. So again, we could maybe make it a little bit higher, but 330 is a common value. But now this is very, very stiff, all right? So what's nice is that it's going to be invariant of this impedance over here, all right? So, but it worked fine with the other two values, so let's just put those back, all right? Okay, so that's good, perfect. All right, now let's go play with our load. So we got 1 milliamp down here. All right, let's make the load 100 ohms. All right, sure enough, we still got the 1 milliamp, perfect. All right, let's go make it 1K ohm. All right, perfect. Look at that, exactly 1 milliamp. So this is working out good. So you see, this is really nice. Now let's go to 2.2. Now remember when we went to 2.2, we lost a good amount of that current last time. Remember, it was like I think it was a 0.86 milliamps. But look at it now; it's still exactly at 1 milliamp. So see, programming it with this voltage divider bias is a much more accurate way to set this. And now let's go to, I think, 5K. All right, and there we go. So at 5K, we've basically the entire voltage is almost dropping over this resistor, and this collector is only 0.94 volts above the emitter here, all right? And even still, it's still working, all right? So we're still getting almost our 1 milliamp here, okay? All right, we're almost getting our 1 milliamp, so that's really nice, all right? Okay, so that is this model of doing this and this technique of doing this. So let's take a look at another technique. All right, let's stop the simulation. Let's go back to our drawing program here. Okay, so now what's another way we could set this bias here? All right, so what's another way we could set this bias? So why don't let's do this. Let's erase this, and again, we'll kind of, and we'll erase all this stuff here. All right, so what we are looking to do here is, what is another technique we could use? So the voltage divider was really good. Is there something else we could do to get this where we want this? So could we potentially use maybe a diode or diodes, right, to set this voltage, right? So is that a possibility? So could we use diodes or a diode, right, like a Zener diode or normal diodes? So let's think about that for a second. Let's do an example, and as a matter of fact, let's erase some of this here. We'll erase this 1 milliamp here, and let's erase this right here, and we'll erase that right there. Okay, and let's erase this 68% here. Okay, so forget about the base for a second. Can we create a circuit that sets the base at a voltage with a diode or a Zener diode, right? So let's try a Zener diode. All right, so what I'm going to do here is I'm going to draw in a Zener diode. So remember, this is the symbol for a Zener diode. And we're going to put that to ground. And now here, R1, and let me just break this for a second. So if we have this circuit right here, we have 5 volts, we've got R1, we've got a Zener diode. This node right here is going to sit at the Zener voltage as long as R1 is small enough to allow enough Zener current to maintain Zener regulation. So we need to set R1 small enough so that we can get Zener regulation. And we need to look at inside of the specifications for the Zener, but let's just say 1K. So at 1K, right, how much current are we going to get at most? We're going to get 5 volts divided by 1K. So 5 divided by 1K, remember volts divided by K is milliamps. So this is 5 milliamps, all right? So we've got a total of 5 milliamps going through here. So as long as that's enough to keep the Zener going, so this I Zener, right? And then as long as there's enough, this IB here, to put the transistor where we need it, then we'll be okay, right? So now let's assume that the Zener was a, let's make it a 3.6 volt Zener, all right? So we'll say that the Zener diode is a 3.6 volt Zener, All right. If it's a 3.6 volt Zener, then what voltage is going to be over this RE right here? So there's 3.6 volts here. We're going to drop 0.6. So right here, and let's do this in a different color. Right here, right, is going to be 3 volts. All right, so we got 3 volts right here. All right. Now we can set our current to whatever we want by setting RE. So if we want 1 milliamp, we would set it for 3K, right? So let's instead let's get 3 milliamps out of it. So we want 3 milliamps. So if we want 3 milliamps, we're going to set this for 1K, right? So 1K. So that let's take a look. So we got V equals I times R. So V is 3 and R is 1K. All right. So we're going to get 3 volts divided by our R of 1K. All right, and volts divided by K is going to be 3 milliamps. So we programmed the current for 3 milliamps. So we're going to get 3 milliamps here. So I sub E equals 3 milliamps, and I sub C will also equal roughly 3 milliamps, all right? It'll be a little bit less I sub C, but I sub E will definitely be 3 milliamps, all right? Because remember, I sub E is where I sub B and I sub C sum up always, all right? And what will I sub B be? I don't really care. It's going to be 1/100th, or it's going to be this divided by beta, right? But we don't really care. We're not doing the circuit like that. We're forcing the voltage here and letting things happen from there. All right, so we're using the Zener regulation properties to set the voltages. So this is very slick. All right, so, and again, we can make the load anything we want. So let's set up this circuit right here and let's see what happens. All right, so we're going to put a Zener in here, and then we're going to put a 1K here, and this should roughly set the current to 3 milliamperes. Okay, so let's go over to the simulator and let's see if we can set this up. Okay, so we're over here in the simulator. So the first thing I need is a Zener diode, right? So we'll press P for parts, and then I'm just going to type in Zener. All right, and we're looking for a 3.6 volt Zener, and we can also put Zener 3.6, and then you can see all these things come up. So we got a 3.669, we got a 3.6500, and we got a bunch of different things here to choose from, right? And we could look at their data sheets and all that. But let's just do something middle of the road here. We'll pick this guy right here. It's a 3.6 at 500 milliwatts. It can handle, so that's not bad. And then these, we're not quite sure what their other specifications are, but we'll just pick this one at 500 milliwatts. All right, and hopefully it has a model for it. All right, so there's our Zener. So now I'm going to do is I'm going to get rid of R4 here. I am going to now set this. What did we say? We're going to set this at 1K. That's going to give us a total of 5 milliamps of current. Some of it is going to have to go into the Zener to keep its regulation, and the rest can go into the base as needed. All right, and we may have to modify this 1K a little bit. And now let's make this load resistor up here. We'll start it off at 0.001 ohms. 0.01 ohms. That should be good. All right, so now when we turn this thing on, what we're looking for is 1 milliamp of current here, right? If everything goes right, and this base should be at approximately 3 volts. Or excuse me, the base will be at 3.6 volts, but the emitter will be approximately at 3 volts, all right? And as a matter of fact, just so we can see that, we'll put another voltage sensor here, right there, okay? All right, here we go. And oh yeah, I'm not saving this, so let's not save this. Okay, ready? Here we go. Let's run the simulation. Okay, so one problem is we maxed out the sensor here because it's in microamps. Let's put it in milliamps. Okay, now let's run it again, and that should run. Okay, good. So we were looking for 3.6 volts, and sure enough, we've got 3.54. Now, we could actually get 3.6 by driving this a little bit harder. Now, over here, we've got 2.86, and we were looking to get 3 milliamps, all right? So let's drive this a little bit harder, and so we get a little bit more current. So how about, instead of 1K, let's do 680 ohms. Let's see if that helps us out. All right, so we got closer to the 3.6, and now we're at this 2.87 here, okay? So again, if we wanted this, so now it looks like we'd like a higher voltage here, right? this transistor into exactly where we want it to be. So maybe instead of a 3.6, maybe we use a 3.7 or 3.8 or a 3.9 Zener, so we don't have to drive it so hard to get it to where we want. But this is close enough. All right. So now when we start off here, we've basically, take a look, the collector is almost at the source voltage of 5 volts, right? So there's very little going on because this load is so small. There's no voltage drop over it, all right? And we've got our 3 milliamps, okay? All right, so we've got our 3 milliamps of current that we programmed it, and that's what we want. So let's go ahead and let's change the load resistor. Let's make it 10 ohms and run it. And sure enough, we've still got our 3 milliamps, almost, 2.87. Right, let's make it 100. Again, 2.87, not even flinching. Let's make it 1K. And 2.79, so we lost a little bit. And now let's make it 2.2K. 2.67, so we lost a little bit more. And now we'll make it 5K. And we lost a little bit more. All right, so again, there it is. That's working. Now, what we could do is we could set this a little bit higher instead of making it stiffer. So we could go here and we could say Zener, and we could say, how about 3.9? All right, and we got these 3.9, and let's grab this one. All right, this 22B. All right, and here it is here. All right, and I'm going to rotate that, and I'm going to delete this D1 and put this here. Okay. And now I'll change this back to 1K, and that's setting up our regulation and so forth. So here we go. All right. And now in this case, this Zener, we've only got 3.19, so that's not helping us. So we need to drop this more. So let's drop it to 500 ohms. Actually, let's use a common value. That would be 470 ohms. So let's drive it a little bit harder. All right, and now we can see we're at 3.78. And then when we have the voltage drop from the base to the emitter, now we're getting this 2.87 volts here. All right, so we're getting a larger voltage drop over here. And the reason why is because we are driving more current through it. Before we're driving 1 milliamp, now we're driving 3 milliamps. And because of that, that base emitter junction is dropping a different voltage. And that's why these things are not exactly stable. They change, these models. But we were pulling the 5K, so let's put a 1K there. All right. Okay, and so now in this case, now we're closer to what we're trying to get here. So we've got 3 milliamps at 1K, and then I can guarantee, of course, if we drop this down to 100 ohms, we're going to have our 3 milliamps and a little bit more because we're a little bit higher here, right? And then if we go to 2.2K, then we've got 2.94, all right, for our current. And let's go one last time to 5K. All right, now, so we got 5K and we got 3 milliamps. Let's do something. So we take 5K times 3 milliamps, and that's 15 volts, right? So what's going to happen here? So that's not going to work, right? So we're only getting this 2.87, all right, 2.87 milliamps here. So again, we'll take the 5K ohms times the 2.87 milliamps, all right, and so no matter what's happening here is that the current that's coming through here, that's getting driven through here, we're exceeding what the source is providing here, right? Because if we look at what the source is, it's 5 volts. All right. So what's happening here is we're saturating this transistor, and now this is no longer working correctly, but it's still trying to maintain, because this is a voltage follower, it's still trying to maintain that that current. Now, what is interesting now is right here. Let's run this. We've got 2.87 milliamps, and right here we've got 5K ohms. All right. So now obviously we can't have 2.87 milliamps flowing right here, because if we've got 2.87 milliamps flowing there times the 5K, we've got 14 volts dropping over that. That's not going to happen. So now let's take a look. Let's open this up. We'll just pull this down like this. Now let's open this up right here, and let's see how much current is flowing in this branch right here. So we will put a current meter in here, and these they don't really rotate very well, so we got to kind of do it like that. Okay, so now let's go ahead and run this. And look, we're actually only getting 0.42 milliamps here, but we're getting 2.87 here. So what's happening is no matter what, we've programmed this emitter a voltage, and therefore this current is going to be this current. So it's getting this current right now. This current is coming from this base right here. So you're getting this base current is what's happening here. And this current right here is no longer what we wanted. And we wanted 2.87 milliamps to our load, but this is not going to work with a resistor this large. But it will try to maintain this current down here, but it just can't do it up here. But if we drop this back down to 100 ohms, right, then lo and behold, we actually have our program current. Our 3 milliamps is up here, our 3 milliamps is down here, and some change, and everything is good. And again, we can now, let's increase the resistance to say 500 ohms. And again, now we've still got our 3 milliamps, we got our 3 milliamps. So this is a really nice circuit. So what it's going to do is it's going to try and maintain that current no matter what until you get to a point where it can't maintain it anymore. All right, and so and then it just stops functioning. All right, so that's another way to bias these voltage followers. All right, so now in both cases we've been using this as a current source, but if we open this up just a little bit and make a simple change to it, then we can kind of use this as a voltage regulator also. So let's take a look at that, and then we're going to finally go to the amplifier. So we're back here, and so this worked, and this worked great, so this is fine. Now what I'd like to do is let's just kind of go down here for a second, and what I want to do is I want to show you another circuit. So let's take our transistor, let's get our emitter here, all right, and I'm just going to put a very small let's just put a 1 ohm. 1 ohm current limiter right there. This is going to go to V sub CC. All right, then what I'm going to do is I'm going to put a resistor here, like this. Then I'm going to put our Zener diode, and we could use the voltage divider bias as well, but we're going to do a Zener diode right here. And let's say we want a 5-volt voltage regulator, a 5-volt voltage regulator. These are just never easy to draw. There we go. All right. So we'll put this to ground. All right, so why don't we get a 5.6 volt Zener? So we're going to get a 5.6 volt Zener, and we're going to set the Zener current. We're going to set this so that we have enough Zener current to maintain this. So why don't we say, let's put this at 470 ohms, okay? And now here is the interesting part. This node right here is going to sit at, so this is a plus to minus, it's going to drop about 0.6 volts when it's on, 0.7 as it turns on harder. And then, so we'll have 5.6 here, therefore at the emitter, the voltage at the emitter equals what? The voltage at the base minus 0.6 or 7, right? Which is going to equal, in this case, 5.6 volts minus the 0.6 volts, and lo and behold, we've got about 5 volts, approximately 5 volts. So now, no matter what load we put on here, so we can put any load we want, so we put our load here, and that now we're going to call this RL because it's the load now, and then this is a limiter, right? So we could call this R limit, and this just limits the current so we don't damage the transistor. All right, so now no matter what RL we put here, we're always going to get 5 volts here, all right, within reason, all right? And so again, let's look at what's going on here. We've got a current coming through here, all right, and that current is going to come through here, then some of it splits off this way, some of it goes down here. This is the Zener current. The current going into the base is the base current, right? And then that's going to create a current here, but we're only going to get that current, let's just call that IE, when it's down here. We're only going to get IE when you place a load here. With no load, it'll just sit and not do anything. Then once we put the load, then this transistor will adapt and adjust. This voltage is going to want to be stuck at 5 volts. So no matter what it's going to do, it's going to say, I need to be 5 volts. To maintain the properties of the transistor in this forward biased junction here. And then whatever this resistor is, it'll set the current. So say if we put a 100 ohm here, all right, so we put a 100 ohm, so there's 5 volts and 100 ohm, let's do it. 5 divided by 100 equals 50 milliamps. So equals going to give us 50 milliamps. All right, let's put a 1K ohm resistor. All right, so that'll be just 1/10 of that. That should give us 5 milliamps. And let's put a 330 ohm. What will the current be? So again, we'll do 5 volts divided by 330 is going to give us 15 milliamps. All right, so if we build this circuit and add loads to it, we should see this kind of behavior out of this. All right, so let's give this a try. So 470, 5.6, a 1 ohm, which is just the current limiter, and then we'll try 3 different loads, 330, 100, 330, and 1K. All right, so I'll keep flipping back and forth so I can figure out what I'm doing here. All right, so let's make sure the simulation is dead. There it goes. Okay, so the simulation is off. All right, we're going to come back here, and we said we got a 470 there. All right. And so we got a 470. Let's go change this, and we're just going to make this 1 ohm, and that's just the current limiter now. All right, and now this is going to be our load resistor. All right, so now we're no longer, and we need to get a different Zener voltage here. So we need to get a 5.6. So we're going to go over here to parts, and we're going to get a Zener 5.6 volts. There we go. And we'll just pick something here, a regulator diode. Well, this one says it's a regulator diode, so we'll just pick that regulator diode. All right, and again, some of these are, so there's, the Zener diode can be used in different ways, and many of the times it's used as a regulator. So they might manufacture it slightly differently for that application. All right, so right now we've got this 1K load here, which is going to pull very, very little current. Let's make it 10K. All right, so very, very little current, so this thing should regulate very well. All right, and so we got 5 volts here, and then now we've got 4.37 volts here, all right, at this 10K. So now let's go ahead and let's decrease this to 1K, all right. All right, and now we've got this 4.23 volts. All right, let's go back and make it 10K again. We had 4.23 and we had 4.37. So kind of what's going on here? What's going on here is we're going to need some more current. And we just don't have enough current going into the base here. So what we're going to do is let's lower this. We'll lower this to 330 ohms. Okay, and so now, so we have, this is sitting at 5 volts right now. And that's not what we want. What we want to do is we want to get this to sit at 5.6 volts so that this drops down here, right? So we want to get this to drop down. So let's get rid of this guy, and that might be giving us some trouble here. So let's make sure 5.6 volt Zener, and let's take a 500 milliwatt, this one. All right, let's put this one in here. Okay, so I made a couple changes here. So I just got a different Zener, and this is a 5.6 volt Zener. And then we put a very, very small load, a large value, a small load, and then we're going to run this. And we see that we have 5 volts here, but we've got a 5.6 volt Zener. So what's wrong? Well, what's wrong is we were trying to do a 5 volt regulator, and we forgot, because it's off the screen there, that we only have 5 volts in the system. So let's put this up. Let's make this 9 volts, all right, DC, all right? And we're going to set it to 9, all right? So there we go. Okay. Now let's try it again here. And that's much better. So now, and that happens also. So you got to be careful, and it's hard, when you're doing this stuff live. You're like, what is going on? But that's why I can edit things. All right. So now we've got our 5.6 volt Zener. We've got it at 5.6 volts almost at the 1K, so that's good. Therefore, we're going to have about 5 volts here at the emitter. And with our 100K load, let me put the whole screen on here so you can see it. At the 100K load, we've got our 0.05 milliamps, which is what we should have at 5 volts. So this is nice. So now we've got a regulator here. So now at 100K, we've got 5 volts. That looks good. Okay, so let's start going in powers of 10 here. So let's put a 10K load. All right, 10K load. Do we still have our 5 volts? We've almost got 5 volts. We only lost 0.06. All right. So now let's go to 1K. 1K. All right. And now we got 4.87. And we've got 5 milliamps. All right. So all the way from nothing to 5 milliamps, we've only gone down 13.13 volts. All right. Or 130 millivolts. All right. Now let's go down to 500 ohms. All right. 500 ohms. And now we got 10 milliamps and we've dropped 0.15. So we're still looking, not bad, not bad. Better than most power supplies you can buy on the market, frankly. All right, now we're at 50 ohms. All right, so now we're pulling 100 milliamps. We've only dropped to 4.7. Can we do a little bit better? Can we get this to regulate a little bit better? Can we? So let's turn this the base up a little bit. So let's go down to 470. All right. And well, before we do that, let's look at what we got again. Let's make sure here. So in this case, we're at 4.7 volts. Can we get that voltage up a little bit higher? All right, so let's put this at 470 and keep that regulation a little bit better. 4.75, right? That's not bad. And we've almost got our 100. Now let's go all the way back down to our 100K. And let's make sure we don't go too far in the other direction. 100K. And we got 5.03 volts. I can live with that. So unloaded, so basically unloaded. So 100K is like unloaded. Let's make it a million, right? So let's make it 1. I think M per million will work. Let's see if it does. Yeah, so totally unloaded. If we had a megohm, right, we get 5.09 out, so that's nice. And then if we really load this thing and go all the way down to 50 milliamps, 50 ohms, which is going to cause 100 milliamps, we only drop down to 4.74. All right, and then again we see is the transistor still operating or is it saturated? So the collector is at 8.91 volts, so we're still okay. It's above the emitter by 0.2 volts, which is fine. We've still got the 100 milliamps coming through here. Here it is. There's 94 here and 93 here, so there's a little bit more here because it's combining with the base current, so that's good. All right, so and everything is working, so all the voltages are okay. What is the power dissipation? Let's figure that out real quick. So we've got 8.9 volts here, and we've got 4.7 volts here, and we've got a current of 94.8. So what's the voltage over the collector-emitter junction? Well, it's 8.91 minus 4.74. That's 4.17 volts. What's the current through here? It's 94.8. It's this current right here, 94.8 times 94.8 milliamps. So that's 0.4 watts. So now, or 400 milliwatts. Now, if we look at this, let's stop the simulation. If we look at this particular diode here, and it does not have it here, but if you recall, the other ones were like 500 milliwatts. So we're at 400 milliwatts, we're at 400 milliwatts on the transistor here. And then we'd have to look at what the power dissipation is on the diode. Now on the transistor, it can probably handle more. If we look up a 2N222, let's do that real quick. Let's go look up a 2N, and this is actually I think it's PN222A. Let's look this up here, and we'll just grab a power max of 625 milliwatts, all right? So 625 milliwatts. So, we're okay with kind of a garden variety. And then we would look up the D1, but we already know that it was 500 milliwatts for the part that we're looking at. And so this is at 5.6 volts right here. This is at 5.6 volts. Let's run it again. So this is at 5.6 volts. And then we could look at what the current is here, and we could look at what the current is here. So there's 7 milliamps coming down through here, right? 7 milliamps coming down through here. Just a little bit of it is coming through this way, and the remainder of it is coming through down here, all right? So for now, we can just call it 7 milliamps. So 7 milliamps and 5.6, so we got 5.6 volts times the 7 milliamps, call it 7.23 milliamps, even though some of it's going to go into the base. and that gives us only 40 milliwatts. So we're within an order of magnitude of heating up the diode, but the transistor is getting hot. So when we're running this 100 milliamps through here, this would actually be getting very hot. And even though it could handle 625, we're at 400 milliwatts. We're 2/3 of the way there. If you put your finger on it, it'd probably get really hot. All right. Now, let's go one little step more, and then we'll wrap this up, and we'll come back in the next one. So let's go to 25 ohms. At 25 ohms, we've dropped a whole volt. This is, at this point, we're not regulating as far as I'm concerned. This is too much to lose. We've lost basically 20% of our voltage. This thing is maxing out. We're at 163 milliamps, and we're probably overheating this at this point. So we've got about a 4.8 volt drop over here. So we got 4.8 volt drop from the collector to the emitter, and we've got 163 milliamps, 163 milliamps, and we've got 780 milliwatts. So we're overheating this and damaging it at this point. Okay. All right. So so that is, we talked about the biasing. So we either use voltage divider bias, two resistors, or we can use a Zener diode. And instead of just doing one-legged setting of the current, we do two-legged and we set the voltage. Then that programs the current here, or if we just use it as a voltage follower or emitter follower, then we can get a voltage regulator out of this thing. So pretty cool. All right, but the thing to remember in this configuration, the voltage here follows this base voltage. So it follows whatever this input voltage is put in. So there's no amplification of voltage. So this is called an emitter follower kind of amplifier, or just a voltage follower, and it's called common collector because of its configuration. I'm going to show that to you in a different image because it's easier to understand. So anyway, so that's this one, and when we get to the bench, we're going to build a bunch of these things, actually build them also. But let's stop here, and then let's come back and let's talk about this here a little bit more. So now that we've done the voltage divider thing, we're going to actually talk about this single stage transistor amplifier, which is not going to amplify voltage, because we know anything we put under the base is just going to come out on the emitter shifted by 0.6, 0.7, but it can amplify current. So if you have a very weak signal, voltage signal, we put it through one of these transistors, and now we can drive something like a speaker with it, as long as we don't need voltage gain, but we need current. All right, so we'll stop here and we're going to come back and talk about this design right here, which is a type of amplifier. Okay, so I'll see you in the next lecture. All right, so let's go ahead and let's make this 10 microfarad. All right, and this will give us a 15.9 hertz 3 dB. So that nicely cut in very early. This one's going to give us a 25 hertz 3 dB. All right, and so that's it. So now we've got this AC capacitively coupled on the input. This ends up being a high pass filter here. We've got this AC coupled here. This is another high pass filter, high pass in, high pass out, and the high, it's not very high. We're talking about hertz here. Anything over 25, anything over 15.9 is going to pass in and pass out. Okay, so let's go to our simulation and put these values in and see what we see. And let's see what's changed. So this one right here, let's put this as a 10 microfarad. All right, we got 10 microfarad. All right, now, so we've got this capacitively coupled. We got 10 microfarad, we got 1 microfarad, we got 5 volts here to set up our power supply and our DC quiescent point or operating point. Then I have this thing called fast sine, and I don't know, is this simulation running? Hope not. All right, so this fast sine, let's go in here and double click this, and what do we got going here? So the frequency is 10 kilohertz, right? So this would pass very easily. So let's just put it at 1 kilohertz for now. So it's 1 kilohertz and an amplitude of 1 volt, all right? So that 1 volt is going to definitely stay within our 2.5 volts that we have for top and bottom range, right? Because we set the quiescent point at 2.5 and we've got a 5 volt range, right? So we're okay. All right, so that should all be good. And I should just be able to run the simulation. And as I run the simulation this time, now as a matter of fact, let me put it over here a little bit. And you got to forgive this scrolling. every one of these apps, I don't know, they just mess around with the mouse scrub bar, scrub wheel, and I modify it so that it works good with the browser, then it doesn't work good with the app, doesn't work good with the paint program, it just doesn't work correctly no matter what. So anyway, it's not scrolling very well. Okay, so now we're good. Now when I run this, it's going to put this oscilloscope up. Remember, we've been having trouble with the oscilloscope, so let's hope that this thing works good this time. All right, let it kind of do its thing. Okay, all right, it's working. So we've got a 1 kilohertz signal. So what I'm going to do here is I'm going to change the sweep rate. All right, now, so let's see what we got here. So the yellow trace is the final DC plus AC signal. That's the yellow trace. Then the green trace is the input signal. All right, and then the blue trace is the final output signal after it's been AC coupled, which also it's been filtered and coupled. So that means that it has no more DC. So this will be relative to ground. So this will be relative to ground, all right? And the green signal will be relative to ground. So if we look at the blue signal and the green signal, they should be identical, all right? They should be absolutely identical. And look at that. So here's the blue scale. The blue scale is at 0.5 volts per vertical division. The green scale is at 0.5 volts per vertical division. Now, if I take the blue channel and see where its ground is, see that little white line that gets drawn there? Let me do it again. That white line, that's ground. And remember, since it's AC coupled, it has no DC offset. Now, and also look, I've got the oscilloscope on DC, so it'll show us a DC offset if there is one. It won't filter it out. See, the oscilloscope, the virtual oscilloscope, has AC and DC coupling inside of it, so it can kind of do what these capacitors do. But we've turned it off, and we're just saying, show us DC. So if there's any DC, it'll show us. But as I move this around, you see that white line, there is no DC. All right, so now the green signal, same thing, there's no DC. So when I put those on top of each other, look at that. They exactly follow each other. So this is exactly what the emitter follower does. So they follow each other. But look at the yellow signal. Let me move this down. The yellow signal is what? The yellow signal is the green signal added to the DC offset of 3.27 volts here. So that's the yellow signal. Now watch when I move the yellow signal around. Look where its ground is. There's its ground way down there. Let me move this here. So look at this. See that? It's riding really high. So it's riding up here and then going around that, riding up and down or wiggling. So you'll hear electrical engineers say wiggle, wiggle, you're going to wiggle the signal. All right, but that's what we say. We say we're going to wiggle the signal. So we're wiggling the signal off of a DC offset, and that DC offset is what? 3.27 volts. Let's count it up. So right now we're at, I know this is hard to see, but it's at 0.5 volts per vertical division. All right, so what I'll do is I'll line it to the little red line. So that's ground. I know that's ground now. So 1, 2, 3, 4, 5, about 6. What's 6 times 0.5? 3 and some change, right? So there it is. So 3 and some change, 3.27, that is exactly where it should be. And then it's wiggling around that. And now what do we have? We have a current amplifier that's amplifying the current. So we get a stronger signal out of here. Then we put in, but the voltage stays the same, and you see it's following. So the blue signal is the output, the green signal is the input, and it just stays the exact same. Hopefully this doesn't crash. All right, now, what do I want to do? Oh, so we've got a high-pass filter. So what is the filter? The filter cuts in at about 25 hertz on the input and about 15 hertz on the output. So let's slow it down to like 10 hertz. And when we do that, what we're going to see is the output, which is the blue channel, is actually going to get smaller, all right, because we're going to attenuate it, all right, and hopefully the oscilloscope will keep running. So let's stop it. And let's change this to 10 hertz. And let's run it. All right, let's cross our fingers that the oscilloscope pops up. Yay, it pops up. And look at that. Just like I said, the blue signal, which is the output, is now attenuated to the green input signal. And it should be because it's actually getting filtered. What's happening is we're here on the curve. We're here at this frontal part right here. We're coming into the full gain 1.0, right? So this would be the 0 dB point. 0, remember, means 1 is the gain. So we're coming up into this point. We're right here right now, so we're much lower. And then after we get past 10 hertz or 25 hertz, then we're going to get all this 1.0 gain or 0 dB, and then the signal will come up full. All right. So let's go ahead and let's stop the simulation, and let's go ahead and put this, and we'll put this at about, oh, let's put it at 50. Let's put it at 50 hertz. All right. That's not going to get us all the way there, but it'll get us most of the way there. All right. And as you see, if I zoom this out a little bit, and I'll bring the blue signal down on the green signal, and you'll see it's almost, you know, just a hair still attenuated, and it should be, right? Because remember, we're looking, now we're up around here, right? And if we went a little bit more, maybe 100 hertz or 200 hertz, then we would be identical. All right. So great. So good. So so that's perfect. So we'll save that and leave that one as is. So let's go back here. So that's it. So that is the emitter follower, which is a voltage follower. So that's the emitter follower amplifier, or it's also called a common collector. And the reason it's common collector is, see the collector up here is kind of common to the input and to the output because it's there's no resistor up here. So this is also called common collector. But and then we've got what? Voltage divider bias. And then look at all these things we've got in here. We've got a high pass filter on the input. We've got a high pass filter on the output. We've got AC coupling on the input. We've got AC coupling on the output. We knew how to compute the quiescent point. It's called quiescent, which just means the operating point. We set the bias at roughly 3.2, 3.3 volts, which then we know there's going to be a forward voltage drop over the base emitter diode of 0.6 to 0.7, which is going to set the voltage at the emitter to a steady state of roughly 2.5. The 2.5 is halfway between our voltage range of 0 to 5 volts, which is what we want so we can have maximum swing. Then we go ahead and we put our input in. As long as our input is smaller than 2.5 volts, high or low, it'll stay within range and won't get clipped. And then we computed what these capacitors should be so that we could process audio signals from the common kind of standard of 20 to 20 kilohertz is what is commonly thought of to be a reasonable audio range for humans. And that's it. So that's an amplifier. And like I said, this is probably way more than you're going to need to know, but this is nice to kind of work through this. So now what we're going to do is we're going to stop here. And the next lecture, we're going to do the common emitter amplifier, which is kind of, I don't know if you can have a favorite amplifier, but I kind of like the common emitter amplifier because it's pretty easy to build. It's fairly easy to understand, and it's a voltage amplifier. And so that's a voltage amplifier. All right, so this one's going to be called common emitter. Common emitter. And the one we just did is called common collector. Common collector, or it's more of an emitter follower. Emitter follower, just because the voltage follows the base. All right. So typically when you're making amplifiers, you have these three different things you want to amplify: current, voltage, power. So we just did the current. Now we're going to do the voltage, and we're going to leave the power for an exercise. All right. So so this is a good lecture. So let's stop here, and I will see you in the next lecture, and we'll talk about voltage amplifiers. All right. Bye. All right, welcome back, and we're on the next lecture of transistors in this transistor marathon that we're doing. Like most things, we have to keep kind of building up on the previous work, and so now, if you take a look at the screen here, we were working on the emitter follower amplifier, and we went through this entire analysis. And if you recall, the emitter follower or a common collector amplifier, what this is good for is amplifying current, not voltage. So this is amplifies current and not voltage. Of course, the emitter follows the base, right? And it's basically shifted by 0.7 volts, 0.6 volts. And then we set the bias point here with this voltage divider bias. and then we AC coupled the input and the output, and these resistors and capacitor, and this capacitor and resistor both form high-pass filters, and we set the 3 dB point so that it would basically start passing at audio frequencies of 20 hertz and higher. All right, so we're all done with that, and so now we're finally going to get to an amplifier that kind of does something useful, more useful I think than this, even though a current amplifier is very, very important. So this is more like a buffer, so that you got an input voltage signal, and then you get the same signal out, but now what you've done is you've buffered it and you've increased the current drive. That's definitely useful, but amplifying the voltage is something that is more useful in my opinion, because a lot of times you have a small signal and you want an amplifier architecture to amplify the voltage. All right, so that's what we're going to look at now. So it's very similar to this, and actually I'm going to redraw all of this, but all we're going to do is we're going to add a resistor right here, all right, and this we'll call this R sub C, and then instead of taking the output here, we're going to take the output here, all right, and this will be our V out. So very similar to this, and the analysis will be very similar, but let's go ahead and let's erase all this. Okay, so here we go. So let's get a color here. So we're going to be talking about the common emitter amplifier. And again, we're going to be using the NPN transistor. We've been just sticking with that because it's easy. All right, and we'll say NPN here. Oops, NPN. And if we want to do with PNP, we just reverse everything, the voltages and the orientation and the directions of the current and all that. Okay, so first let's just kind of draw what this looks like. And we'll call this V sub CC. And as a matter of fact, what we'll do is we'll make that a different color. And down here, we've got our emitter resistor. And over here, we're going to have our input. And what we're going to do is we're going to again use a voltage divider bias to set the operating point. And this sets the DC operating point of the amplifier. All right, or the quiescent point it's called. Now we're going to leave out the capacitors for now, because we'll get to that in a little bit. All right, and we're going to take an output here. Okay, and output there. All right, so now let's start labeling what these things are going to be called. So we're going to call that RC. We'll call this RE. We're going to call this R1. We'll call this R2. And another thing we haven't even mentioned once is these transistors, and let's label this. This is what the collector, this is the base, and this is the emitter. Transistors are typically called Q. So this would be Q1, all right? Same thing with FETs, you call them Q. Q1, Q2, Q3, Q4, all right? So this is going to be kind of the basic construction of our amplifier. And so now let's start setting this up with the values that we want, all right? So, all right, the first thing that I want here is, let's say that first let's set a voltage. Let's set a voltage up here. So we're going to say V sub CC. This time let's set it to about, we could set it to 10 volts. All right, we'll set V sub CC to 10 volts. All right, and then now we just start picking things. Now, if it's 10 volts and we want an amplifier that has the most swing, all right, on the output, that means we want to set this for approximately 5 volts. All right, so we want to set that V sub C, and remember the collector, the emitter, the base, this is V sub C, this is V sub E, and this is V sub B, right? Those voltages on those nodes, right? But I'm going to just erase this, those symbols so we have some room. So we want that to be approximately 5 volts at DC kind of static bias. All right, so when this thing is just statically sitting there, that's going to set the operating point, okay? All right, so first thing, let's just start picking some values here. So what I'm going to do is I'm going to set RE equal to 2K ohms. All right, I'm going to set it equal to 2K ohms. And let's say that we're going to put, let's put 1 volt. So we'll put 1 volt. And again, this is what you do. You just kind of decide what you want to do. All right, so let's put V sub E here. All right, we're going to put this V sub E at approximately 1 volt. All right, and if that's true, then that means that V sub B, right, V sub B up here, all right, that voltage there, we need to set that at approximately 1.6 or 1.7 volts, because remember, we're going to get a plus to minus voltage drop from the base to the emitter of approximately 0.6 or 0.7 volts, right? 0.6 or 0.7 volts will be that base to emitter drop. Now, let's go ahead, so that we're starting to pick things here. Let's go ahead and let's write some equations down over here. So what do we got here? What do we know? We know that I sub C equals the beta times the base current. And remember, this is just for one model. There's many models of the transistor, but we're using this model right here. And so we know that. What else do we know? We know that I sub E equals, and so I sub E is the sum of the two currents, which would be the base current, I sub B, and this current here, which is I sub C. Both of those sum up to make I sub E. So I sub E equals I sub B plus I sub C. All right, so far so good. And so now let's replace I sub C here with this I sub C. So then we have I sub E equals, and you know what, let me make those E's a little bit better. I should probably capitalize those, huh? Let me see, I sub E, does that help? I think so. I sub E equals I sub B plus this I sub C here, but here's I sub C again, which is beta times IB. So this is beta times IB. Okay, so now we see that I sub E equals, let's factor out the I sub B here, and that'll give us I sub B times 1 plus beta. All right, so the two important equations are this one here, right, that one, and this one, which gives us I sub C and I sub E in terms of the base current and the beta. And we can see they're almost identical. So let's write this down for I sub C. I sub C equals I sub B times beta. I just wrote them, you know, just flipped the two variables around there. So we can see that they're almost identical. In one case, it's I sub B times beta. In the other case, it's I sub B times 1 plus beta. Very, very close. So in fact, we can say that I sub E is equal to I sub C, or we can say it's approximately equal to, or we could say, you know, approximately equal to. All right, if we want to make that approximation. And how big of an error will we be? Well, we'll be pretty small. So if we take the ratio of these two things, look at this. If we take I sub C to I sub E, so the ratio of I sub C to I sub E is, what's I sub C here? It's I sub B over beta, and I sub E is I sub B over beta plus 1. So these cancel out. So then we're just left with beta over beta plus 1. So what this is telling us is that if we want to convert from I sub C or to I sub E, we're just going to be a beta over beta plus 1. So if beta was 100, right, that'd be over 101. So it's you know, basically less than 1%, right? So the error is going to be about 1% if beta is approximately 100, right? As beta is higher, then it's going to be even smaller. It's going to be 1 part in 100, 1 part in 200, 1 part in 300, and so forth. As beta gets lower, depending on the conditions, then this error gets a little bit higher, and you can't just say I sub C equals I sub E if you want to be as accurate. But for the most part, we can most of the time say I sub C equals I sub E because they're just going to be 1 part in 100 on average, different from each other. But if you want to do the calculation, then there it all is. Okay, so that's that again, which is a review. All right, and so now let's do some math here. Let's do some math. So if we're saying that the voltage here at V sub E is going to be 1 volt, and we've got 2K there, then this I sub E, this current here, this I sub E, is going to be roughly the 1 volt over the 2K, which is going to equal, let's get our calculator out. Now, hopefully, so 1 divided by 2K, which is 0.5 milliamps. Hopefully, you're starting to get a feel for milliamps and so forth, 0.5 milliamps. And it's important because when you're doing calculations, if you get like amps or mega amps or nanoamps, and you're working with something that should be milliamps, it should immediately, you should kind of have a sense or intuition that these numbers are not right, and you probably multiplied or divided by a factor of 10 or more someplace incorrectly. So that's why I say do it with a calculator, do it in your head until you get a really good feel for this. Okay, so I sub E, and again, we're kind of like not making good E's here, at least I'm not. Let me make that a little bit better. Kind of use this capital E. Okay, so I sub E equals the 1 volt over 2K, which is 0.5 milliamps. Okay, so we got 0.5 milliamps flowing through here. That's fine. We're saying that we're setting this voltage at 1 volt, which means we're going to have to figure out this bias, right? We don't know what these resistors are that set that at 1.6 volts, so we're going to figure that out. All right, and now here's something that we need to calculate. So remember, I said a little while ago, we want to set this in the middle of the range. So right now we've got this 10 volt range, right? And we've done this before. So let's take a quick look at what I'm talking about here. So here is the total range of things. And let's say that this is voltage here. This is voltage up here. And we'll put time down here. All right. So what we're trying to do is we're trying to say if we've got a 10 volt supply, we're going to set the output so that it sits at the middle of that, all right, for all time. Well, the middle of that would just be 10 divided by 2, which is 5 volts. So to have the maximum amount of swing of our output voltage, right, we want to be set at 5 volts. If we were to set this lower, we could have a higher positive swing, but then we would have a small, and let me show you what that would look like actually. So here's what we want ideally. We want a positive swing of 2.5 volts, and then we want a minus 2.5 volts from this 5 volt setting right here. So this is, excuse me. This will be 5 volts up here plus 5 volts, and this will be minus 5 volts. And the reason why is because the top of this is our 10 volt. So we set it in the middle, which is 5 volts. So we can go positive 5 and we can go minus 5 before we hit either of these rails, right? And remember, the rails are just that top 10 volt. And then down here, which I've kind of drawn ugly, this would be the 0 volt kind of thing, all right? So that would be kind of 0 volt. Matter of fact, let's just erase this here. Let's try and draw these things as accurately as possible. Accuracy is important with math and electronics. Okay, that's a little bit better. All right, and so now we're calling this the 0 volt. So this is plus 5, minus 5, so we set the center point or the DC operating point at 5 volts. Okay, so relative to that, we want the maximum amount of swing. Now, what if we said, well, why not set it at 1 volt? Okay, let's set it at 1 volt. So here's 1 volt. So here's 1 volt right here. And we'll just draw a line. And now let me draw this in a different color so we can kind of see it. I'll draw in this kind of pinkish color. So in one case, now we can go from this 1 volt up here. So we have a total of 9 volts of stride, and then we come back down. But then when we come back down here, we don't have negative voltage here. So we're going to get clipped. See that? We're going to get clipped. And this is what we're going to see coming out of here. This kind of thing, this clipped waveform. So let me fill that in a little bit so you could kind of see what it looks like. So it would look like this. It would be clipped because there's no negative going waveform, right? Because we have no negative voltage. We don't want that, all right? So what we want is to set it in the middle, and that's why we set it in the middle, so we can have the maximum signal swing on the output, all right? So we set it to the middle of the voltage range, which is 5 volts in this case. To get 5 volts, what are we going to do? Well, we know that we're setting a DC bias point because of our bias here of 0.5 milliamps is going to be going through RE. Well, if 0.5 milliamps is going through there, then through IE, it's also going to be going through I sub C. it'll be a little bit less, right, because of this. But it'll be so small we won't even notice it, and it'll be well within the area of the resistors we're going to use. So we're going to get 0.5 milliamperes here. So this I sub C is also 0.5 milliamps. Okay, well, if that's 0.5 milliamps and we've got 5 volts here, then we need to figure out what this resistor is to get that. Well, we're 10 volts up here and we're 5 volts here, so we dropped 5 volts. Okay, so what do we have? We have V equals I times R. So V equals 5 volts, or a delta 5 volts, equals I, which is 0.5 milliamperes, times this R, which is what we're trying to find. So R is simply the 5 volts divided by 0.5 milliamperes, right? So R C, and let's make that in green since it's green. We'll say RC equals 5 volts divided by 0.5 milliamperes. All right, and that's going to tell us what RC resistor we need to set this 5 volts right here so that it sits there in DC static mode at 5 volts. All right, so we've got 5 divided by 0.5 milliamps, and of course that would be 10K, right? Because if it was 1 milliamp, it would just be 5K, but half a milliamp means it's 10K, right? And of course the calculator agrees with me. So this is going to be 10K ohms there. All right, so RC is 10K ohms. All right, good. All right, so now we're getting there. So now we've kind of set up what the DC the DC bias is here at by setting V sub B, and now the output will sit at 5 volts when nothing's happening in the circuit. But now we need to figure out R1 and R2 to kind of make this happen. All right, so now we need to kind of go through and figure out what resistors we should use to get 1.6 here, right? All right, so what I'm going to do is I'm going to pick a resistor. So I'm going to pick R1 to be 100K. All right, and remember we can do this arbitrarily because this is just a voltage divider. So the voltage VB, so V sub B, what does it equal? It equals the total voltage, which is V sub CC, which is 10 volts, times this this R2 here, right, over R1 plus R2. And what do we want VB to equal? We want it to equal about 1.6, maybe 1.7 volts, so that we get this 1 volt here at this V sub E, right? Make that better. This is a horrible V sub E. Let's fix that. Okay. Okay. All right. So that's what the math is. So we've got 2 unknowns but only 1 equation, so we're going to have to pick one of these things, right? And remember, we pick these based on the total impedance because we're going to turn this into a filter at some point, and also how stiff we want this voltage divider so that as we input to it, it doesn't modify this voltage. So there's all those considerations which we already talked about. So I'm just picking 100K for R1. Then if I pick R1, then we have to pick R2, or we have to solve for R2. So let's do the math. So we have 1.6 volts equals, and we've got 10 volts times R2 over R1 plus R2. All right, and we picked R1, which is 100K. So let's replace that there. So this equals 10 volts times R2 over R1 plus 100K. Okay, and that still equals that 1.6. Let's write that down again. 1.6 volts equals 10 volts times R2. Now what I'm going to do is, this is down the denominator, this R1 plus 100K. I'm just going to bring it over here, this R1 plus 100K. And let me do that again, so it's a little bit cleaner. So R1 plus 100K times the 1.6 equals this right here. And what did we've got R1 plus 100K, and I just did something wrong. What did I just do wrong? We've got this is what we did wrong. Okay, so let's just start plugging things in here. All right, so we've got the 1.6 volts equals 10 volts times R2 over R1 plus R2. We know that R1 equals 100K. All right, so we can just plug some values in here. So this equals 10 volts times R2 over 100K plus R2. All right, and so now let's go ahead and why don't we take this term right here, this 100K plus R2, and we'll bring it over here. So 100K plus R2 times 1.6 volts equals 10 volts times R2. All right, now we're almost done here. Let's divide both sides by 1.6 volts. And actually, we could have either way. So let's do it the other way. So let's multiply this out right now. So we're going to get 100K times 1.6, of course, is going to be 160K. So this is 160K plus 1.6 R2. All right, and that's going to equal, and let's get rid of the volt, we'll just leave that off for now, plus 10 R2. Okay, so now we can subtract 1.6 R2 from the 10 R2, and we're going to get 160K equals the 10 R2 minus 1.6 R2, okay? All right, therefore, R2 equals, so we do 10 minus the 1.6, 10 minus 1.6, and we get 8.4 R2. So R2 is going to equal the 160K divided by this subtraction here, which is 8.4. So this is going to equal 160 divided by 8.4, which is 19.0K. 19.0K. All right, so if we use those two ohms there, so 19K roughly, 19K. Now, remember though, that this 19K, this R2, is going to see this impedance of this RE here as well. Remember that it's going to get impedance reflected into here. So we're going to get a 19K in parallel with a 2K, and this 2K is going to drag it down quite a bit. So because it's going to be 2K times 100, it'll be 200K. So it's going to be 20K in parallel with 200K. So it'll drag this down a bit. So what we want to do is we want to put this up a little bit more. So we could put it at like 20K. All right, and I think that's what I did in the simulation, which we'll get to in a minute. So we got 100, as a matter of fact, let's go take a look at the simulation real quick here. And yeah, 22K. So you can see it right there, 22K. All right, so we're actually going to, when we end up doing this, we're going to, put this up a little bit higher. And the reason why, so remember, the calculation is a starting point. So 19K is kind of what the math says, but then what we're going to do is we're going to set this resistor at 22K, and then that'll give us more accurate value for this 1.6 that we're trying to get. Because remember, we have to remember this R2 is going to be in parallel with this RE, impedance reflected through the base here. So it's going to be RE times, the beta of like 100. So it'll be 200K. So 19K in parallel with 200K, right? If you do that product over the sum, it's going to be less. So we need to add a little bit, the 22K. So if we do 22K in parallel with 200K, right? The question is, does that get us, because we're looking for a real 19K. That's what we want. But if we put 19K there, it's going to get paralleled with this. So we need to put a higher resistor so that the end result is 19K. So we get our voltage divider bias of 1.6 to 1.7 volts. So what happens when you do 22K in parallel with 200K? So remember, it's the product over the sum. So it's 22 times 200 over 22 plus 200. Now you notice what I did here was I got rid of the K, because since they all have Ks, we can divide by them and cancel them out. So 22 times 200 divided by 22 plus 200. And that gives us 19.8K. Perfect, 19.8K. So by putting it up to the 22, we get closer to the 19 that we want. And when I run the simulation, I found that, and 22 is a common resistance value, so that's why I set it like that. We could probably get a little bit closer by making it 21K, but 22K is common, and that's close enough. All right, so with those two resistors, for R1 and R2 of 100K and 22K, now we're done. We've set the DC point here for 1.6 volts for this bias. That means that the base emitter will drop about 0.6, 0.7. We'll end up with 1 volt here, right? We'll end up with 1 volt there on the emitter. That 1 volt will then cause 0.5 milliamps of current to flow through this 2K resistor, which will then also cause 0.5. This I sub C will be the same. It'll be a little bit smaller, but close enough. It will be 0.5. And now we say, well, we want to set the DC operating point of the output swing so that it's in the middle of the range. And what's our range? Well, we look at our power supply, and it's 10 volts. So what's half of 10 volts? 5 volts. So I want to set it at 5. So what resistor at 0.5 milliamps results in an output of 5 volts? Well, that would be 10 volts minus a 5 volt drop here, which means we need a 10K. So that gets us all of this, okay? So that gets us all of this. All right. So now what I'd like to do is this. I'm going to jump to the simulation, and we're going to take a look at that, and then we're going to stop, and then we're going to do another lecture, kind of follow right up. But I want this to sink in a minute. But let's look at the simulation, and then we're going to come back, and we still haven't figured out what this does. So it's supposed to amplify voltage, right? It's a voltage amplifier. So let's write that up here. Common emitter amplifier, and it's supposed to be a voltage amplifier. All right, that's what it's supposed to be. All right, but right now it's not clear that it's doing that because we haven't done any analysis, but the analysis is fairly complicated. So let's take a pause, let's go look at a simulation, and then we're going to come back and we're going to do the math and show why the simulation does what the math does. All right, so let's go look at the simulation. All right, so this is called Crash Course EE Transistors 04. And so here's the exact circuit. So we got our 100K, we got our 22K, we got our 10K, we got our 2K. And then on the input and output, we've got two capacitors. And remember, all that's for, and we'll add that in. All those capacitors are for so that we can leave this thing at a DC operating point, and then we're going to add an AC signal, a small one, and we're going to wiggle. Remember the wiggle term. We're going to wiggle the input, which is going to cause a wiggle on the output, and it's going to be somehow amplified or attenuated or something. We're not sure yet, but that's how we couple the signals in, through AC coupling, and we're going to actually do that when we come back in the next lecture. All right, but for now, let's go back to the simulation. All right, so we agree we've got the same thing here, and then all I did here was I changed this to 9 volts because it's a common battery voltage, 9 volts, and it's almost, and I didn't even change what the values are. They actually are close enough so that we get what we want. So let's go ahead, and first thing that I'm going to do is I'm going to cut off, and here's the input. And the input is running at 10 kilohertz, and its amplitude is 10 millivolts, all right, 10 millivolts, all right? But what I'm going to do is I'm going to just cut that off, turn that off, all right, and then I'm going to run the simulation. And forget the oscope. And let's look at the DC operating point here. What's going on here? So look at our base. It's at 1.58 volts. And that's perfect because we wanted 1.6 volts roughly, right? 1.6 volts. So that's looking good. Then our emitter voltage, look at that, it's 0.95 volts. And we, of course, wanted 1 volt, so that's looking real good. And then, of course, if we have a 2K resistor, that means we should have about half a milliamp, and we sure do, 0.47 milliamps. That's nice. Then with our 10K here and our 9 volt source, then we should get 9 volts minus 10K times the current. So look at our voltage here. We're sitting at about 4.7 volts. 4.3 volts is where we are relative to ground, and a total of 4.7 dropped off that. So in this case, this is a 9 volt battery, so the perfect middle operating point would be 4.5 volts. And look, we're at 4.3, so that's very, very close. That's good. So there's our DC operating point. Everything looks very nice, and that's exactly what we want for this amplifier. Okay, let's go stop the simulation, and let's reconnect this. All right, and now the let's take a look. And so this frequency right here, 1 kilohertz, 2 kilohertz, 10 kilohertz, whatever, that's going to have to do with the filtering on the input and the output. Now remember, here is a filter. So it's a capacitor and then a resistor. And so this is a high pass filter, just like in the previous example with a common collector or emitter follower amplifier that we did. But how you have to figure this out is you take the voltage source and ground it, and then this 100K parallels with the 22K. That becomes the resistor for this. And then also looking at this impedance here of 200K roughly, if you want to be accurate. So you got this 200K impedance in parallel with a 22K, in parallel with 100K. That's this resistor right here. It all adds up and kind of gets clumped into here in the model of a high pass filter with a 1 microfarad, and then you figure out what the 3 dB point of that is, right? And the same thing here. So we got this capacitor here, but now this is different. We haven't seen this. Last time we took the output here, but now we're taking the output right here. So what's the resistance looking into the collector? It happens to be infinite as far as we're concerned, so it doesn't count. So what we see is this 10K, and again, we take the power supplies and we put them to ground when we're doing these impedance calculations. So we see 10K to ground, so we're seeing 10K and a 1 microfarad. Again, it's a high pass filter, and we could figure out the 3 dB point would be 1 over 2 pi RC, right? And the R would be that, and the C would be that. All right, and then we figure it out for, and again, I'm doing it for audio, so it makes sure that it starts passing it at 20 hertz or less. All right, so let's turn it on. Let's see what happens. Okay, so first thing is, what color is what here? The input, the original sine wave, is this line right here, which is going into the green trace. So here's the green trace. This is our signal. So that's our signal in. And remember, it's in millivolts. And so if we look here carefully, I've got it set for 10 millivolts per division. So each one of these divisions is 10 millivolts. All right, so if I move it around up and down, you can see there's the center line. See the white line? And if I put it down here, just hard, there we go. So you can see it's 10 millivolt peak, 10 millivolt peak. That's exactly what we would expect it to be. So that's exactly right. Okay, now what else do we have here? This line is the yellow one, and that is going to be the total DC signal with the AC signal riding on top of it. All right, so that's the yellow line. So what are we expecting? We're expecting to have the green signal, which is a 10 millivolt peak, so 20 millivolt peak to peak, wiggle or signal added on top or superimposed on top of the DC bias point, the voltage divider bias of 1.6 volts. So watch when I move this yellow signal. And we're on, let me put it to DC mode. There we go. Yeah, so the problem with this thing is the scale of it causes this oscilloscope grief when things are in a different scale. So what I wanted to show you is that this yellow signal is really riding on top of the 1.6 volts, which it is. But you see I've got AC coupling. If I put it to DC coupling, then it's confusing this, this instrument, all right? And the instrument is just not doing well. But in any event, the green signal and the yellow signal are the same. You can see they have the same amplitude, but the yellow one is actually offset by 1.6 volts. But the point is they're in phase, they're the same signal, just offset by a DC offset, which is the voltage divider bias. Okay, that's important. Now here's where things get freaky. So first let's make sure we're all on the same scale here. So the blue signal's at, the green signal, which is the input, is at 10 millivolts. The yellow signal is at 10 millivolts. So that's our input. Now here's our output here, which is the blue signal. All right, so there's the blue signal, and it's right here, and that's our output, the blue signal. Now, what I want you to take a look here is the yellow signal and the green signal. Let's take the green signal, because this is the absolute AC input. This is the very beginning AC input. If we take a look at this, it's on the 10 millivolt scale, so 10 millivolts per vertical division, right? There it is. And so it's going 10 millivolts up and 10 millivolts down. That's exactly what it should be doing. Now the blue signal, we've got it at a different scale. See, I've got it at 50 millivolts to make it look the same. But if I put it at 10 millivolts, it's much bigger. Now let me move this yellow one out of our way. All right, so, and then also look where ground is. Ground is right in the middle because it's AC coupled. The output is AC coupled. See that capacitor? So we're only getting the AC component, no DC component. So that 5 volts, we want to set that DC operating point so we get the maximum swing, but when we get the signal itself, we want just the AC component of it, right? So that's why it's sitting in the middle and ground is in the middle as it should be, which is that white line. Now, if you look, the blue signal's at 10 millivolts per vertical division. The green signal, the input, is at also 10 millivolts per vertical division. So we're comparing apples to apples. Wait a minute, the blue signal is bigger. It's bigger. So what's going on here? And it's bigger, and so it's amplified, but what else is going on? Now, maybe you don't see it yet, but let me change the scale of the blue signal so that the two waveforms are kind of looking like the same. And now look, can you see what's wrong? They're 180 degrees out of phase. So the output signal is amplified, which is good. It's amplified, but it's 180 degrees out of phase. It's been inverted. So this kind of amplifier not only amplifies voltage, but it inverts the signal, and that's really important. So if you are expecting the signal to be the exact same as the input, except bigger, it won't be. It'll be the same as the input, amplified but inverted. So it's an inverting amplifier. So it's an inverting amplifier. Now, can we eyeball what the gain is of this and then use that knowledge so that when we do the math, we have something to check against? Sure. All right, so let's just do some counting here. All right, so the green signal is the input. All right, the green signal is the input, and what I'm going to do is I'm just going to put it right there. And we already know that this is 10 millivolts per division, so it goes 2 divisions. That's easy to see, and we know that. So there's 2 divisions, right? From top to bottom is the total stride. Now let's look at the blue signal, and how many divisions is this? So we're also at 10 millivolts per division. So we're comparing apples to apples. We're at the same scale graphically, so we can count these up. All right, so I know this is hard for you to kind of see on the screen with a little mouse, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost 10. It's a little teeny tiny bit less than 10. So this has got a total stride of 2. This has got a total stride of 10. So the gain is 10 divided by 2. All right? Let's just pretend we don't know how to do arithmetic. 10 divided by 2 is 5. And it's a teeny tiny bit less than 10, so it's probably 4.9 or something. It's 5, but what kind of 5? A negative 5. So the gain is negative 5. Now, can we see that anywhere? The gain is negative 5, right? Let's take a look at the circuit here. So we've got these 2 resistors that are setting up the bias. So that probably doesn't have anything to do with the gain. But the 2 resistors that are in the output do have to do with the gain, and the gain of the transistor has to do with the gain. Now, here is the magic part. What you want ideally when you build an amplifier is I want an amplifier that is invariant of the gain of the transistor. In other words, whether it's a beta of 100 or 1,000 or 1 billion, I don't want that to come into the result of the amplifier's gain. Because I could have a different transistor, the gain could change as a function of temperature and all kinds of other things. So what I want is, I want to design something somehow that the gain gets canceled out, and all we see is a ratio of fixed components that I control. So forgetting about the gain for a second, look, there's a 10K and there's a 2K. What's 10K divided by 2K? 5. So there it is. So the gain is simply RC over RE. Doesn't have anything to do with beta, does it? Why not? Well, because the current here has to do with beta. The current here has to do with beta. So if we design the circuit and we finagle it, what happens is we get these betas canceling out, but then we still get the ratio of the RC to the RE, and then with a minus sign, and that's the gain. So the gain here, the common emitter amplifier voltage gain, is this R10 over R7 in the way that it's labeled right here. So it's the collector resistor over the emitter resistor. All right, so that's a good place to stop. So now let's go back to the drawing here, and now what we're going to do is let's calculate why that is. Now we've kind of intuitively done it, and you know what, if we go back to the simulation, let me save this and make sure it's stopped. If we go back here and we simply change one of these values. Like instead, make this like we can make this. Let's make it like 15K. All right. Now, when we do this, we could potentially blow up the operating points, right? And we have to readjust things, but the input is so small, we should be okay. So if we make it 15K, then it's 15 divided by 2, which is 7.5. So we expect about a 7.5 gain. So let's see what we get. And sure enough, look here, right? There's our input, which is still, it's just got a stride of 2, right? It's 20 millivolts total. But now the blue signal is now much bigger. And again, let's count it. I'll count it for you. So ready, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, almost 15. So there's the 15 and there's the 2. The 2 is the green one, and again, you know, the 15 divided by the 2 is the 7.5. There it is. So it actually amplified it 7.5 times. So it works. It's an amplifier, right? And so that's perfect, but it inverts the signal. So remember that. All right, so let's stop here. We're going to go back to the drawing in the next lecture, and then we'll do the math that proves this gain, which is not too hard, but I want to kind of break it up because we're going to probably need a half hour to do that. All right, so stop here, and I will see you in the next lecture. All right, welcome back, and we are on the last lecture of the transistor section before we actually get onto the bench and build stuff. So we are continuing with the common emitter amplifier that we've got here up on the screen, and what we're going to do is we're going to find what the gain is or compute what the gain is and analyze it. So let's just jump right in here since this is a continuation of the previous lecture. So basically what I'm going to do here is you've got all this information. I'm just going to erase all this and we're going to redraw this circuit. And what we're going to try and do is what we're going to derive is the gain as a function of RC and RE. But we're going to give ourselves some room here. So why don't we go ahead and let's just erase this whole thing so we've got some room. All right. And let's go ahead and draw this so we can see what we're doing here better. All right, so this is common emitter amplifier gain derivation. Okay, so that's what we're trying to figure out right here. All right, so why don't we start with our circuit, and let's get our transistor here, get our emitter, and get our collector. And after a while, you're going to start getting really good at drawing these circuits and kind of making small modifications to get them to do what you need them to do. So we're going to call this, matter of fact, let's do this. And now what I'd like to do also is we are going to put in some of the missing components here. So let's get our voltage divider bias going there. And we'll get our capacitor here. All right, we're going to call this Vin. I'm going to call this Cin. Sometimes it's called Cn or C1. You know, whatever is fine. And this is going to be to our V sub Cc, which we had set at 10 volts on the previous example and 9 volts in the simulation, but actually we don't really care what it is. We're going to just leave it as V sub Cc, so it doesn't really matter what it is, so we're just going to leave that. Let's see, what else do we have? We're going to take the output here, all right, and there's going to be another capacitor, and then this is going to be V out, okay, and I'll call this CO or C out, okay. And now let's go and put some of these resistors in here. I'm going to call this RC. I'm going to call this RE. We're going to call this R1, and we're going to call this R2. All right, and let's kind of dot these nodes here so you can see that they're connected. All right. All right, so let's again, when we do this kind of stuff, what it's all about is just writing down your modeling equations so you have everything so you can kind of see what you can figure out. All right, so let's write down some stuff. So I sub C equals beta times I sub B. I sub E equals beta plus 1 times I sub B. And then finally, I sub E also equals I sub B plus I sub C. All right. And this is a lot of tongue twister stuff here, so hopefully you're hearing me clearly, but you can see what I'm writing. All right. So those kind of model what's going on. That's the model we're using. All right. And let's see what else here. Anything else that we need to know? One thing we can write down is we can say that V sub E equals V sub B minus 0.6 or 7 volts. All right, so that's another one. So V sub E tracks V sub B by an offset. All right, and let's just draw this little thing in here, plus to minus, and this is usually like 0.6 volts. Right? Okay, and then let's label what these things are, so everyone's sure here. So this is the collector, right? And this is the emitter, and this is the base right there. All right, base collector emitter. All right, and again, this is an NPN transistor. So let's put NPN. PNP is the same. It's just voltages are backwards, currents are backwards, and everything else is the same. All right, all right, what we want to do here is what we're trying to come up with is we want something. What we want is, why don't we write what we want? All right, so what we want to come up here with is we want to come up with gain equals V out over V in, and somehow that's supposed to equal minus RC over RE. That's where we want to go. Somehow we want to figure this out. So, and we found this kind of experimentally and intuitively by looking at the simulation and by me kind of telling you this is what it's going to end up being. But this is what we're looking at. So the question is, how are we going to get there? So we have these equations here. And now what we have to do is start doing analysis and try and figure out some way to relate V out to V in to these things here. Now, this is going to be the final circuit, all right? But this V out and V in here, one thing that I'm going to kind of do is let's make sure we're clear. So this is V sub C right here. That's that output right there. And this will be, the voltage here would just be V sub E. And I'm going to try and use capital letters here, V sub E. And this voltage right here is V sub B. This V in and V out, these are these AC signals. All right, so these are the small signal AC signals coming in and finally coming out that are capacitively coupled. All right, so kind of keep that in mind as we kind of run through this. All right, so so the first thing let's figure out here. How about, let's see, let's start with, let me find a good color here that's bright. Okay, so let's figure out what VC is. All right, so I'm gonna start here. How about right here? So V sub C, and this is so this is our DC V sub C. All right, V sub C equals, and let's get a current here. So this current, and remember this this current really kind of goes through this whole thing, and it's really hard to draw without just making a complete mess of everything. So I'm going to draw it like that. That current right there is I sub C, and then down here it's I sub E. And we know that I sub C and I sub E are almost identical. They're just one part in beta, right? So we can either assign them to each other, and I sub c equals I sub e, or if we want to be exactly accurate, we can kind of keep this one part in beta. But in any event, so just keep that in mind. All right, so this current moving down here, all right, that is definitely I sub c, and this current down here is I sub e, okay? And the current going into the base is I sub b. All right, so what can we write here? So this V sub c, let's figure that out. So we know the current is I sub c, so V sub c equals the voltage here, which is V sub cc, and that's going to be minus the current times the resistance. So that's I sub c times RC, all right? So that gives us one equation right here. So let's write down our, we'll say these are, our equations that we're kind of working with. All right, now, what else do we know? Let's see here. How about, let's see here. What is another thing that we know? Let's write down this I sub e a little bit. What do we know about that? So I sub e is going to be equal to V sub e over R sub e. All right, so I sub e equals V sub e over R sub e. All right, so now we've got this voltage V sub e, we've got one of our resistors R sub e, and we've got our other resistor R sub c. So now the question is, how can we kind of relate these things to each other? All right, now, so now let's, we're gonna do a little bit of a trick. So the first thing is, what we want to relate is the input to the output. Now the input is V sub b here, and the output is this V sub c, right? What relates the input to the output? Well, this equation right here helps us in the voltage sense. So V sub e, which is this voltage right here, is just V sub b minus 0.7 volts or 0.6 volts, right? All right, so those relate those two things together. Now, this, when we use capitals, when we use capital letters, we're talking about DC, all right? When we use lowercase letters, and let me see if this makes sense to you. So if I were to write, so this is, and what I'm going to say is we're going to say this is at DC, or this is DC, gain. Now, what about at AC, or what's going to be called small signal? So what we're talking about now is what happens when we put just a little bit of a wiggle on here, right? Just a little bit of a wiggle. Well, you've got V sub e and V sub b, V sub e and V sub b. V sub b tracks V sub e, but now if you're talking about the deltas, if you're only talking about the deltas, right? So if we're talking about delta V sub e, and we're talking about delta V sub b, what's going to happen here is that if we're only looking at the difference, right, and we subtract these two things from each other, because V sub b is always going to be equal to V sub e plus this 0.7 volts, the 0.7 volts will subtract away, and then what we'll get is, if we're looking at deltas only and small changes, all right, we're going to call this little V sub e, all right, is going to be equal to little V sub b. All right, so this is the small signal version of things. So it says that V sub e equals V sub b if you're talking about small signals, right? Because we're just talking about the delta here, just the delta, all right? So we don't care about the 0.7 volts. We always know that offset is there, but the deltas will track with each other. All right, so if one goes up 1 volt, the other one will go up 1 volt plus the 0.7 volts. But that delta stays the same, the 1 volt. All right, so that's the small signal. Now, let's also talk about this I sub e here. So now this is, again, this is the DC at DC, or the DC gain. But if we're talking about just the little small signal, we're adding on top of this, we're going to change this and we're going to use lowercase letters here. So instead, I'm going to say, I sub e, and we keep the subscripts capitalized. I sub e equals V sub e over R sub e. And the resistors are still resistors, so we keep those capitalized. So I sub e equals V sub e over R sub e. All right? Okay, and then, so that we've got that equation right there. And now, let's play with this one. So now V sub c equals V sub cc, which is the power supply, minus I sub c times RC. But again, if we're only talking about the delta, then the delta, the V sub c is constant. That's gonna get subtracted out, right? So if we're just looking at the delta or the small signal change, then we could say something like this. We could say V sub c, and this again is a lowercase, equals, this goes away, and then now what we're left with is minus I sub c times R sub c. All right, so these are the small signals. So again, this one is at AC or small signal. All right, this one here is at AC small signal. All right, these are just the small signal. So let's kind of circle these things. So we got this one here. We got this one here. We got this one here. All right. Now what the question is, can we bring all three of these things together? All right. So let's see what we can do here. So this one right here, so remember, what we want to relate is the output to the input. So in this, before we get through these capacitors here, the output is V sub c and the input is V sub b. So what I'm really looking for right now is I want V sub c over V sub b. All right, but I don't want V sub c over V sub b, right? What I want is little v sub c over little v sub b. All right, that's what I really want, okay? I want this thing. All right, I want little v sub c over v sub b, because that's going to be what's going to get out these capacitors, all right? But that's exactly what we have right here. So I've got little v sub c equals minus IC times RC, and then I've also got this I sub e equals V sub e over RE. All right, so now let's take a look at this. I'm just going to write this over here. So this is little I sub e, and let's put these all in green now so we don't confuse ourselves too much using too many colors there. So I sub e equals V sub e, and that's little v sub e, over R sub e. Okay, and then let's bring this one over here, and this says that little v sub e equals V sub b. Okay, so now these three equations, if we start plugging them into each other, right, and finagling, this is kind of what we get. So let me see if I can do this without making a mistake here. All right, so I'm going to start with the top one. So I'm going to start with the top one, and the top one says little v sub c equals minus I sub c. Now, we don't have I sub c in these two equations, but remember, I sub c and I sub e are so close to each other, we can replace I sub c with I sub e, and we do have I sub e. It's VE over RE, all right? So this is minus V sub e over RE, and this whole thing is times RC, that times RC. So all I did was, just to make it clear, we have this IC right here, and IC equals IE for the most part. IC equals IE, one part in beta, right? One part in beta. So then all I did was I replaced IC with IE, which is small VE over RE, and that I got this right here. All right. Now we're almost done. We're almost done. Now why don't we do this? Let's take VE, which is this output here. Let's take VE here. All right, let's move it over here. So now what I'm going to get? I'm going to get little v sub c, and again, that's supposed to be little. That's, you know, my attempt at a small lowercase letter here, over V sub E equals minus R sub C over R sub E. We're almost there. Look, we're looking for something that looks like V sub C over V sub B because that's the output over the input. I've got V sub C over V sub E. We've almost got it. What can we do here? Aha. Look at this. V sub E, little v sub E equals little v sub B. So this equation right here can be rewritten one more time as little v sub C over little v sub B equals minus RC over RE. And V sub C over V sub B, this is just the output over the input, which is just the gain, the small signal gain. So this is small signal AC gain. That's it, right there. So there's the derivation. Now, to be absolutely accurate, if we want to be absolutely accurate, then in front of this ratio V sub C to V sub E, we would just put this beta over beta plus 1 if we wanted to. So it would be like 0.999, and then this would be accurate. But we can throw that away and assume it's close enough to 1 as beta gets large. So that's it. That is the gain. So there's the derivation of the small signal gain. So the trick is, now let's follow through this. The trick is you first set up this kind of a DC gain and set up these equations because the DC we understand. Then what we say is, all right, once we have this DC gain set up and we have these equations, right, that model the different things going on, then what's nice is anything that is going to be a delta is both the input and output would both change kind of at the same time in these equations. So any constant offset gets subtracted away. It just disappears, right? And that's why this VE equals VB minus 0.7 volts. Now it's dynamic or small signal VE equals VB because this delta here, this offset just gets subtracted away because it's going to be in both values, so it's going to subtract away, right? And then we write all these in terms of small signals, and we get rid of anything that's constant when there's going to be a delta from one point to another, right? So, and let me just kind of say that. So say if we have something that say we've got an x, right? And we say we got an x plus let's say a, all right? And then we have x plus delta x plus a, all right? So from this to this, what was the actual change, right? Well, the actual change was the x's cancel out, we can get rid of those, right? The a's cancel out, we can get rid of those. And the only thing that changed is this delta x. So that's kind of the whole point here, is when you're talking about just deltas, all these constant terms disappear. Then we came up with like 3 equations here, and then we just played algebra with them. And then when we got done, we figured out the gain was minus RC over RE. So what's cool about that is it's always the collector resistor over the emitter resistor with a negative sign in front of it, with a negative. So it's an inverting voltage amplifier. So a common emitter amplifier is an inverting voltage amplifier, and beta, right? Beta does not come into play. Now, in reality, it really does, right? There's a term here of beta over beta plus 1, right? Beta over beta plus 1 is in this equation here as a constant, a multiplying factor. But let's say beta equals 100. What's beta plus 1? 101. Get your calculator out. 100 divided by 101 equals 0.99. So it's 99% correct. So we don't need to worry about that, and that's exactly what we wanted. We want to get rid of beta. So the whole goal is when you make a transistor amplifier, or any amplifier at all, the gain is going to vary, right? Maybe it's 50, maybe it's 100, maybe it's 200. It changes under different conditions. So if you can design a circuit that takes advantage of the properties of the model, either transistor or FET or whatever, and the gain falls out of the model, right? And you're only left with the passive components setting the gain, that is what you want. Now the beauty is, as long as, so then you say, well, this can't be. I mean, then what's the point of having a gain? the gain still needs to be there, but as long as the gain is high enough where whatever amplification you're setting will still work, then it's okay. So for example, we're only set, in our simulation, we set the gain for 5 and then 7.5. Well, the gain's at least 50, right? Even if the transistor is like in really bad shape and it's really hot and all kinds of things are going wrong, it's at least 50 and it's probably up to 250. So since the gain is high enough, we don't have to worry about it. And even if the gain gets into this situation where we start saying, well, how much are we going to start to deviate if we don't multiply by this? And we could put this factor in front of here if you wanted to, right? But it's just going to be 50 over 51. Let's try that. So worst case, it's 50 over 51, right? So what? Now it's 98% correct, right? Within a 2% error. The components that we're going to be using are probably going to be 1% to 5% most of the time. So that just doesn't matter, right? Now you can get precision resistors that are 0.1% and even better actually. They're laser trim, super expensive. But 1% are pretty easy to get these days, metal film resistors, and you can get them all day long. And I suggest, me personally, when I do designs now, I just do everything with 1% resistors. Maybe 5 or 10 years ago, I would use 5%, but they're so cheap. They're just an incremental cost over 5%, so I just use 1% in everything. Now, but what gets expensive are capacitors. So if your circuits now, if you're doing filters, right, then the capacitors are typically going to be 10 or 20% accurate, and then they can vary over temperature and other things and frequency depending on the kind of capacitor. So these can be actually more expensive, right? To get those trimmed to an accuracy if you need that. But these are not coming into play here in this amplification. All right, and then the very last thing, if we go to the simulation again, let's go run that one more time. So here's the simulation, and the values are all the same: 100K, 22K, 10K, and then we got a 1 microfarad on the input and output. Now, so let's do something here. We got two things going on here. We've got this input here, which creates a high-pass filter. And if we wanted to, you could compute what's 22K in parallel with 200K, because this is going to get impedance reflected. Then in parallel with 100K, and then with this 1 microfarad, that's one of them. And then the other one is a 1 microfarad with a 10K for the resistor. Okay, so let's run the simulation real quick here. And then we see we're getting our amplification of 10. Our green is the input, and here's our output, all right? And we're getting amplification of 5, but the total stride here will be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because the stride here is 2, right? The total voltage peak to peak is 2, and then so this one will be 10. 5 times 2. Okay, so that worked out. But let's look at the frequency here. The frequency is 10 kilohertz. So as I lower that frequency closer and closer to whatever the cutoff is of this high-pass filter, this is going to start to attenuate. So if we go down to 100 hertz, let's see what happens. So we go down to 100 hertz, and let's see what our gain is. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10. So it didn't change much because the 3 dB point is very small. It's a very small number. So, and we can figure it out, and we're going to figure it out in a minute. Let's go down to 10 hertz. All right, and let's hope the oscilloscope keeps working. Go down to 10 hertz, all right, and then now this is giving us a little bit of trouble. Now at 10 hertz, what's happening? Now the input is still going 2 divisions peak to peak, and it should be 10 divisions peak to peak here if it were getting the full gain. But now look, it's 1, 2, 3, 4, 5, 6, and a little bit of change. So it's basically 3 times. So the gain is dropped. So this signal is not getting amplified the entire way. So the amplifier is working, but what's happening is the signal on the input and on the output are both getting attenuated, so we're not getting the full signal, which is exactly what we expect. So let's go ahead and let's calculate what the high-pass 3 dB point is on the input and on the output. All right, so let's go back here. So let's remember 100, 22, 2, and 1. All right, let's see if we can remember all that. So this is 2K, right? Is it 2K? It's been 2 seconds since we switched it. Yeah, that's 2K. 2K, 10K, 2K and 10K. So let's go back there. All right, 2K, and this is 10K. And this is 100K, and this is 22K. All right, and this is 1 microfarad, and this is 1 microfarad. All right, so what I'm going to do here is I'm just going to erase something here let's just erase some of this. All right, and we'll erase that. And I don't want to erase our gain formula here, and I'll just erase this little arrow. Okay, so what I want to do is I want to do the parallel combination of 2K impedance reflected to the base, which will be this resistance times beta, and we're assuming beta is about 100. So that'll be 200K in parallel with 22K, and then that'll be in parallel with 100K. All right, so let's go ahead and do this. So 22K in parallel with 200K, and remember, this one is special. This is really 2K impedance reflected, right, to the base, all right? And then that whole thing in parallel with this 100K, right, 100K. And remember, we have to do all these, and when you do this impedance calculation, all power supplies go to ground, and then that way this 100 now actually is in parallel with this. You can see that if this were not V sub CC, if it were ground, and that's how you do that when you're computing impedance. Impedance doesn't care if it's going to a power supply. It's going to either power supply plus or minus, doesn't matter. It's just still an impedance. Okay, so 22 in parallel with 200. So it's the product over the sum, right? So it's 22, and I'm not going to use the K because I know everything's in K and the result will be in K. So 22 times 200 divided by 22 plus 200, all right, is 19.8K. So you see it barely affected it, 19.8K. And now that's all in parallel with the 100K, all right? So again, this resistor right here is getting modified by these other impedances, but not too much. But that's why we made it a little bit bigger when we did the calculation to set the bias. Remember that? We made it bigger. It was supposed to be 19K, but we made it bigger. So when all this other impedance affects it, we get the 19K. Okay, 19.8 in parallel with 100. Remember to compute parallel, it's product over sum. So 19.8 times 100 divided by 19.8 plus 100. All right, and I'm going to tell you it's probably going to be 19, 16. Oh, I'm way off. What was I thinking? 16.5. So 16.5K. All right, so that's what this whole impedance here really looks like with this capacitor. All right, so what we really have over here, we'll draw it here, is we've got a capacitor, and then we've got a resistor going to ground. That resistor looks like 16.5K. This is already set at 1 microfarad, all right? And then here's our V in, and then this is getting connected here, and this is going to create our little V base. This is our wiggle, right? So now let's compute our 3 dB point, right? So F 3 dB. Anyone remember what this is? It's 1 over 2 pi RC. Super simple. So 2 times pi times R, which is 16.5 K. Now you do have to put the K because we're trying to get the right answer here. Times 1 microfarad equals, and remember to invert this, 9.6 hertz. 9.6 hertz. So we've got a curve here that looks like this, right? So this is like 1.0 gain here, or 0 dB, right? And this looks like this, and it goes straight. And this point right here, right about here, this is the 3 dB point, which it's 7.7 is the gain, right? And then this point right here is 9.6 hertz. Okay. So anything greater than that, we're going to get the full signal out. Good. Now over here, we've got a simpler situation, but let's talk about this again. So we've got our capacitor. This is another high-pass filter, right? It's just upside down. We've got a 10K, so now this is a 10K. So let's just put, we'll put comma, also a 10K. And then it also happens to be 1 microfarad, so the 1 microfarad stays the same. Now, wait a minute. What is the impedance looking into the collector? That's a reasonable question. Is it big? Is it small? Whatever. So it's actually infinite almost. It's huge. It's megohms. So we don't have to look in this direction and worry about it, right? But it's a good question. If somehow it could see the emitter, then we'd have to deal with this. If somehow it could see the base, then we'd have to deal with this. But we don't. All we have to deal with is this guy right here. All right. So again, let's plug it into our 3dB equals 1 over 2 pi RC. R just changed this time to 10K, right? So now this is 9.6 hertz, so we're going to let's put 9.6 hertz here is a 3dB of this one, and now we're going to figure out this one. So it's 1 over 2 pi RC, where R now is 10K, so that's an easy one. So 2 times pi times R, which is 10K, remember you got to put the K's in now, times 1 microfarad equals, let's invert this, 15.9 hertz. So 15.9 hertz and hertz. All right. So this one, this red one, we could say the red one is the input high pass. So this is input high pass. All right. And then we can draw another one. Why don't we draw it in yellow? And the yellow one looks like this. And then that is horrible. Let's try it like this. Maybe I can draw it better like this. This is supposed to be a straight line, folks. All right. And now this 0.707 is supposed to come out here a little bit farther, and then this would be 15.9 hertz. All right. And the yellow one, this is the output high pass filter. All right. So that's it. So that is a common emitter amplifier that gives you voltage gain, inverting voltage gain, and very, very, very useful. And so that, along with the common collector, and why is it called a common emitter? Because this is common to the input and to the output. The other one, the common collector or voltage follower or emitter follower circuit that we did in the previous couple lectures, that only gave us current gain. So now we can get current gain from one and we get voltage gain from the other. Now, of course, we can also create amplifiers that give us voltage and current gain, but we're done for now. We're done. We're not going to go into this anymore. This is just looking at all this math on here hurts my eyes. But I wanted to go through this. It was important to do these examples so you have some basis of how you compute this stuff and how you figure out the filtering and the small signal stuff and the biasing. And this is really important. And this is going to help a lot when you get a little pinch and you need a little circuit to do something. You could say, hey, maybe I can use a transistor to do this, a little amplifier, a little current source, a little emitter follower or something. You're going to have some context and some basis for this, all right? Now what we're going to do is we're going to get to the fun part. We're going to build some of these transistor circuits. And so we'll build maybe a current source and maybe the emitter follower and maybe the amplifier. I'm not sure. We'll see how it goes. But in the next lecture, that's what we're going to do. We're just going to build, and run some circuits and see what we get and see if we can kind of mimic what we've been doing all this math on for these previous lectures. All right, and then after we do that, then we're going to circle back and we are going to come back and then we're going to start talking about, we are finally to getting into digital logic now. But before we do that, we're going to show how would you make a logic gate with a transistor, which we've already done before, but real quick, we're going to do it again, and we're going to come up with some logic gates and look over that stuff so that we know what's on the inside of these things. And then we've more or less finished with all the analog stuff, and then now we're going to move into digital, and that's going to be a lot of fun. And that's so much more easier than the analog stuff. But that was the hard stuff. You got through it. So pat yourself on the back, and let's come back in the next lecture. We're going to build some stuff, and after we get done with that, we're going to do some TTL logic, transistor logic built on transistors. Talk about that. We'll build some stuff, and then a couple more things, and then we're into digital, and then that's it. So a long haul to get to this place, but it was totally worth it, I think. All right, so I'll see you in the next lecture. All right, welcome back, and we are on the next lecture of the transistor coverage, and now we're going to do actual experiments. Now, of course, we covered a lot of material, so we're not going to build all these things, and we simulated so many things we don't need to build them. But nevertheless, we're still going to build some of the circuits that we went over just to kind of see them in action and also experiment and see what kind of real-world side effects occur. So up here on the screen was the last thing that we did, which was the common emitter amplifier. So hopefully you have that all kind of memorized. So I'm just going to delete that. Let's get rid of this. And there it goes. All right. So why don't we start off with, let's see here. How about just let's start off with the transistor switch. All right, transistor switch. And this is one of the simplest things that we can do. And all it is we're going to use a NPN transistor, and we'll say NPN here, NPN. And it would work the same with a PNP, of course. And another thing also, in these experiments, typically the NPN we would use would be like the 3904, the 2N3904, or the PN 2222. These are two common kind of devices that you can use. So, all right, and with the transistor switch, typically what you do, okay, and this is a horrible transistor. Let me do that again. Typically what you do with the transistor switch, if you recall, is, here we go, this is a better emitter. All right, there's the emitter. Okay, and then here's the collector. So we are going to put the emitter directly to ground, connect it directly to ground. Therefore, when the transistor is on and saturated, the emitter will be at ground. Therefore, the base, so we'll get about a 0.6 or 0.7 volt drop here. So the base right here, VB, will sit at about 0.6 to 0.7 volts, right, approximately. Then what we're going to do is we're going to put our load up here. So we put the load up here, whatever it might be, and this is the load. And that just connects directly to the power supply, V sub CC. So in this case, it could be, it could be 3.3 volts, it could be 5 volts, it could be 6 volts, 9 volts, 12 volts, whatever. That's the power supply. Now to turn this thing on, what we need is, and since we're going to drive this in a saturated kind of way, we don't need a voltage divider. So we're just going to call this RB for R base. And this is going to connect directly up to the power supply. And we might set this, if we want to turn this base on really, really hard, we might say, 100 ohms to 1K. All right. And then if we did the math and figured out that there's 0.6 volts here, 0.7 volts here, then there's whatever the voltage is on the other side, we could figure out the current that's getting injected into the base, and we could see that we've definitely got this in a saturation. I don't want to spend a lot of time going over this. We already know what we're doing, so we're just going to go do it. So this load could be anything. So why don't we, for fun now, we kind of already did this in a previous lecture back when we were talking about semiconductor theory, but now we're going to do this knowing a lot more because we did power supplies. And because we did power supplies, we're going to actually take a look at the transients that occur when we turn this thing on. So why don't we, let's go ahead and let's hook up a motor. All right, a DC motor. We're going to hook up a DC motor as the load, and we're going to hook that thing up. Let's see here. So I'm just going to kind of draw what a motor might look like. Little kind of circle there is kind of how they're drawn, and we'll have it plus to minus like that. So that's going to be our motor that we're going to hook up to this. And when we do that, we'll run it, we'll be able to turn the motor on. A couple things that we have to consider is what is the maximum current, right, that can flow through this circuit here. So either, IC or IE, what is the maximum amount of current? So if we go look at, let's see here if we can get one. And I want to keep this page right here. So we'll open up another DigiKey page. All right, and let's type in 2N2222. All right, and now I was hoping to have. And let's see here if we can find, and instead of that, let's do a PN222. That means the plastic version. There we go, that's what we want. All right, what I want you to look at is see that the maximum collector current, let's see here, V sub C saturation, I sub B, and I sub C. So I sub C is what we're looking for, and that's 500 milliamps. So the bottom line is this transistor, you can it can flow 500 milliamps and be okay, and it can dissipate 625 milliwatts. And we've looked at that before, right? And its highest frequency is 300 megahertz. So we're not going to have to worry about that. All right, so let's go ahead and let's build the circuit. We're going to build it right now. We're going to put a motor on here. We're going to put a base resistor on here with a switch to turn this thing on. We're going to look and see what this thing does. So let's go over here and do it. Okay, so here we are on the bench, and we've got our trusty solderless breadboard, and we've got our transistor right here. So this particular transistor is a PN222A, and let's take a look at that on the zoom camera. And if I can get this to cooperate with us, there it is, PN222A. And I've confirmed that it's emitter base collector for this particular manufacturer. So it is emitter base collector using the flat spot, and so there it is, it's a half circle. So emitter base collector. So that's the only really thing we got to keep in mind, all right? What I'm going to do here is I'm going to talk our way through this, and I might speed the camera up here and there, but we'll see. All right, so the first thing we're going to do is we're going to put the transistor inside of there. So we've got emitter, base, and collector. All right, so the emitter, we want that to go to ground. So we're just going to put that straight to ground. And I've got the power supply off, yes, so the power supply is off. The power is going to come in here on red and blue, which are going to be the two rails. And then I've got them going up here. Then I've got them crossing on top and bottom. Then we got a little LED and resistor here to know when the power is on. The LED is off, so the power is off. So that's a good little thing to put on these boards. All right, and why don't we zoom in just a little bit more? Let that camera stop shaking. All right, so we've got our emitter to ground. Now what do we need? We are going to put a base resistor. Let's start off with, just so you can see what's going on here, let's start off with 1K. So that would be brown, black, red, right? Brown, black, red. All right. Now, as a matter of fact, let's start off with 10K. That would be brown, black, orange. So I want sort of a larger resistor so we get a smaller base current. So you can kind of see what the effect of that is. We're not going to drive this thing as hard initially. All right, so we got brown, black, orange. Okay, and then let's get a switch. We'll get a switch, and this is a momentary switch, and we're going to hook that up to the positive rail. All right, hook that up to the positive rail. Oops. All right, so there we go. So that's what we got going right there. So when I hit the switch, when I press the switch, we'll get current through this base resistor, this 10K. All right, good. Now the collector is where we're going to put our load. So what I'm going to do is I'm going to put our load a little bit off to the side here. So we put a little distance between things. There we go. So we can kind of work with it. So there's our load right there. And this is the collector that we're hooking the load up to. And this is going to ultimately go up to the positive rail. So what I'm going to do is I'm going to put a resistor right here for now. And matter of fact, why don't we put it right there? All right, so now we can put our load between these 2 points. All right, we can put our load between those 2 points, and then that's gonna do what we need done. All right, so okay, so now here is a motor, and this is a standard DC motor, and you've seen these before. And I flagged the motor shaft, so just put a little piece of tape on it so we can see it spin around. All right, and then the other thing I did was I built these little connectors here. So I soldered these on here, and then I put heat shrink tubing on there, which we've seen that as well. And then you notice the manufacturer put a red dot, which means that's the positive. All right, now most of the time these will run in both directions. So if you switch the polarity, the motor will just run in the opposite direction. But nonetheless, that's the direction that it's supposed to have a positive applied to. All right, and then you can see I just put some more shrink tubing here so these wires don't pull themselves apart. And then just at the end, I've just got a connector. So white is plus and black is ground, all right? So we're going to hook it up in that orientation. just like that. All right. Okay, so we got our motor, we've got our transistor, we've got our switch, and we've got our 10K. All right. Now let's go ahead and let's turn this thing on. So what I'm going to do is this motor also, these motors need a voltage and a current to operate at. And so we have to have a large enough voltage to push enough current through it. So this motor is probably a 12-volt motor, but we're going to run it at 9 volts. We're going to run it at 9 volts. So the V sub CC will be 9 volts here. And that'll get it running nice without burning anything out. All right, so the power supply is on. You notice our little red LED popped on, turned on. All right, and let's go ahead and turn the motor on. All right, and nothing happens. All right, so nothing happens. All right, so why is nothing happening? Well, this 10K is just not giving us enough current in the collector circuit. All right, we just simply do not have enough current in the collector circuit, so we're going to have to change that 10K. All right, so let's go ahead and let's do that. Let's change it to 1K. All right, so now we're changing it to 1K. Let's give it another try. And there we go. All right, so the problem is you just simply did not have enough base current, which would cause enough collector current to get this motor to turn on. All right, and that's what I wanted to show you is you really need to turn this thing on hard because this motor requires a lot of current to operate. All right, so let's go ahead and you can hear it running there. Now kind of listen to that. Now what we can do is we can measure the current here, right? We could put an ammeter in line, but I'm looking at the power supply and it's pulling about 210 milliamps right now, 210 milliamps. Let's make this resistor even smaller. So right now it's 1K. Why don't we make it 100? Let's make it 100 ohms. So here's 100 ohm. All right. So we'll put that 100 ohm in there. All right, so now we're going to get even more base current, if possible. It's we're probably saturating the transistor with the 1K, but let's go ahead and try it now. And actually, now we've got 0.3 or 290 milliamps, so we actually got a bit more. All right, so that's kind of what we want. All right, so now we really got this motor going. All right, so now we can take a look at when this motor is on. If we wanted to, we could take a look at what the base voltage is, all right, when this motor is on. So let's go ahead and do that. So what I'm going to do is I'm going to zoom the camera out a little bit. All right, and I've got parts everywhere. So it's just the way it is. There's always parts everywhere. Okay, so let's take a look here. And let's see. I'm gonna try and be an octopus here and see if I can do all this while, there we go. All right, so we got the multimeter, and what I'm going to do is I'm going to put this on ground here, and then I'm going to put the meter on the base. Okay, and you can't see me pushing the button, and we are out of focus. Let's try this. There we go. All right, so here we go. I'm going to press the button, turn it on, and I'm not getting a good connection. Okay, so let's try something else here. Try it again. All right, there we go. All right, so what we're going to do is we're going to have to put a cable to be able to. Oops, we had it on the we had the meter on ohms. It had switched as I moved it. So okay, let's give it another try. Here we go. Okay, there we go. So the base is at 0.9 volts. All right, so it's at 0.9 volts, and the voltage at the power supply is 9 volts. So we got 9 volts on the left here, and we got 0.9 here. So we roughly got 1 volt here. So we got a total of 8 volts over here. So 8 volts divided by the 100 ohm, that is the amount of current we're trying to push into the base, and then that current times the beta would give us the collector current, right? Okay, so we know how to do that. That's great. That's fine and dandy. But what I want to show you now is this. What I want to show you is we've got this motor here, and now we're turning this thing on really hard, and we're probably getting as much current as we're going to get out of this thing. all right, out of this transistor without it getting too hot. So, okay, we can turn it on, that's good. But let's take a look at what the power rails look like. All right, so now that we know about power supplies and all that, let's see how dirty the power looks. Okay, so what I'm going to do is I'm going to get one of our probes here, and I'm going to hook it up so we can see the power rails and with the oscilloscope, and we can then determine if we need to do anything about stuff. All right, so let's do that. Okay, so here we go. So now I have the oscilloscope hooked up, and I've got channel 1 showing here. And channel 1 we've got connected literally to the power rails. So there's channel 1 to power and to ground, and we're connecting it fairly close to where the load is, the motor, all right, which is our load. So we can put our motor up here so you can kind of see that. So now the question is, when I press this button, all right, and the motor goes spinning off, which is funny, all right, when we turn this on, what does the power supply do, right? So remember the whole thing about power supply design, right? We want to see how clean that is. So first thing I want to do is, let's see if we can get this motor to sit still here so I can kind of hold it here. All right, now I want you to take a look at this oscilloscope. So now take a look at the other camera there, and now watch this. So I'm going to turn it on. Wow. And now here's the continuous noise. So let's change the frequency here, the sweep frequency a little bit. So there's the motor running, and I've got the oscilloscope in AC mode, so it's not showing the DC, but it's just showing the noise, the AC noise. And you can see we're at 200 millivolts per division right here, 200 millivolts per division. And you can see that the noise is about 200 millivolts. So that's bad right there. Now, what else is going on? We got another bad thing happening. When I turn the motor on and turn the motor off, we're getting voltage spikes. So see if you can see those. So see that spike? And I'll do it again. All right, and so let's change the scale here, and I'm going to change the sweep rate. And okay, there it goes. There was one. All right, and I'm going to change it some more. There you go. All right, so that is really bad. So you can see. So now let's try and capture this. All right, so I'm going to try and capture this. So I'm going to put this on single sequence. And okay, so we almost got the whole thing. So let's put it out even more. All right. Okay, there we go. So now I'm going to put it on single sequence, and we're going to try and capture it. There we go, right there. So here's me turning on the motor, and here's the motor turning off. So you can see these massive spikes. Now, what are those caused? Those are inductive spikes, right? We've seen that before from inductors. That's exactly what they do. So the second that we turn this thing on, we get this voltage spike. And now notice it's also in the negative direction there, which is not a good thing. And at 500 millivolts per division, that's 1, 2, 3, that's 1.5 volts, and then this one's about half a volt. And if you keep playing with it, you can get it in both directions to go up to about 2 volts in both directions. Now, at a 9-volt power supply, that means we're dipping, 7 volts and we're going up to 11 volts, right? And if we had say a 5 volts or 6 volt power supply, we'd see the same thing happening. So two things. We don't want this noise here, this continuous noise when the motor's running, and we don't want these giant spikes. So let's go back to our design. So here we are at our design. Now, what can we do to mitigate this? So what are some things that we learned? So the first thing is, let's turn off the power. All right. So the first thing that we learned was we can put a diode across the motor so that we, when the inductor continues, when the field collapses and we get a voltage in the negative direction there, we can snub it, and the current will flow through the diode and shunt through the diode. All right, so let's get a 1N4001 diode. All right, so I've got one here, and then the trick is you put it in the opposite direction that current normally flows in the motor. So I'm just going to put it in right here, and you'll be able to see it in a second here. So there we go. So now normally current flows this way, right? So it goes through the motor and then this way. Here it comes from the positive rail. So we put that in the opposite direction. So when this inductor, because the motor is like an inductor, right? And as it commutates and the motor spins around, what's happening is we'll get a voltage, we'll get a large voltage on this side, and then that'll be bad because that'll put a large voltage on this collector here. So what'll happen is it'll shunt through the diode. It'll go through the diode. So that's number one. So that's going to help so that we don't damage the diode. So that's number one right there. All right. So now let's see if this helps any. So let's go ahead and turn the oscilloscope back on. So now take a look at the oscilloscope here. Let's do the motor again. We're going to turn it on. Let's turn the power on. Here we go. All right. And we're still getting the same kind of thing, but we're not looking at the voltage across the motor and the collector, so we're not interested in that right now. But we've helped that, and now when we turn this on, we're still getting that noise. I've just turned the scale down, so you're not seeing that continuous noise because it's at 500 millivolts, right? So if I turn the scale back up, you'll see it better. So here is the oscilloscope when the motor's off, just quiet, and now here is when it's on. So you can see that noise there, and it's a good 200 millivolts. So we got the noise and we got the spikes. We still haven't helped anything. All right, so let's turn off the power. So now what's the next thing that we can do? Well, the next thing that we're going to do is we are going to put capacitors. We're going to put capacitors from each of the leads of the motor, all right, the two leads, and we're going to put those to ground. Now, normally you might put them to the housing of the motor, but if you put those to the ground, that'll help a little bit. So we're going to take two 0.01 or 0.1 microfarad, and we're going to put those to ground. And again, we got really long wires here, so we're not helping ourselves too much, but if we had short wires, that would help because we got a lot of inductance. Okay, so now we've done this. Let's see how we helped ourselves out. So I'm going to turn the motor on, turn the power on, and let's turn the motor on. And you can see we've still got that 100 millivolts, and we're still getting these horrible spikes as I turn this thing on and off. All right, so what else can we do? Well, we're pulling an enormous amount of current initially from the power supply, and it just is not up to the task. Can we help this out? So let's start, let's go ahead and let's put a 220 microfarad capacitor on the V sub C line of the motor here. All right, so this is gonna be a filter, and we wanna put this in the right direction here. All right, so now ideally, I'd like to put it right from where the motor connects, but we just don't have enough lines here. So what I'm going to do is I'm just going to actually put it right here and give ourselves some room. We'll just put it right on the rails, and it would be a lot better if it was right coming from the motor, and we just want to make sure we've got the orientation right. Okay, so we're just going to put it right here. All right, as close as we can. Okay, so that's a 220 microfarad, all right? So let's go ahead and let's give it a try. Let's turn on the motor. All right, and we've definitely reduced the noise a little bit. All right, and we also really haven't helped the spikes too much, okay? Really haven't helped the spikes too much. So let's turn this down a little so we can see it, so we can see the whole spikes. Okay. So there we go, and let's turn it down a little bit more so we can see the total spikes here. And there we go, there's a good one. All right, there's a good one. And let's try and record one of those. There we go. So we're definitely getting, so again, we're on the 500 millivolt scale here, we're getting 1, 2, 3, we're getting about 1.5 in the negative and about 0.5 in the positive, and we still got our noise there. All right, can we make this capacitor bigger, right? 220 is not getting it done. All right, so let's go to a larger capacitor. Here is a 2200 microfarad. So this is 10 times as large. All right, so let's see if this gets it done. All right, so we got that 2200 in there. We got it. It's polarized, so make sure you put it in the right direction when you do these kind of experiments. Okay, let's turn the power back on. Okay, and now let's give it a try. I'm going to turn the oscilloscope back in run mode. Okay, here we go. Oh, wait a minute now, what's going on here? The motor's on, but there's like no noise there. Look at that. It's flat. All right, and now let's turn it on and off real quick. All right, And now look at these spikes we're getting, right? They're smaller. So now notice we're getting about 1 volt in the negative, and we're getting about, a quarter volt in the positive direction, and the noise is almost gone. So let's change the scale here so we can see the noise. So now look at that noise. So that's nice. So that noise is gone there. So we really killed the noise. You can see nothing is happening. We're still getting these spikes, but they're not as bad. All right. So we put it back to the 500 millivolt scale, and there's this, there's a spike. There we go. There's an off and on, and let's put this in single step mode. Ready? And let's get a. There we go. So there it is. So now we got 1 volt and we got a quarter volt. The noise is almost non-existent now, so that's really good. Again, to prove it, let's pull out the capacitor. All right, and let's do it again, and I'll show you that it is really bad. So you can see there, much higher. All right, and the noise, of course, you can see that noise there now. All right, let's put the capacitor back. Hot swapping this capacitor here. All right, here we go. And the noise is nice when it's in continuous mode, and there's a on-off, there's an on-off, there's an on-off, and it's less. So the point is that with these modifications, then we can get this to run a lot cleaner. So at the end of the day, if you're going to run motors, the transistor will work. We can use the transistor. We can get enough current through for this, small motor here. And in reality, you'd probably use a FET, right? FETs are better because they have very, very small on resistance. They're just like mechanical switches practically. But you have to concern yourself with these power supplies, and you need to put your oscilloscope on the power supply, and you need to look at what's happening when you turn this motor on and off. And then you need to put these diodes here, these flyback diodes, right, on these motors so that you don't damage the switching device, because there's going to be a large voltage generated when that motor turns on and turns off, right, and that inductor goes back and forth and does what inductors do. So you want to protect that. But nevertheless, basically with just a couple little capacitors and one large capacitor, we've kind of filtered a lot of this, and we've got this to be, pretty reasonable. All right. So anyway, that is the using the switch, but with our knowledge of power supplies, that now we could analyze the oscilloscope information and know what we're doing a little bit, and then make some changes here to get a little bit better performance. And now some things that you might try, if you want to keep cleaning this up, you can start doing inductive filtering on the power supply. You can put larger capacitors, you can put Zener diodes and clamp things. There's all kinds of things, and you can Google and internet, look for things, different techniques to kind of make that better. Or you can use a motor driver, where some person designed a driver that drives motors, and you just put the passive components it requires, and then the motor doesn't muck with the power supply so much. So anyway, perfect. All right, so let's go ahead and let's go to the next experiment. All right, so now let's do another experiment, and let's get rid of what we have here on the screen. Okay, and let's do the current source. So let's build the current source. So here's a simulation of the current source. So again, this is what Crash Course EE Transistors 02 is the name of the file. All right, and in this case, we've got a current source where we're using a voltage divider bias to set this cleanly, and we're setting the base at a certain voltage, which then causes the emitter to be at a certain voltage, and then we put a program resistor, a current programming resistor, it's kind of called, in the emitter to ground, and that sets the current. So if I run the simulation with these values, so if we have a 2K, a 1K, we've got our 2N2222 or our PN2222 with a 1K down here, then we're going to get about 1 milliamp, all right? And then no matter what we put up here in the load resistor position, so if we go here and put 100 ohms from 0.01 ohms, we'll still get that same voltage, same current, all right? So this is a constant current source, and we can go ahead and we could put 1K here, run the simulation. Again, we'll still get the voltage. Now, when this will stop working is when we make this resistor so high that we can't drop the voltage over it anymore because the source voltage isn't large enough. So if we put this at, say, 4K and we run the simulation, all right, now we're at 0.99 milliamps. So we still have a volt of headroom here, but we're getting to the point where we don't. Now, if we put 5K, now watch what happens. Now we're at 0.92 milliamps. So now at this point, we cannot drop the voltage at this current because we don't have enough voltage to drop. All right. So anyway, so in this particular circuit, if we go from 0 to 5K, we will have a constant current source that'll stay around 1 milliamp. So let's go ahead and build it with these values. So we got 2K, 1K for our voltage divider, and then we got 1K down in the emitter as the program resistor to program the current, and then we'll put our load resistor with a few different values and see what happens. Okay, so let's go build it. All right, so here we are on the bench. So first thing is let's get our trusty transistor here. Here's my PN2222, and we will put it here. All right, so there it is. Remember, it's emitter, base, collector. All right, so what do we need here? So first things first, we have to create the program resistor. Let's do that. That's pretty easy. So from the emitter to ground, and let's zoom in a little bit for you. There we go. Zoom in just a little bit. So from the emitter to ground, we want a 1K resistor. So what's 1K? That's brown, black, red. All right, here we go. Brown, black, red, right there. All right. Now, the collector is going to be where we're going to put our load. So what we're going to do there is we're just going to put a couple wires to bring that out so we can kind of work with it. So we'll put it right here. Just kind of move it away from the transistor, give ourselves some space. Let's get rid of this oscilloscope connection from the previous experiment. All right, and our load is going to connect from that point up to the positive rail, right? So let's go ahead and we'll connect a wire right there. All right, so that's where our load will go. It'll go from here to here, from these two connections here. All right, so that's good. Now we need to create our voltage divider. So our voltage divider is, let's take a look. It is 2K and 1K. So it's 2K and 1K. So 2K from V sub CC, we need a 2K. So 2K is red, black, red. So be careful, red, black, red. So let me find that. All right, so I've got our 2K here, red, black, red. All right, so now I'm going to put that up to the base. And you know, when we're doing these little experiments, it doesn't hurt to kind of you know, design things in a clean way, even though we could use less wires, but it kind of makes it easier to see what's going on. So now, so that's going to the base, and then this point right here is going to go to V sub CC, or power, right? All right, so that's our 2K. So let's get a little red wire. Red means plus or power. All right, so that's good. So I got that. Then I need the other end of the resistor. I need the other resistor here. That's going to go to ground. That's going to be our 1K, which is brown, black, red. Brown, black, red. All right. And I'm going to put this right here. And there we go. Kind of bend these little bits so they look nice. Okay, so there's our voltage divider. Now we need to take that and we need to go to ground, right? So let's get a black wire. We'll go to ground. All right. So we've got our voltage divider. That's going to set up our base bias in a nice clean way. Then we've got our program resistor, which is 1K, and that's going to, basically we're going to get about a volt over this, which will end up giving us 1 milliamp of current. Then anything we put here, we should get out a milliamp. A milliamp should flow through it until we make that resistor too big. Now, let's measure that current. So let's put a sensor here in the circuit. See if we can find one little, this one's a little better. All right, so I'm going to put a sensor right here. And which way is current flowing? Current is flowing in this direction here. So why don't we, let's open this up a little bit so I can put this sensor here. All right, there we go. All right, so I'm going to put the sensor there, and then I'm going to plug this into the amp meter, and then we'll put the load right there. So that's where the load's going to go. So let's put one right there right now. So why don't we start off with 10 ohms, all right, which is a brown, black, black, brown, black, black. So I'm just going to put it right here. So there's our 10 ohm resistor, brown, black, black. Now I'm going to hook up this amp meter, and we'll put it on milliamps because we're only pushing 1 milliamp through here. We could put it to microamps if we wanted to, but milli should be fine. Let's see here. So let's connect this up. Remember, amp meters go in series. All right. Now let's see if we can get our meter where we can see it. All right, so let's see. How about that? Does that look good? Okay. All right, so we're looking for DC milliamps here, and we've got 2 decimal places of accuracy, so that should do it. We've got our 10 ohm resistor here, and so now when we turn this whole thing on, we should get about 1 milliamp of current with 5 volts as the power supply. All right, so I've got 5 volts on the bench power supply. It's coming in right here. Notice our little LED is off. I'll put my hand there so you can see it's off. So I'm going to power it up. LED turns on, and sure enough, we have 1 milliamp. All right, so that's pretty close, pretty impressive. All right, so now we've got our load there of 10. So now let's start going up, and let's see what happens. All right, so let's just get a bunch of resistors here for fun. So let me grab some. So let's we'll go by powers of 10 basically. All right, so here's 100, and let's get a brown, black, red. There's 1K. And let's get a red, that's a 2.2K. And let's see here. Do I have a 5? Do I have a 5K someplace? 5K, 5K, 5K. Looking for 5K. And oh, there's one. So there's a 5.1K. All right, so 5.1K. Okay, so here we go. All right, so I'm just going to do this hot. So I'm just going to pull this down and just do this hot. We're not going to hurt anything by doing that. We're opening the circuit, so we're not hurting it. And we only have 1 milliamp, so nothing's going to blow up. All right, so there's our 10 ohms. So I'm pulling that out and putting in the 100. Put in the 100 ohm, and there you go. We still got the 1.05. So it's a nice current source. So it's looking like a current source. Good. Here's 1K. Let's put in 1K ohm. All right. Now take a look at that. Beautiful. Still maintaining that 1 milliamp. Let's go 2.2K. 2.2K here. And still maintaining that 1 milliamp. All right. And so it's almost magical, isn't it? I mean, it just keeps working, huh? And let me see, do I have a 3.3K? Yeah, let me see if I have a 3.3. Here's 3.3K, which is orange, red. Still just perfect. Now here's a 5.1. Now here is the point where this is impossible. It's going to violate it, right? It's going to violate the source voltage range, because at 1 milliamp and 5.1K, that's 5.1 volts of drop, and it can't do that, so less current's got to flow. And sure enough, 0.78 milliamps. All right, so if we try and put a 5K resistor in there, the current, so it stops being a constant current source, which of course makes sense because we can't supply that current across that resistor. It violates the power supply rail. And so now we only get 0.78. So not bad. And we pull it out, and sure enough, go back here and we'll put our 3.3K or 2.2. What do we got? Put something in here, put our 3.3 back. All right, and there we go. All right, so that is exactly what we want out of that. Works perfectly. So if you need a constant current source, you can program the current with the emitter resistor. So let's zoom in here a little bit. Zoom, zoom, zoom. All right, zoom, zoom, zoom. I've got a little 2-year-old little girl, and she's been watching Bolt, and he goes zoom, zoom, zoom. All right, so this program resistor right here sets our current, so we can change that how we want, and also with the voltage divider, and get whatever current. So this is a nice, simple current source, constant current source. All right, and as long as that resistance doesn't change too much to violate what the power supply is, it'll do what you need to do. All right, so cool. So that's good. Now, along with current sources, Now let's talk about a voltage source, a constant voltage source or regulator, right? And if you remember what we did to get that was we could do it with a Zener, right? Remember we could do that with a Zener diode and we get a little power supply out of a Zener diode. But with a transistor, if you remember, we could use a Zener to set the base voltage, right? And then that would give us, and then we use an emitter follower configuration, and then we can get a constant voltage source and kind of a voltage regulator. So let's build that next, all right? So let's go ahead and let's do that, all right? Okay, so we're going to do the regulator. So let's take a quick look at what that looks like again, just so to refresh your memory. So we're going to do the kind of Zener regulator. So what do we have? We've got the transistor here, and then we've got our emitter, all right? And then this is just where we take the voltage off. This is V out. Then up here we have R limit. So this is a limiting resistor. We can set that to 0. So this just limits so that we can control how much current. And up here is V sub CC, and this is going to be whatever the power supply is. So let's just say it's 9 volts in this case. We're going to regulate that 9-volt supply. Now what do we do here? How this works is we have this kind of situation here. We put a Zener here, if you remember, and that goes to ground. And then we have a resistor here, and this goes up to the power supply, remember that, and we can call this RZ to set the Zener. This is what supplies the base current and also allows the Zener to regulate. And then this point right here, this is going to be V sub B. All right, and then remember, we're going to have a voltage drop over here, so this makes this a little tough to get the right Zener. So say we wanted to make a 5-volt supply. Well, if this is a 0.1 volt Zener, which is kind of common, and we drop 0.6 volts here, then we're going to get like 5.3 volts, 4.3, 4.4, 4.3, 4.4 volts, right? So the problem is what we really need is like a 5.7, 5.8 volt Zener. So we'll try both of these, but what's going to happen is we're going to end up creating a regulator that doesn't give us a 5 volts, but it gives us less than 5 volts or more than 5 volts because I simply don't have the Zeners on hand that would give us the exact voltage that we need. So I've got 5.1s and I've got 6.8 volt Zeners. All right, and so we'll set this Zener resistor, we'll set this at about, we want to get enough Zener current in here to regulate this. So we'll set it at about 1K, and we shouldn't need it to be any smaller than like 330 ohms. That should do it so that we get enough base current, I sub B, and then we get enough Zener current, I sub Z, to maintain this Zener voltage here so that it can drop down here on the emitter, and then we can take advantage of it. Okay, so let's go ahead and let's build this. All right, so we've got our transistor. Again, we're just using the 2222, right? And so we got emitter, base, collector still, all right? And so what do we need? So we need a resistor, and we're going to start off with a 1K, which is going to go into the base, and that's going to be for our source of current for the base and for the Zener regulation itself. So we need brown, black, red. And again, I'm just going to kind of do it like that so we can see it, all right? And then and then I'll take it to positive. We could have just went directly to positive, right? But we make these things clean so we can see them and so you can kind of see what I'm doing. Otherwise, it's just too hard to see what's going on. All right. And then now we need a Zener, and the Zener is going to be facing with the cathode to the base, and then the anode will go to ground. Again, I'm going to do more than is necessary here. So this is a 5.1 Zener, 5.1 volt Zener, and then the other end of this goes to ground. All right, and that's going to set up, and that's going to force our voltage at the base. Okay, so that's Zener biasing. All right, so then we got that, and then now we need our collector is going to go directly to power, right? So we could have a current limiting resistor there if we wanted to, but we're going to hook this directly to power. So let's get a small, we'll just use this one. So we're going to hook the collector, so remember it's emitter, base, collector. So here it is here, and we'll hook this right up. Good. All right, so that all looks good. So that's kind of what we got going on there. All right, so we just got a circuit here, and then that's the Zener regulation at that common node in the middle. That's going to the base, so we've got 5.1 Zener. And then we've got both of these going to the plus rail. So now the emitter is going to be where we're going to take this output. The emitter is where we're going to take this output. All right, and let's get a semi-long wire. I'm going to put this over here. All right, so we're taking this emitter. I'm going to bring it all the way over here, just like that. So there's our output right there, okay? And that's going to be, of course, relative to ground, right? Okay, so then the question is, we want to see how this maintains stability as we put different loads on it and pull different amounts of current. Okay, so we really want to measure both the voltage and the current. So we can compute one with the calculator and we'll measure the other one. So why don't we measure a voltage? So I'm going to put the meter here on volt mode, and it's screaming at me because the cable's in the wrong place, which is good but still annoying. All right, and then what we're going to do is we're going to hook the meter up right here, the probe up there, and then we'll put the other line to ground. All right, we'll put that to ground. So that's going to measure the voltage, and then we'll just use the calculator. So V equals I times R, so I equals V over R. So whatever resistance we put as the load here, we'll just use the calculator to compute what the current is, right? But what we're interested in is how the voltage stays stable, all right? Okay, so what we're going to do is we're going to start off with a huge load, a huge value for a load, which means a very small current, so 100K. So 100K ohms is no current. No current is going to flow through that at all. We're going to get very little, and so that'll be our starting point. And then we want to see what this voltage is here, all right, and see how this Zener regulation regulates. Now remember, we are using a 5.1 volt Zener diode here, 5.1. So that means when this transistor turns on, it's going to be 5.1 minus 0.6. It's going to be like 4.5 volts. All right, so what I'm going to do first is I'm going to set my power supply up to 9 volts. So kind of simulating a wall wart or something. So the rails will be at 9 volt. There we go. Rails are at 9 volt. So the rail's at 9 volt and it's not on yet. You don't see the red light, right? So that's good. And when I turn this on, then everything is going to fire up, and then we're going to get that Zener regulator starting to set that voltage of the base. And then what we should see out of here is about 4.5 volts. So what I'm going to do is I'm going to bring the meter here again so we can see it. And I'll zoom out just a little bit for you. Excuse the camera wobbling. It's up on a kind of structure here, and it's not as rigid as I would like it to be. There we go. Okay, so here we go, and right now the load is 100K ohm. So if the voltage at the regulated node here, the emitter, this is going to be an emitter follower, right? It's at 4.5 volts. You know, 4.5 divided by 100K is nothing, right? So let's do it. So 4.5 divided by 100K ohm is what, 46 microamps, excuse me, 45 microamps, right? 45 microamps. So it's nothing, okay? So here we go. Let's turn it on. And we turned it on and nothing happened. Okay, so we turned it on and nothing's happening, right? We're not getting our emitter voltage where we want it, all right? So what could be the problem? Well, the problem is we don't have enough current to get this Zener to regulate, all right? The Zener is not regulating, all right? So what we need to do is we need to increase this current, all right? So let's turn this off, and we're gonna decrease this resistor right here. And let's put about, let's go to, we'll go to 220 ohms. All right, so we're all ready to go here. Let's turn this thing on. All right, we got our red light, and now we've got our 6 volts over here at the emitter, which is our output. We've got our 100K. So again, we've got very little current. So in this one right here, we're using the 6.8 volt Zener in this case. right? So the 6.8, so that's why we're getting the 6 volts out there. So we're getting what, 60 microamps, right? So 6 volts divided by 100 k ohms is, of course, 60 microamps, right? Okay, so that's good. So we've got regulation here. So we got at 100K, we've got 6 volts, and that's the voltage that we were shooting for in this case, right? So we got 6 volts. Let's go ahead and just change this. Nothing's going to happen bad if I just pull this out in real time. The voltage will stay the same. It'll go up a little bit higher because there's no load. All right, so there's 100K. So let's just drop it straight down to 10K. So that's brown, black, orange. All right, brown, black, orange. There we go. So that's 6 volts almost. Same thing. All right, but now how much current are we pulling here? So, you know, let's just call it 6 volts divided by 10K. Now we're pulling 600 microamps, right, or 0.6, right, milliamps. Okay, so let's keep going. So that was 10K. Let's go to 1K, which is brown, black, red, of course, brown, black, red. Let's find a good one. Brown, black, red. Here we go. And let's put that one in here. So here's 1K. All right. Now take a look at, we've only lost 0.07 volts. All right. And of course, now we've got about 6 milliamps is flowing, right? 6 milliamps is flowing. So that's doing good. So we went from micro to 6 milliamps, and we've lost only 0.07 volts here. So this is regulating real nice. All right, so that was the 1K. So now let's go a little bit slower. Let's go 220 ohms. So here's 220. All right, and now we drop down to about 5.9 volts. So we got 5.9 divided by 220, and so now we're looking at, we got 26 milliamps. So we've got a, so right now, you know, up to about 26 milliamps, we've only dropped 0.1 volt basically. So we've got pretty good compliance here. Let's go to a 100 ohm resistor, 100 ohm. Let's pull a little bit of current out of this thing. So let's find 100, which is a brown, black, brown. All right, there you are. Of course, as I'm doing this, it's always hard to see these tiny little things all over the place. There we go. Now look at that. So 5.88, very little change. And again, we could take 5.88 divided by 100, and of course, that's going to be 58 or 60 milliamps roughly, right? 58 milliamps. Okay, so we're doing good. So we're pulling a lot of current. So this is a pretty good little voltage regulator, huh? And you know, things are going to start getting hot. So this is 60 milliamps right now. It's, I can feel it's a little teeny tiny warm. All right, let's go ahead and let's put a 33 ohm. 33 ohm. All right, 33 ohm. Here we go. All right. And at 33, we've dropped to 5.86. So 5.86, so 5.86 divided by 33 equals, so now we're pulling 177 milliamps out of this thing. And I can guarantee this is hot. So if I touch this, ooh, that definitely burns. All right, now let's figure out what the power is, right? So the power would be I square R. So if I square that, and then I multiply that times R, which is 33. So there it is. So I square R, it's pulling 1 watt. And this is a 1/4 watt resistor. So it's going to get real hot real quick, and it's going to probably start smoldering in a second here. But we're pulling 177 milliamps. So, and look at our voltage here, you know. So, you know, we're doing good. So let's turn that. I'm actually not going to pick that out with my fingers. I'm going to turn the power supply off for a second. All right. And then I'm going to get some handy dandy compressed air. Cool it off. Now touch, touch, touch. Okay, and take it out. All right, let's turn the power supply back on. All right, and then there we go. So there we go. So that was a 6 volt Zener regulator with a transistor and voltage follower or emitter follower configuration, and that's a great little circuit right there. If you're in a pinch and you've got a transistor and a Zener diode and you don't want to put a regulator, you can do that, or you can just use a Zener diode, right? So either way, that is a little regulator, all right, voltage regulator. So now we've done a constant current source, and now we've done a constant voltage source, all right. So let's go ahead and let's think what we'll do next, all right. So let's go back to the blackboard and figure out what we're going to do next. Welcome back, everybody, and let's see here. We are on the next lecture, which is kind of just a continuation of the transistor coverage. We're trying to break this up because these experiments are pretty big, and I don't want to do them all and rush in one lecture. So let's get right back into it. We're going to talk about the common emitter amplifier. We did the analysis, of course, back in a few lectures ago. So the common emitter amplifier actually gives us voltage gain, which is something that we like. And looking here on the screen here, let's see what color we got here. Looking here on the screen, we see that the gain of the amplifier is minus RC over RE, where RC, of course, is this collector resistor and RE is this emitter resistor. All right, it's called common emitter simply because the emitter here is common to both the input and the output. Let's see what else here. In this configuration, we've got the R1 and R2 is creating the voltage divider bias. So that sets the DC operating point of everything, sets the base voltage, which then of course sets the emitter voltage right here. And then that sets the current, the quiescent or DC operating state current down RE. And that kind of sets the whole system up. Forget about the capacitors for right now, right? Once this thing is set up, then what we want is we want this point right here, which is kind of the output, which is the output. This is going to be V out, and then through the capacitor, we'll call it V out AC. But we want this to be in the middle of the range of the voltage swing. So if we set V sub CC here at, say, 9 volts, set it at 9 volts, then what we would like is this to hang around 4.5 volts when this is at DC steady state. And then that way, whatever input we apply to the input over here, when it gets amplified on the output, it's got as much room to swing as possible. All right, so it's kind of hard to hit this exactly in the middle and make everything else work, but that's what you're trying to shoot for. So whatever the voltage is of V sub CC, you're going to try and make sure that that DC operating point is in the middle. All right. Let's see what else we have here. And then the whole idea is, here would be the input, and this would be some small signal. Maybe this is, 1 to 100 millivolts is the input. Maybe we're getting this from a sensor, or, it's coming in from an RF receiver or a microphone or anything. And so typically millivolts is a reasonable small signal. You can get down to microvolts also and less, but typically we're talking about millivolts as a small signal. All right, and then so that would be amplified. It's a capacitor coupled on the input here. And then this input capacitor, we're going to set it at about 10 microfarad. And the reason why is we want this to pass basically audio. We kind of designed it originally for audio. That's this 100K, 22K, and then we found what this value would be. And then by making this larger, this just sets the 3dB point a little bit back. So basically from DC up, this thing is going to pass the signal. So from DC up, this is going to pass the signal, and then same thing here on the output. We got a 10 microfarad, and then that's going to see this 10K going to ground. Remember, when you do analysis for impedance, you just ground your power sources. So 10K to ground, and then looking in here, when you look into the collector of a transistor, the input impedance here is in the megohm, so it's pretty much infinite as far as we're concerned. So this is a high pass filter with a 10K and then whatever this capacitance is here. And again, we're going to set this to about 10 microfarad, and that means we'll get basically DC or a few hertz up, it'll pass. All right, so those would be high pass filters. All right, let's see. And then, let's take a look here. So if this is our input and this is the blue signal, and we look at these two values here. So we've got 10K and 2K, right? So what should our gain be? Our gain would be negative 10K over 2K, which is going to equal negative 5. So we're actually going to get, a negative 5. So the signal would be 5 times larger, but it would be inverted, right? So 5 times larger, and the frequency would be the same. So I want to maintain these widths here if I can. So let me see if I can do this. I don't know, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay, so that's not bad. So that's what the output would look like. That's what we're expecting. All right. So that's it. So let's go back to the simulation. And this, if you haven't seen this one, this is the common emitter amplifier, and I pulled it from some of the other simulations that we had that had it all the different circuits together and created a separate one. And this one's called Crash Course EE Transistors Electret amp _01. So this is kind of giving away a surprise Electret amp here. So if you know what an Electret microphone is, then you probably can tell what's going on here. What we're going to do at some point is we're going to put a microphone to this, and we're going to amplify an audio signal. But before we do that, we're just going to inject a signal from the signal generator and make sure the amplifier is working correctly. All right, and so you can see here I've copied down what is here. All right, and the values are all the same. So you get the 100K 22, you've got our emitter resistor of 2K, we got a 10K up here, and we've got a 10 microfarad and 10 microfarad, and that is about it. So let's run the simulation. And again, this is Proteus, and you can download this off internet for free for the eval version, which means you can't save things and it doesn't have all the features, but it has enough to do this. So the green signal, if you look at the scale here, it's at 10 millivolts per vertical division. The blue signal is also at 10 millivolts per vertical division. The blue is the output, the green is the input. And so you can see if you just eyeball these, they're about 5 times bigger. And if you count them, this is going two divisions, 1, 2. And then if I count this, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so the gain is 5, and it's inverted. So let's take a look at that. If I move this up here, and then I move the screen one down here so you can see, notice that they are 180 degrees out of phase. All right, so everything is as it should be, and it's working correctly. All right, so now another thing let's take a look at. Let's take a look at that DC operating point, right? That DC operating point. So right now, these are DC meters. And so they're looking at the DC value. So the AC that's changing really fast, they're not really paying attention to. So we can see that the DC operating point is 4.7 across this, and then 4.29 down here. So we're right in the middle of that 9 volts. So there's 9 volts up here is the DC supply. So that's good. If we wanted to, we could get it perfectly at 4.5 volts. But what's going to happen is because of the value deviations and the resistors and the transistor and all these different things, we're going to have to play with this anyway on the bench and kind of tune it to get the values that we want and kind of then put those back in the simulation. The simulation is too clean, basically. All right, so let's stop this. Okay, so let's go ahead. Let's go ahead and build this circuit over here on the bench and then run it with this exact same kind of thing, and we'll use a signal generator to inject signal into it and make sure that we've got a voltage amplifier. Okay, so let's go ahead and do that. Okay, so we're here on the bench and we've got our trusty transistor in the board here, and you can see my mess of parts, which I keep trying to keep organized, but it's very hard. And one thing that happens, this will happen to you, is see this cable right here? This is an oscilloscope cable, and what happens is the cable kind of falls, and then it rolls across the desktop and then drags everything with it. It is a constant problem, and you'll know what I mean when you try and do this. Okay, so I just wanted to show you how I do have all these parts here so I can kind of see what's going on. So, engineering is messy. So let's zoom in so we can see what we're doing here. Get a little bit closer for you, I think, so you can see it. All right. All right, and what we're looking to do is copy the circuit. So I've got my PN2222 in there, and it's emitter, base, collector, right in a row, emitter, base, collector. Doesn't necessarily have to be that way. It might be collector, base, emitter, depending on the manufacturer, but it's an NPN, and that's what it is. I've checked it. It works, and we've been using it. All right, so let's just go ahead and build this circuit based on the schematic back on the screen there. So let's get with it. So let's start off with let's go ahead and get our base set up. So let's get our base voltage divider, which is a 100K and a 22K. So let's work on that first. And when I'm doing this, I like to kind of design things more as if they were a schematic. Now maybe if I were to design this on a PCB, I'd put the resistors nice in a row and all that, but here I kind of want to design it so it looks like the circuit in the schematic capture. All right, and then now we're going to take these and we're going to go to a ground and our plus V sub CC. So this one's going to go to ground. And these two rails will be hot once we power this up. Red will be plus 9 volts and blue will be ground. And the power supply is off right now. I'm looking at it and it's off. And we can tell that because our little red light's off. So I always hook up a little red LED on power there. It'll save you blowing out some parts once in a while. You can see it power on or not. Okay, so that's good. Now let's get our emitter resistor. And we're looking for 2.2K. Here we go. We're looking for 2K actually. But you know what I found? I found that 2.2K in the actual desktop build of it works just a little bit better. We'll get a little less gain theoretically, but it works a little better as far as setting the static voltage, the DC operating point. So we're going to use a 2.2K. I've got 2K here also, but this just works a little bit better. And I'll show you. All right, so that's our emitter. And be careful, there's these 3 leads here, base emitter collector, and many times you're going to accidentally put a wire in the wrong one. I've done it, many times. All right, and so now we've got the collector resistor here, and we need a 10K for that. All right, because we're looking for a gain of 5 roughly, right? So we're going to get a 10K, which is brown, black, orange, and that one is going to go to the positive rail. All right, so that's our collector resistor right there. So far, so good. So far, so good. All right, now what we're going to do is we're going to take the input. We need a capacitor. We're going to bring that input into the base. That's where that input goes. And then the output comes from the collector out. All right, so let's get a wire first. Get a wire here. Give ourselves some room here. So here is our collector out. So there's our output right there. All right. And then here's going to be our input, which is going to be on the base here. And I'm going to just put it right there, nice. Okay, so take a look at that. So that's what we got now. Okay, looks good, looks good. All right, let's get some capacitors. We need 10 microfarad. We could use ceramic, we could use tantalum, we could use electrolytic. We don't really care too much about the quality or variance of them right now. We're just looking for bulk capacitance. So we're just going to use some electrolytic capacitors. I'll grab a couple here, and let's see if you can see this. Yeah, that one's 10 microfarad, right? So that's good. So we'll put this on the input, and be careful. It's going to be plus towards the input signal and minus away from the input signal. So there we go right there. And then on the output, we got another one here. And let's see. Yep, that's 10 microfarad right there. And 10 microfarad and 50 volts, right? So that's good. Again, there's the plus and minus is the other side, so we want to connect it like this. All right, so that looks good. Good, good. Okay, so I think that is about it. Let me look here. Yep, that's it. It's pretty simple. Okay, now let's go to our signal generator, and what I'm going to do is I'm just making sure this thing's off, and I'm going to set it to amplitude of 100 millivolts. We'll just start there, 100 millivolts. All right, and you've seen that many times, so I'm not even going to show it to you. You know what it does. The signal generator just generates a signal. Oh, and we need some posts here, so let's get some posts. So here's where our input is going to be. So there's our input, and here's our output. All right, and then we're going to need a ground here and another ground here, and good. And and be careful. You see me I'm using my finger to kind of pick these things up. Just just the stickiness of your finger kind of picks these posts up, and then I put them in there. I have impaled myself before slipping and pushing one of these posts right through my finger, so just be careful. You're going to hurt yourself a lot. I mean, my hands are in pretty good shape actually for doing this stuff, but a lot of guys, electrical engineers and stuff, their hands are just beat up. So just be careful and take your time. You'll hurt yourself. All right, so that looks good. So let's get our signal here. So there's ground and there's the positive. Okay. All right, and good. That should basically be all we need there. Now let's get a scope meter on here, and I'm going to try and put these around so they don't occlude anything and pull out as well. All right, so here is going to be channel 1. Remember, I've got these marked. I've got these oscilloscope meter probes marked. So it's on 1 times channel 1. I'm going to put that right there so we can see the input signal. Okay, good. All right, and then let's get the other channel, channel 2. And remember, your scope might have 4 channels. It might have 8 channels. I don't know if I've ever seen an 8-channel scope. I've seen 4-channel scopes. I've got a couple over here. But 8-channel, I don't know if I have seen, at least a desktop scope. All right, and we're going to put the ground here like that, get a good ground. And then we'll put the other probe here on the output. Okay. Now notice the output is unloaded. So we could just put a little load here to kind of simulate a little bit of reality so that we're driving something other than pure air, right? So why don't we, let's put 100K, 100K. So 100K puts a little bit on it, so we're not, looking at absolutely no load, okay? That's all. All right, good. Okay, so let me go power this up and turn everything on. We've got the power on. There it is. We got the power on, so everything is working. Nothing is exploding. I've got the signal generator at 100 millivolts peak to peak sine wave, and we're at 1 kilohertz. So we're definitely above DC, and the high pass filter on the input and output are well past their 3 dB point. So that means we're not getting any attenuation. All right. Now let's go take a look at the oscilloscope. So remember, the yellow trace is the input and the blue trace is the output. And if you look, I've got the divisions, a voltage per division at both at 50 millivolts, so we're at the same scale, and obviously the blue is bigger. And how much bigger is it? If you take a look here, we've got about 100 millivolts. This is reading a little bit high, even though the signal generator is saying 100 millivolts. Anyway, it's reading 100, 110, whatever, and the output is reading 418 here. So we're getting about 4 times gain, all right? And if we look at our resistors, we've got a 10K and a 2.2K, so 10 divided by 2.2 is 4.5. And we're getting, roughly, depending how this changes, a little bit over 4, so that's what we expect, right? Now, let's try something here. Let's go ahead and let's put a 2K down in that emitter resistor. Let's put a 2K, so that's red, black, red. So I'm going to put red, black, red down here instead of red, 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 which is 2.2K. Put this down here. All right. And all right, so now what's happening now is we're getting a little bit more gain as we expect. So now the gain is about what it should be. All right, it's almost 5. But what's happened is we've lost some of our dynamic range. And let me show you what I mean. So I'm going to turn off the output right now. All right, and let's go back to the circuit here. And what I want to show you is the DC operating point. All right, so let's look at some DC stuff here. All right, so what I'm going to do is let me zoom out. Hopefully you can see this. Okay, so there we go. We're on DC. All right, let's try not to break anything here. All right, so first let's look at the base voltage. All right, so let's look at the base voltage, just see where that is. All right, so the base voltage is at 1.58, almost 1.6, so it's almost perfect. So that means the emitter would be at about at a volt, and that's getting that 1 milliamp of emitter current that we use to kind of program things. But let's look at the collector, what the collector is sitting at. And it's sitting at 4.02. Now we got 9 volts, so what we really want there is 4.5 volts, 4.5, right? That puts us in the middle of the range. So if I go ahead and switch this back to this 2.2, watch what happens. I'll go switch this emitter resistor back to 2.2K, and look, we'll get a little bit better. So if we look at the base voltage, so look at the base voltage, that's almost identical, so that's okay. And now let's look at the collector and see it's 4.5. So that's exactly what we want. So, it's, do you want a little bit more gain, or do you want to have more of a symmetrical swing and be in the middle of it, all right? So at this point, we'll just tolerate a little less gain because I like it to kind of be more in the middle. All right, that's a little bit more symmetrical to me. All right, so let's bring this back down here. Okay, so let's turn the signal generator back on. All right, take a look at the oscilloscope. So again, we've got the same measurement here on the vertical axis. So whatever you see is the gain that's going on here. And we're getting it about, a little bit over 4 times. And we've got the resistors programmed to 5 times, so that's exactly what we want. Now, we know that we have high-pass filters on the input and on the output, right? So let's go ahead and let's increase the frequency here. So I'll increase the frequency. And as a matter of fact, I'm going to drop the scale down just a little bit. And maybe we can see these a little bit better. I'll go here and move this one here. So there's the input and there's the output. All right. Okay, so I'm just going to start changing the frequency. 3 kilohertz, 7 kilohertz, 10 kilohertz. And keep your eye on the peak to peak here, right? The input shouldn't change. Well, the input can change because there's a filter there too, right? So keep going of 60, 70, there's 100 kilohertz. So we've gone way past audio, and at 100 kilohertz, we're starting to see the signal dying out. And so we're still getting the input, but now we're getting some attenuation on the output. Look at that, 344 millivolts. So we're getting some fall off of this high pass filter. So this can be a number of different things that are happening. And if we keep going, there's 150. And now look at the input is starting, or excuse me, the output keeps dying down. The input is okay. So the signal's getting through the input. Now I'm at 200, 300 kilohertz, and I have lost a lot of the output here, right? And this is getting filtered. So let's go ahead and we'll just switch out this capacitor. So it's a 10 microfarad right here. All right, so I'm just going to switch that out. Now we got no signal, right? And I'm going to put in, we're just going to experiment here. We're going to put in a 220. We're going to put in a 220, if I can find where I just put it. Where did the 220 go? There it is. All right, so we got a 220. We're going to put this in, and let's see. All right, so that didn't help us. Making it bigger is not really helping us, okay? So let's see. Can we make it smaller? Let's make it 1 microfarad. What's that going to do? 1 microfarad. All right, that actually made it a little bit bigger. So what's happening here is this capacitor is getting this capacitor because of the frequencies being affected at this high frequency, and we're starting to get another filter kind of going. See, this output right here, this other resistor right here is also having an effect. So if I pop the resistor out, all right, since it's 100K, it's not having too much of an effect. All right, so now let's try this. Let's go to a 0.1 microfarad capacitor, and let's see if we can get some of this, more of the signal back. All right, more of the signal. And this is why electronics is fun. You can do the theory, you can play with it and all that, but sometimes you just start changing parts, and based on your intuition, you kind of say, what's going to happen here. All right, and that's getting a little bit lower. So it looks like if we go ahead and we put that 1 microfarad back, we're getting better high frequency response here. We're getting 188 millivolts out, which is still not the gain that we want, right? We've definitely lost. We're almost unity gain here, right? We're at like 1.5, 1.6 gain. But as we go down, 200, 100, now we're 100 hertz, 90. We're at 20 kilohertz now. At 20 kilohertz, we got that 420 millivolts. At 10, we got 420 millivolts. So, and I'll drop it down some more here. 420. Now let's go back to that 10 microfarad. Let's go back to our 10 microfarad. And all right, and we're still getting about 420. So the 1 microfarad monolithic capacitor does a little bit better at the high end. This electrolytic just starts falling apart. Okay, and so we can put that back in there. All right. So we get the gain we expect here, and we get a little bit better gain at the high end there. Okay, so let me slow that back down to 1 kilohertz. There we go. All right, so that's it. So that's working. So we got a working common emitter amplifier. It's amplifying theoretically about 5 times, but in reality we're getting a little bit over 4 here, and we could change these resistors and get more gain out of it if we wanted to. But that's good enough for now. So now what I'd like to do is I would like to connect up a microphone and amplify the microphone signal. All right, so what I want to bring your attention to is an Electret microphone. So let's go back to the computer, and we're going to take a look at microphones, and then we're going to add the microphone back to the circuit. So you can see in the circuit, I've got this component here, which is a mic, and the mic has a plus, and it's got a minus, and it's got a resistor here, and then connected to power. So, you know, what is going on here? What's this microphone, right? And so let's take a look here. And what it is, it's called an Electret microphone, and these are very, very old. And yeah, in fact, there it is, since the 20s, right? And basically how this works in a nutshell is, look over here in this picture, there's a small capacitor, and the sound pressure changes the distance between the plates. As it does that, the capacitance changes, right? Based on that, you can generate a voltage. But what Electret microphones have is they actually have charge on these plates already. So they come with charge on them, and the resistance is so high this charge never dissipates. So they have charge on these plates. So again, if you vibrate the plates with sound pressure, you can generate a voltage. Then actually inside the microphone, and here's what the microphone looks like, and I'm sure you've seen these many times, there's a FET, or what's called a JFET, a junction field effect transistor, that amplifies this signal. And this FET has huge input impedance, like many megohms, right? And so there's no current flow. We're talking about electrons are flowing, like just a few of them, and it amplifies this signal. So from the outside, what it looks like is just two leads. And what you have to do is hook power up here, and then ground it here, and then use a capacitor to capacitively couple the signal. And then now you can take that signal, and you're going to get a small signal. It's actually going to be in millivolt range. It's actually pretty big. And then, but it's got no drive, right? No current drive, no power. And then you can take that into your amplifier and amplify it, and you know, listen to it. All right. And so if we go back to our circuit here, where is it? So this is exactly what we have, and we've got a 9-volt supply up here, we've got 3.3 K here, so this is what's powering that JFET. And then if we also look, and we start looking at common microphones, one that you will find is there's a company, CUI, C-U-I Inc., and they make all kinds of microphones and so forth. And this works from 20 hertz to 20 kilohertz. And you can look up the data sheet for this particular part, and the part number is 102-1721-ND on DigiKey, right? It's right here. But anyway, they're all very similar. And here's the data sheet for it, which is interesting. Let me make this a little bit bigger for you. So if we scroll through this data sheet, we can see everything about this, and it's fairly simple. And it starts talking about omnidirectional, which means all directions it picks up, more or less. And then it's saying what its sensitivity is. So at one kilohertz and 1 Pascal of pressure, 0 dB equals 1 volt per 1 Pascal. And then, you just start reading all these different values here. Operating voltage is 3 to 10 volts. So we're running it at 9 volts, so that should be okay. And then you just, read this, what's the frequency cutoff, 20 to 20 kilohertz, and so on and so forth. And you can, figure all these things out and understand what is going on. Then it shows the mechanical design. And one thing you can tell when you look at the back of these, and we're going to go look at it and hook it up in just a moment here. One thing that you can tell on the back is the ground. So one of these contacts will be connected to the housing, and so you can see it here, the shield case, all right? And so that's the ground terminal, and you can see it right here. And that's kind of how you can figure it out if they're unlabeled, which a lot of times there are. And so that's what it looks like. You got a capacitor, you've got this JFET impedance converter, it's called, and then you set up a resistor to power the thing to your power supply, and then you have a capacitor, and they're just using a 1 microfarad. You could use 1, 0.1, 10, whatever, depending on this RL and so forth, so that you get the right filtering, right? It creates a high pass, low pass filter, and then you take that signal and do whatever you want. So in this case, they're saying, hey, hook it up to 3.3 volt power supply with an RL of 2.2, and things will do what they're supposed to do. All right, and then it's showing the frequency response. Look at this. So 0 dB, remember, this thing isn't, doing any kind of amplification per se. So it's just saying that the frequency response is going to be unity gain here, 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 and then up here, it gains it up just a little bit and then starts falling off, right? So the whole idea of this is designed to just have a flat frequency response. You don't want different frequencies causing more or less gain, right? Because that would emphasize different spectral components of your voice or the sound, right? Right, and you read the rest of this if you like, whatever. But anyway, there's lots of these components. Okay, so all we're going to do is we're going to add this circuit right here. We're going to power it up from the power supply. Let me back this up so you can see it. We're going to power it up from the power supply through 3.3K, so we don't want to run too much current through here. We don't need to. And then it just goes right to our capacitor. So literally, that's all we need to do, okay? All right, so let's go to the bench and let's actually take a look at an Electret microphone. Okay, so here is an Electret microphone. Get it to zoom in and cooperate with us. And I've got many of these, and so you can see the back there. And you can see something that kind of looks like it's a transistor, and it's actually not in this case, but the transistor's in there, right? And then you can take this apart. So this has just got some wires on it, and and a connector, so it can be plugged into a board. And that's it. So it's just got two wires. So now let's take a look at one of these things torn apart. So I broke one apart already here. So here is, now this is called the capsule, and this is just a piece of foam, and the foam is just glued on there, and it's got this, that's it, right? And it's got a little hole in it, and that's where the sound hits the diaphragm, which is basically a capacitor. And you can see inside of that reflective surface, that is the capacitor in there. And then here's the back of it. Let me zoom in here. Let me see if I can get this thing to cooperate and zoom in. Yeah, there you go. You can see I broke it pretty well. And then there was one contact in there, and that was connecting to our circuit. And I broke all this out, right? And here's what the original back looks like, right? Okay. And then this is just a rubber little grommet on it, so it doesn't get banged around. Okay. And here is what was inside of there. So that's the back, right? And then here's the front. And that's our JFET right there. So there's our JFET J35. I'd probably never be able to figure out what that component is, but it's a 3-lead device, just like a transistor. And then there's our 2 leads coming out. And then the black lead is ground and the white lead is positive. And so that's how we have to power this thing up. So what I've done is I've got this guy right here. Let's get that to cooperate with us. All right, I've got this guy right here, and you can see I kind of labeled these and put these wires on here so I could plug them into our board. All right, so there's basically the exact same thing right there. There's one from one manufacturer, and here's just another manufacturer. So these are 3 different manufacturers I've got, all the same kind of thing. And I could take this off and it would be the same. Okay, so that's it. So we're just going to hook this up to our circuit. And then we're going to see if we can amplify audio signals. All right, so let's go and do that. Okay, so here we are on the bench, and let's go ahead and put our microphone into position. So what I'm going to do is I'm going to take some of this stuff off just for a minute here so I can kind of see what I'm doing. So we'll just take our signal generator off, and we'll take a couple of our probes off here. Let's make sure the signal generator is off. It is. Okay, and then coming into the capacitor, that's where we're going to have the signal. All right, so we're going to take the positive lead, and that's going to go right there. Super simple, just going to go right there. So put that right there. And then ground, just going to go to ground. This thing is super easy. All right, but where the tricky part is, and a lot of people, if you're a fan of Arduino or Raspberry Pi or different microcontrollers, the propeller chip, whatever, PIC, Savars, you name it, you might be tempted to hook a microphone up to one of the analog to digital converters and like record audio and amplify it and play with it and process it. And you might think I should just be able to hook this directly up. It won't work. You have to power it, and then you're going to have to AC couple it. So these couple little things are going to make all the difference. All right, so let me zoom in a little bit here. So I'm going to zoom in so you can see what I'm doing here. All right, let's get that camera to stop shaking. Okay, so now what we need here is we've got the positive lead right there on the other side of the capacitor, and this is where we got to give it that bias. We got to power up that transistor. So we're going to use a 3.3K, so that's going to be orange, orange, red. And we could go a little higher, a little lower. You could kind of measure this and see where it's most effective, but this seems to be okay. So there's our 3.3K. All right, and it's just going from positive to that point on the left side of this capacitor, and where that positive output of the Electret microphone is. So now there's going to be our AC signal. So no longer do we have our signal generator signal, right? Okay, makes sense. Okay, so now let's get rid of the signal generator. I'm just going to move this over here without wreaking havoc on this desk, hopefully. And now I'm going to put our probe back on this input right here. So now we'll actually see what that Electret outputs, and it'll be on channel 1. All right, so there's our circuit, identical circuit. We haven't changed anything, haven't changed any of the values. We left this capacitor here, right? We left this capacitor here, this 1 microfarad, because it seemed to have a little bit better performance than that electrolytic for high frequencies. But anyway, since low frequencies are the same, let's just go back to the 10. Go back to the 10, and I have a little cute little 10 here I just found. Very cute, little teeny tiny little baby 10. There we go, little baby 10. All right, microfarad. There we go. All right, so let's go ahead here and let's zoom in just a little bit. Okay, all right. Okay, so we've got everything powered up, and right now you're looking at the oscilloscope, and hopefully you can see my voice modulating these signals. So here's the microphone back on the other camera here, and I'm just going to kind of talk into it as I'm talking to you, and you can kind of see what's going on. All right, so the first thing that we notice here is the oscilloscope. We've got our yellow trace, which is the Electret mic, and then we got the blue trace, which is the output. So one thing is I've got these at different scales. So first, let's put them at the same scale and compare apples to apples here. All right, there we go, same scale. And let me move this down a little bit, and there we go. Okay, and then what I'm going to do is I'm going to change the input to channel 1 instead of the output. All right, there we go. Okay, testing, testing, 1, 2, 3, testing, testing, 1, 2, 3. So you can see these things are changing as a function of time here and the amplitude of my voice. And definitely the bottom signal is larger, and it's larger by about a factor of 5. Now, human voice is very complex, and there are many, many frequencies in it, right? It's got a big spectrum. But let me see if I can make a pure tone here that doesn't sound too goofy. So we can get something that looks semi-sinusoidal so we can compare it. So let's see here. All right, so that's not bad. So if we look at those two signals, you can see we're both at 100 millivolts. Let me do it again. I'm going to put them closer to each other. Okay. That one's not bad. That's almost a pure sine wave, huh? So anyway, it's amplifying. So we've got, and let me slow it down. Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3. And you can see testing, testing, 1, 2, 3. You can definitely see the gain. Testing, testing, 1, 2, 3. Between the yellow and the blue there. So anyway, we're getting about a 5 times gain, which is what we would expect with our circuit. And now, so the next question is, coming back here to the circuit itself, what if we were to put a speaker here or something? Would we hear this microphone? Would we hear it, right? So, well, I don't know. Let's try, and then let's see what happens. So we're going to just remove our little load resistor there, and let's go get a tiny speaker. I'm going to get a teeny tiny speaker. You're not going to be able to hear this, but I will tell you the truth if I hear it. All right, and here's our tiny little speaker right here. Teeny tiny little speaker. I think this is about, let's measure it. So let's see, we've got our calipers here. Let's put these in millimeter. I like millimeter better than inches. All right, let's measure this with the calipers across its main diameter here. Yeah, it's about 16 millimeters, about 16 millimeters, okay? So 16 millimeters, so this is pretty small, and it's really thin. So this is great for wearable kind of devices and those kind of thing. You put that right in the back, you got a speaker. So I'm going to hook this right up. Now, what's the impedance of this? Oh, let's measure that. Let's measure the impedance. Do you guys remember what the impedance? I don't know if we've learned this. Have we learned this? I don't think so. So I've got this on resistance, and I'm going to go here and connect it. Just kind of hold it with my hands here. All right, and so what I'm going to do is put this so you can see it. I'd like you guys to see everything so you can be just as surprised as I am sometimes. Okay. All right, so what is the resistance of a speaker? All right, so it's definitely not K. There we go, 2, 3, 4, 8. 8 ohms, right? And that's what it's supposed to be. This is an 8 ohm speaker. Sometimes they're 4 ohms. You find different values, but 4 and 8 are the most common, all right? So it's an 8 ohm load. Now, if we take this load and we have very little current, we know that we're not going to be able to drive this. This is a huge load because it's a small resistance. But, you know, so what? Let's just plug it in and see what happens. We're not going to blow anything up, so we'll plug it in there to ground. All right, and I'll talk. Now, testing, testing, 1, 2, 3. Now, I want you to look at the oscilloscope. Watch this. Testing, testing, 1, 2, 3. Oh, let's hook. Do we have everything hooked? Yeah. Testing, testing, 1, 2, 3. Look at the blue signal. There is no blue signal. We have just killed it. And the reason why is the impedance is so low that we can't generate a voltage anymore. All right, so I'll remove the little speaker, and then lo and behold, there our signal is back. All right, so what's the problem? The problem is we have voltage gain, but we have no current gain. This thing cannot supply any current, this kind of amplifier. So what we need now is a current amplifier. Well, we already saw that. That was the emitter follower. That's a current amplifier. We could get a lot of current out of that. So we could mix this with that, and we could get voltage and current amplification out of it if we wanted to. All right. Or there's another configuration where what we could do is we could put this inside of the collector circuit directly, and then drive it in the collector circuit, and then we could still do the base circuit kind of the same way. That's another way to do it. We could drive the speaker as well, but we're not going to do that. We're pretty much done here with this amplification circuit. I've kind of showed everything I wanted to show. So that's it. And then again, you could play with the values and change what the gain is within reason. So that's really cool. And then with these little transistor blocks, rule of thumb, you want to get gains of somewhere between 10 to 25 or 50 at most. You start gaining things up by 100, you start amplifying a lot of noise. So typically 10 to 25, 10 to 50, that's the highest you want to have every one of these little single transistor gain blocks. And there's lots of things we can do to this to make the circuit more robust and give it better frequency response and all that. But again, we have done enough with amplifiers and this kind of thing. So now what we're going to do is we are going to transition over to digital logic. We're going to use transistors to implement some simple digital logic like we've done before, and as kind of a segue into digital. All right, so we are wrapping up analog electronics and wrapping up transistors. We've done it all, and so now we're going to go and kind of transition into digital logic by means of implementing some simple circuits with transistors. All right, so that's what's going to be next. All right, so I will see you in the next lecture. Bye. Welcome to the next lecture, and we are on the digital part of the course now. So we have finished up with all the analog for the most part. Obviously, we're going to still use analog components in our circuits, but we're done with the analysis and learning about analog. So you know everything you need to know about analog to get some work done to design circuits and filters, and we know Ohm's law, we know Kirchhoff's law, we know how to compute currents and voltages and deal with filters and amplifiers. So you actually have a lot of knowledge, and the good part is you know about a lot of different electronic elements. You can always go study more if you want to learn more in depth. All right, so now what we're going to do is we're going to move into the digital realm. And so digital simply means we are going to deal with ones and zeros that are represented by voltages or currents, typically voltages. And so 1 voltage, say 5 volts, might be a 1, and 0 volts might be a 0, or 3.3 volts might be a 1, and 0 volts might be a 0. And there's different logic families that have different voltages. All right, so ones and zeros that are mapped to voltages. All right, so that's one thing. Now, at the end of the day, these circuits still have to be made out of analog components. There's no such thing as digital electronics. Everything is analog, right? Everything. But we create abstractions and models so that we can think of them as operating in a different way, kind of a black box way of thinking. So we're going to actually dive in and look at what's inside of these circuits, these digital circuits, simple ones, and we're going to build some to kind of bridge your knowledge from analog to digital. So you're going to see how would you build a digital OR gate or a digital AND gate, right? What would go in there? And then once we have that, then you can kind of say to yourself, I can imagine how something more complex could be made, like an NVIDIA graphics processor, where it has billions of transistors, right? So it's just building blocks. So this is the cool part about digital. Digital is a lot of fun because once you have the basic rules, and you don't violate any of the analog rules, right? You connect things together properly, and you understand ultimately these are analog circuits. So if you do things in the wrong way, they're going to fail, right? But that's why we know analog, so we know what we're doing. All right, just like if you want to be a really good programmer, you can't just learn to code. You have to learn how hardware works. How does a cache work, right? How do you count clock cycles? How do you program an assembly language? How does a computer actually work? If you don't know those things, you'll never be a Jedi programmer. Same thing with electronics. You have to know analog to understand digital well and to be able to use digital well. So what we're going to do is we're still following the book here. And we're on chapter 3.10, Framework for TTL CMOS Logic. So again, just like in analog, we're going to be throwing out a lot of words here, a lot of acronyms and things like that. So we're going to have to learn yet another language to talk about digital. And one thing I want you to do, which is what I did when I learned all this, anytime you see a word or an acronym that you don't understand or don't know what it means, go Google it. Now, of course, I couldn't Google it back then. I had to find it in books when I learned. But Google it and see what it means so that you can at least see what you're reading there. And you're not just reading gobbledygook, all right? So, what we're going to do is we're going to go through the material here very, very quickly inside of the pages of my book. You can read that at your own leisure. And then we're going to go on the blackboard on the computer here, and we're going to build some circuits. And then we're going to go to the bench, and we're going to build this stuff. So we're going to build an AND gate. We're going to build an OR gate, an inverter, and look at how these things work. So this is going to be a lot of fun. It's going to bridge us from analog to digital. All right. So we're going to jump right into it. And I'm not sure what's going to happen, so let's just see what happens. And I'm going to throw a bunch of different information so that we can kind of get a foothold in this whole digital world here. All right, so the first thing is we start off, and if you look up here, Framework for TTL CMOS Logic. So what is this? What's TTL? So TTL stands for transistor logic. And it simply means a kind of digital logic based on transistors. You could also make logic based on, remember we did it with the diodes? There's diode transistor logic and all kinds of technologies that people were experimenting with up until about the 70s. In the 70s, they kind of locked down on TTL. And then also another technology that started happening was CMOS, which is based on field effect transistors. It stands for complementary metal oxide semiconductor. And this kind of logic is based on FETs, so it's very fast and it's very low power. Now, initially, CMOS was not as fast as TTL, and it had other problems. You couldn't output a lot of power, but now CMOS is super fast and super low power, and you can output high amounts of power, and so that's kind of the logic family of choice now is CMOS-based technologies based on field effect transistors, not normal bipolar junction transistors. All right, so that's what those two words mean. So let's just start into this. All right. So we've got digital systems, and we're going to represent, so we're going to start off with saying that 5 volts is a 1, and 0 volts is a 0. So we've got ones and zeros, and we have to represent those with a voltage. So we're going to represent those with 5 volts and 0 volts respectively. There are other logic families that use 3.3 volts, 2.5 volts, 1.8 volt, 1.2 volt, but typically if you're going to build digital electronics and interface to things like Arduinos and Raspberry Pis and whatever else, you're going to see that everything is going to be mostly 5 volt or 3.3 volt, and 3.3 volt, if you're a professional engineer, everything is like 3.3 volt. You would never use something that's 5 volt, but a lot of older technology is 5 volt, so that kind of gets legacied in, like Arduinos use 5 volt processors, so everything has to be kind of 5 volt. But if you were to design something yourself for a product, you would never use a 5 volt system. You'd use a 3.3 volt system. All right, but anyway, those are kind of the two main voltages, so 5 volt systems and 3.3 volt systems. And they represent ones and zeros, and so that's what we're processing. We're processing ones and zeros. Because we're processing ones and zeros, we have to learn the language of logic, or Boolean algebra it's called, Boolean algebra. So let's just start looking at some of these symbols. Now, if you're a programmer, which I hope you are, then all of this will make a lot of sense. So digital electronics is very analogous to programming. It's just like programming in C code or JavaScript or PHP, whatever. The logic functionality is exactly the same. All right. So here we go. So bitwise not. So we could say that some variable z is the not of x. All right. So this tilde simply means to invert x. All right. And that would assign the inverted value of y of x. All right. So if x was 1, then z would be 0. If x was 0, then z would be 1. Right? Bitwise AND logic, so you use the ampersand, or you could just say AND, same thing, it's just ones and zeros. So if both of these were 1, Z would be a 1. If either of them were 1, if it was 1, 0 or 0, 1 or 0, 0, again, you're going to get out a 0. Just standard AND, right? Or, and the symbol, vertical bar, kind of like in programming, or you could just say or. It's bitwise, and remember, we're just dealing with one bit, which is going to represent a voltage. So X or Y. And so if either of these are a 1, then Z would be a 1, and that's the and then if they're both 0, then Z is going to equal 0. All right. So not, and or are the three basic binary, logic operations. They're not all binary. These are binary, and this is unary, right? It just has one variable here, and these have two. With these three things, you can basically make anything that you want. All right. So again, if we had, we're just making up kind of a little computer language here. If we have a variable type called bool, we could say x, y, and z, and then we could say z equals x and y or z. And then depending on the precedence, so the precedence typically is and has higher precedence than or. So first it would be x and y. Then that whole thing would be ORed with Z, then that whole thing would be inverted. All right, so you could just write these things. Now, so then the question would be is, how do you build these things? So say you want to do this with hardware, right? And that's where we want to get to. Okay, so creating a convention, so we just talked about this. So what's the voltage representation of 0? What's the voltage representation of 1? And depending on the logic family, it may be different. So we're going to be talking about 5 volt and 3.3 volts, all right? But here's a little figure that shows some different logic families and what their voltage ranges are. So here's your standard 5 volt TTL, here's 5 volt CMOS, this is LV TTL or low voltage TTL, and this is 2.5 volt CMOS and then 1.8 CMOS. And then under here, you see all these little variations of it, different acronyms. And so this stands for low voltage TTL, this stands for low voltage CMOS. So there's all these variants, and so this is crazy now at this point. So there used to just be like TTL and CMOS. Now there's a tree, a huge tree of all kinds of different logic classes and families and so forth. So when you're building things, typically these days, if you're going to interface to a 5 volt system, you might use 5 volt TTL. If you're going to do a 3.3 volt system, you might use LVC or LV families. And these have a lot of different properties, right? So they may have higher drive or lower drive or higher speed and so forth. So you look at these families to get the kind of characteristics that you want out of the switching of the digital logic. Now, what are these little graphs right here? What do these represent? So when you have a digital system, remember, it's ultimately going to be based on analog electronics, right? Because of that, the analog electronics that are creating this abstract model of something digital that's either on or off, right? It's never really on or off. It's mostly on, it's mostly off, and it's someplace in between, right? And as long as you don't violate that, it can understand it. So, for example, say this is 5-volt TTL. If you take an output, right, you take a wire and you put a voltage on it. If that voltage is greater than 2.4 volts up to 5 volts, a standard TTL IC, integrated circuit IC, will read that as a 1. All right. Now, if it's below 2.4 volts, right, down here to zero point 0.8 volts, in this region right here, okay, this is kind of this unknown region. We don't know which way it's going to go, right? So this is this unknown region in here. So we got to go down here to this region, and down here, uh, what this means is this is when you would detect a low. So specifically this, and I don't want to get too much into all this right now, but V output low means the logic family is guaranteed to never output anything greater than a zero point 0.4 volts to as a low. 0.4 will be the highest voltage it will output as a low. However, it will detect anything up to a 0.8 as a low. So this is V input low. So that's what these things are. So this is V output high, V input high. This is V threshold. And so V output high means you're guaranteed that if a TTL logic IC outputs a high, it's guaranteed to be at least 2.4 volts. All right, that's V output high. But on the other hand, V input high, anything greater than 2 volts, it will detect as a 1. So there's kind of this hysteresis going on, right? So the 2.4 is not the boundary. It's 2.0 in one case and 2.4 in the other case. So it'll output a 2.4. So it always outputs a little bit higher, but it'll tolerate a little bit lower as the input, meaning a high. Same thing on the low, except in reverse. So it'll output 0.4 at maximum. We really want it to output 0, right? But 0.4 is the maximum it'll output if it's outputting a 0. But it'll detect a little bit more. Up to 0.8, it'll say, you probably meant 0. Okay? So that's how you read these things. All right? So again, these are V output high, V input high, this is V threshold, this is V input low, this is V output low, and of course V sub CC just means the power supply rails and ground is ground. Now, this margin in here, this area, is called the noise margin. So basically, how much noise can something tolerate before it flips to the other direction? All right. So you're outputting a high. How much can you tolerate in noise before you flip, a bit to the other state? All right. So you want things that have really large noise margins. Okay, really large noise margin. You don't want a small noise margin like over here. Look at this. So with this 1.8 volt CMOS, the noise margin is tiny. So say you got an output right here. If you get some noise on there, you could dip down into a low pretty easily, right? So you want things with high noise margin. So look at this. This is centered, and it's got a larger noise margin than the 5-volt TTL. All right. And now, proportionally, this 3.3 volt TTL has got a pretty good noise margin right here. All right. So we basically want these regions, very large. All right. So that's what this little chart means, okay? And again, you can read all this: V output low, V input low, V input high, V output high, and so forth, all right? So now let's go ahead and we're going to actually build an inverter and see how this thing works, all right? So you can take a look at this right here, and you can read the book, so I don't like just kind of skimming through circuits in the book and look at the analysis if I don't have to. I'd rather build it with you on the blackboard and do it. So this is kind of what we're modeling here. So we're just going to say, can we take one transistor and can we turn it into an inverter? Right? So it looks like we're going to do something where we put a base resistor and we're going to put a collector resistor, and then we're going to see, can this have an inverter-like action to it? So can I put in a 5 volts and get out a 0, or put in a 0 and get out a 5? All right, so that's the question. Can we build a basic digital element out of an analog element? So that's what we're going to do. So let's go to the blackboard and try that. Okay, so we're here on the blackboard. So what we're going to try and do is we're going to do a transistor inverter? That is the question. Can we do this? All right, so let's go ahead and let's start here. So we know a lot about transistors, all right? So let's just get into it. All right, so we're going to take a resistor here, and we're going to take our transistor. We're going to use NPN. Again, we could do this with PNP, but NPN is just easier. I'm going to put this down to ground, and then I'm going to put this collector up here to V sub CC, and let's run this whole thing at 5 volts. All right, and let's label these so we know what's what. So what's this? Remember, this is a collector. This is the emitter. This is the base. All right, and this resistor right here, this is, we're going to call this RC, the collector resistor, and I'm just going to set that to 100 ohms. All right, and then this right here, this we're going to call this RB, which is the base resistor here, and I'm going to set that equal to say like let's write that a little bit bigger. 2.2 k ohms, all right, 2.2 k ohms, okay? And we're going to bring the input here, and then we're going to take the output right here and go like this. So this will be the output. Some little dots right here. All right, now, since we're doing digital logic, we're going to start writing things in terms of variables. Okay, so we're going to call this X, and we're going to call this Y. All right, and again, now let's also do some other symbolisms. So so this means inversion. Invert. We put a bar over it, so we put X bar. All right. If we want to do an AND, we can also use the multiply operator as AND. So that's AND. Okay, and OR is the plus. X or Y. So these are the same thing as this is equivalent to, right? Equivalent to the doing the tilde X, and then this is equivalent to, like, you know, again, if it's kind of, and I'm going to have a hard time making this symbol. Let me see if I can do this right. The ampersand symbol. Oh, that's horrible. But you get it. And then X plus, this would just be X, like that. So when we're doing digital electronics, we don't use these computer symbols, we use these symbols. So we use the multiply symbol, we use the plus symbol, and then we use the bar over a variable. And that's really, really important to remember this, because it is a type of addition and it is a type of multiplication. And when we talk about Boolean algebra in the next chapter, you're going to see why that holds true, all right? But for now, forget about that. Let's just get back to the circuit. All right, so here's our circuit right here. So we got a 2.2 K base resistor. We got a 100 collector resistor, 100 ohm collector resistor. We've got our emitter directly connected to ground here. Now let's draw what's called a truth table. All right, so truth table. So a truth table is something that we draw that describes the function of the circuit. So we've got one input X, all right, and we've got one output Y, all right, and so what are the possible inputs for X? So X can either be a 0 or a 1. It can be a 0 or a 1. And I want to know, what is Y going to be equal to? So that's the question. So we're going to figure that out. Now remember that 0 really equals 0 volts, and 1 really equals 5 volts, because that's what the system is really operating at, right? Okay. So now what we're going to do is we are going to analyze the circuit in these two cases, all right? So let's give it a shot. All right, so here we go. So if we have a 0 for X, so X equals 0, then that means we have 0 volts, all right? So let's apply a 0 volt here. So we apply a 0 volt here, and so what does that mean? That means that there's going to be no current going into the base. That means that we're not going to forward bias the base emitter junction, so the transistor is going to be off. If the transistor is off, then the impedance, looking down in this direction here from this point, from our output, is going to be nearly infinite. It's going to be mega ohms, right? Mega ohms. So if it's going to be mega ohms, then what we're going to see at Y here is we're just going to basically see, this is like, you imagine the whole transistor is not even there. So what we're going to see is we're just going to see this 100 ohm connected to a 5 volt power supply. All right. So whatever we connect this to, right, whatever we connect this to, we're going to draw a current out here like this. All right, and that current is going to go through this resistor and it's going to go to our next input stage, whatever it is, all right? So say if it's a digital circuit, then that'll go to a digital circuit. So what we're going to basically see here is this transistor is off, so another rule is digital circuits have very, very high input impedance. So very, very little current will flow here, okay? Typically microamps to milliamps, so microamps to milliamps. And so those currents are called, so I input low and I input high. What this means is what's the current that the digital device needs if you're driving it low, and what's the current it needs if you're driving it high, all right? And because remember, whatever chip is over here, whatever IC is over here, we're going to have to, drive that IC because it's got analog electronics in it under the hood, all right? So now what we can do is, so let's go take a look here. So what kind of currents can we expect if we're driving something low or high? So right here, this is driving it high. So we put in a 0 and we're actually getting out of 5 volts. There's a resistor here which is limiting the current, but we're getting a 5 volts out. So, but what are these I input low and I input high? Let's go take a look. So if we go into a DigiKey and we search for a standard inverter, so an LS04 inverter. So this stands for low power Schottky, and the 04 is the number of an inverter. If we go open up the data sheet, which I've already done here, you can go through the data sheet. Let me make it a little bit bigger. Oh, there's our truth table. So high equals low, low equals high. All right, and there's the symbols for them. All right, I'm going to show that to you in a second too. All right, and there's that Y equals A invert with a bar over it. All right, and here's the actual circuits. So if you have a plain 7404, there's the actual circuit. So we can analyze this. We know how to analyze this, right? And here's the LS04. So this is low power Schottky. It's got Schottky diodes in it. Much more complicated. And then here's just the Schottky 04. So the low power Schottky 04 is much more complicated. All right, but that's not what we're looking for. What we're looking for is this table right here. Take a look. So here's V input high, and there's at 2 volts. V input low, 0.8 volts. Remember, we saw that on that chart. I output high. So here's the output current. So when one of these inverters is outputting current, it's going to output 0.4 milliamps when it's outputting a high. And when it outputs a low, it's 16 milliamps is the max. All right. Now, here, let's keep going. That's not what we want, because we want I input high and I input low. We want to see what one of these chips would need. So here we go. So I input high is 40 microamperes. So in our circuit, when we're driving this high, we can expect whatever the receiving end is here, whatever this output is going into, is going to pull about 40 microamperes. And the 40 microamperes is a maximum. All right, and then I input low is minus 1.6 milliamps. So if we output a low, current's going to go in the opposite direction and sink into our circuit. But right now we're doing the 40 microamps. So the 40 microamps, so let's go back there. All right, so we went and looked up, because we're trying to build something that might interface to real digital logic. So we know that whatever's over here at this end, and that's a question mark, whatever's over here, whatever device we connect this to, maybe we take this to another inverter, and then there's the symbol for the inverter. But maybe this is a 74 LS04. It's a real inverter, not this little thing that we made. We know that this thing is going to need what? 40 microamperes of current. 40 microamperes of current. Okay. If 40 microamperes of current gets pulled through this resistor, we got 5 volts. We're going to pull 40 microamperes of current through it. What's the voltage drop over the 100 ohm resistor? All right, so remember, voltage equals current times resistance. So let's compute that. All right, so this is going to equal the current, which is 40 microamperes, times the resistance, which is 100 ohms. So let's do it on our calculator. So 40 microamperes times 100 equals 4 millivolts. 4 millivolts. So if we're at 5 volts here, and this is going to drop 4 millivolts, so what is the voltage going to be at Y? It's going to be 4.1 4.996 volts. It's 5 volts, folks. So in other words, when we drive a TTL chip, we're going to drive it really, really nicely. This voltage is only going to drop a teeny tiny bit, and it's going to stay a 1. No problem. Okay, so that works, right? So that's it. So we put in a 0, we got out a 1. So over here in our table, we got out a 1, and so that's exactly what we wanted. All right, now let's go ahead and do the analysis in the other direction. So let's put in a 5 volts and let's see what happens. So if we put in a 5 volt, what happens? All right, so now let's we'll erase this here, and I'm just gonna have to erase some of this and then redraw it, unfortunately. All right, I'm just gonna erase that right there. Okay, and we'll leave that calculation right there. Okay, so again, this is 100 ohms. All right, now what we're going to do is we're going to go and put 5 volts here. So this is the case where we want to apply a 1, which is going to be 5 volts. So we're going to put 5 volts here. Now what's going to happen? So we got 5 volts here. Let's assume we turn the transistor on. If we turn the transistor on, we're going to get a voltage drop, base to emitter, of about 0.6 volts, about 0.6 volts. So that means if this is at ground, then the base is going to be at approximately 4.4 volts, right? 4.4 volts. So we've got, the base will be at 0.6 volts, but the voltage drop over the resistor, right, will be 5 minus 0.6, so this will be 4.4 volts. All right, so that's going to be the voltage drop. So how much current, what's the current going here? Right, so we're going to compute I sub B. So I sub B equals what? 4.4 volts divided by our resistor, 2.2K. All right, so let's do it. 4.4 divided by 2.2K equals 2 milliamps. 2 milliamps. So I'm really turning this transistor on really, really hard. We could make that a 10K, but we're going to turn it on really hard. And the reason why is we want this collector-emitter junction to go to almost zero resistance. We want this voltage. Now remember, when we turn this transistor on, remember, this thing is going to be anywhere from like 0.01 to 0.2 volts above ground, right? We want that to be as close as possible to that 0.01. We want it to be all the way to ground, right? So we punch in 2 milliamps, and so what's our current that's going to be in the collector circuit here? So now we're going to get a current out like this. It's going to go right down through here, and what's that going to be? It's going to be the 2 milliamps times beta. Beta, say, is 100, so it's going to be like 200 milliamps, all right? But wait a minute, it can't be 200 milliamps because there's a resistor here. So there's a resistor here of 100 ohms. So in other words, it could flow this much, but it's not going to because we've got a current limiting resistor. So what does this resistor limit the current flow to? Well, it's going to limit it to 5 volts divided by 100. Let's do that. 5 divided by 100 equals 50 milliamps. All right, so we're going to get 50 milliamps of current. So when we turn this thing on, what's going to happen is we're going to get 50 milliamps of current here, and the entire voltage is going to drop over this 100 ohm resistor. So this point right here is going to be 0 volts. All right, it's going to be 0 volts. So what's going to happen over here? Look, we've got our 0 volt right there. All right, so we've got an inverter. Now let's look. Well, wait a minute. How much current do we need to sink here? How much current do we need to sink here? If you recall, it was 1.6 milliamps. See if we can get to that. We're looking for I input low, and it's 1.6 milliamps. Now notice that negative sign in front of it. That's because the current's going in the other direction. So the current now is going to go from, let's draw this in green maybe. It's going to come from the device like this. So if we still have this output connected to an inverter and we output a 0 here, so there's going to be a 0 here, right, which is a 0 volts, right? But the current is going to flow out of this thing down to ground, so it's going to sink current. So we've got to sink current, and the question is, can we sink 1.6 milliamps of current? And yes, we can. The resistance here is the total current that this thing could sink down here is very large. It is like the 200 milliamps. So we could sink an enormous amount of current through here. It's going to come right down through here, and whatever this collector emitter junction resistance ultimately is down to, which is very, very minuscule right now. So we could push any amount of current we want down here within a limit. So we can definitely pull down the 1.6 milliamps. So that's going to allow this to zero to get asserted here, and then we're going to go on our merry way. All right. So now we can see that this thing is acting like an inverter. We put in a 0, we get out a 1. We put in a 1, we get out a 0. And then these things map to voltages. 0 volts maps to 0, 5 volts maps to 1. So we've got this nice inverter here, all right? And that's it. So this is basically this thing. So if you look at this thing, that's what we've built here. Now ours is a little bit more simple, right? Let's look at the Texas Instruments part here. It's better than ours. So here's Texas Instruments. Here's their inverter here. There's their simplified inverter. So you can see what's happening here. We've got kind of this 2-transistor Darlington pair kind of thing going on here. And then right here, we've got these 2 transistors, all right, instead of just 1. And then right here, we've got this transistor. We're using the collector circuit here, emitter circuit here, to go into the base of here. We've got another diode here. So this is much more complex, and every one of these little elements gives some benefit. But this little guy right here will work. It's going to burn a lot of power. It's very wasteful, but this will work. So this will be an inverter, okay? Okay, great. So that's a basic inverter circuit, all right? So now that we know that, all we need to do is basically put a 2.2K resistor here, a 100 ohm here, and now we can abstract this. So let's abstract this, all right? So let's go ahead and let's erase this. Let's just erase this whole thing, all right? And I'm going to leave those things up there, all right? And now what I want to do is let's redraw our inverter circuit. So here's our new nice inverter, right? So we're going to draw a nice inverter. Draw it a little bit lower. So we got a base resistor. We got our transistor here. All right. We've got our collector current limiter here. And then we've got our output going here. All right. And we're going to draw this as X. I'm going to draw this as it's X. This is X naught, right? Or we could call that Y. Okay. And then the emitter goes straight down to ground. And then this value here, we're saying 100 ohms gets it done. And that gives us a good amount of current. And so the 100 ohms gives us like 50 milliamps of current. And now if we were ever to pull 50 milliamps of current all the way through here, the voltage would drop all the way to 0. But if we dropped about half of that, we'd still get about 2.5 volts out of here. It'd still be enough to be a digital 1, but we could drive something like an LED or something that took a lot of current, right? So that's why that's important. So we want to have a lot of current there. Okay. And let's see, is there anything else? Oh, one more thing. So when there's nothing on this input, this X input here, this thing is just kind of floating. And believe it or not, static electricity and just, noise and whatnot could potentially drive this thing in one direction or the other. So let's go ahead and let's make sure that it doesn't. So let's pull this down to ground through a 100K resistor. So this is a pull down to ground. So now when nothing's connected here, we're pulling this down so that we know we're going to get a high out of here, right? But not a very powerful high, right? We're going to turn this thing on very, very little, but at least it's stable, all right? And this is 2.2K. So there's our circuit right there for our inverter, all right? Now, let's draw some symbols over here. So I want to show you what these things are. So this inverter, so these 3 things. So we've got inversion and an OR. All right, so let's draw what these things are. So this thing right here is how we draw an inverter. All right, and so this is X, and this is X bar. That's what an inverter. So what's this triangle business? So let me tell you about that. The triangle means amplification. So triangles typically in electronics, once you start drawing symbols for them, if you see a triangle just by itself, this can be analog or digital, but it typically just means it's an amplifier. So it's a digital amplifier or it's an analog amplifier. So all it's going to do, it's going to amplify the signal, typically the current drive of the signal, so that it's got more current, right? If it's digital, it'll keep it as a 1 or a 0, but it'll give it more current drive. Now, if it's a analog circuit, it could actually amplify the current or the voltage or both in the power. But triangles mean amplification. Now, in a digital circuit, if you see a triangle, then this is a buffer. It means it's being amplified, the input equals the output. Okay? Now, so there's the inversion. Okay, so this is a NOT or an inverter. Now, what about this AND? Okay, so what does that look like? All right, so I'm going to draw this for you, and it looks like this. All right, so it's basically a semicircle here and a flat side, and then this is X, and this is Y, and this output is Z. And Z equals X and Y. That's it. All right, so this is an AND. That's the symbol for an AND. And then let's do OR. So an OR is a little bit tricky. So what I do is I draw two lines, and then here's an OR. So it's this kind of a half moon thing, and then it goes straight, and then it goes like this, and then it goes like this, and then it goes like that. So that's an OR. So here's an X, and here's a Y, and here's a Z. All right. And you can Google these symbols for inverters, ANDs, and ORs, and people draw them in different ways, but basically this is how they should be drawn. And then this is going to be X or Y. And so remember, the plus means OR. So those are our three basic symbols right there. All right. So now, can we take our basic transistor inverter, and can we create these other circuits, right, in this OR circuit? All right, so can we do that? The answer is yes. So briefly, let's go back to the document. I want you to see the document. So we already did our inverter, and this is another analysis, and this uses slightly different values, but same kind of idea there, and I go through that. All right, and then here's what a NAND gate looks like. So remember, these components are inverting, so things are getting inverted. So if you wanted to build an AND gate, right, you wanted to build an AND gate, you're going to take two transistors and you're going to build them like this. So this is really an inverter here and another inverter here. You're going to tie them together in series like this, emitter to collector to ground. But what you're going to end up with is not an AND gate, you're going to get a NAND gate. All right, so what does that mean? So what that means is, and you look at this truth table, it's showing you voltages and outputs. So an AND gate is basically if both inputs are 1 at the same time, all right, that's an AND gate. A NAND gate is the opposite, so it's like putting an inverter at the end of it. So when you make this configuration, you end up with an AND with an inverter, or a NAND. So if we want to turn it into an AND gate, we have to add another inverter, all right? But forget that for 1 second. So just realize that if you want to do an AND or a NAND, this is the construction of it right here. You can do this in series. So you put the two transistors in series. Now, likewise, if you want to do an OR gate, right, you put them in parallel. So see how both collectors are tied and then to this resistor right here, so they're in parallel. But what we end up with, right, what we end up with here is a NOR gate instead of an OR gate. Again, it's inverted because the basic element we're using is an inverter. So we have to invert it again to get the OR gate, all right? But those are the constructions. So those are the constructions. So let's go back to the drawing board here and do this. All right. So now, so we've seen that these other words here. So if we take an AND gate, right, and then we invert the output of it, it's called a NAND gate. Now, how do we do that? All right. So what we do is this. So it's AND gate like this, and then if you just put a bubble on the output, then the bubble, now it's called a NAND gate. Same thing with an OR gate. If you put a bubble on the output, then it becomes a NOR gate. All right. And now, see these Z, instead of Z equal X and Y, it's X and Y inverted, the whole thing inverted. And same thing with NOR, instead of Z equals X or Y, it's the whole thing inverted. All right, the whole thing. So let's draw these truth tables real quick here. All right, so let's do some truth tables. All right, so our inverter is pretty simple. So here's the NOT, all right, and you've got an X, and we've got a Y. We're just going to call it X and Y for now. And if it's 0 or 1, so it's inverting it. So it's 1 and 0, all right? Now let's do the AND gate. So we've got two inputs, we got X, we got Y, and we got one output Z. So this is a binary operation, right? So we got 0, 0, 0, 1, 1, 0, and 1, 1, right? So one thing you're going to have to do is learn to count in binary really quickly, right? How to permute all these bits. All right, so if it's AND, it's only going to be high when both inputs are high, all right? So 0 and 0, nope, that's a 0. 1, oh, well, I just made a mistake. Let's do that again. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so both inputs are low, we're going to get output low. One input is high, but nope, both of them have to be high. The other input is high, nope. Both inputs are high, yes. So only when X and Y are both high, we get an output high. Okay, that's the AND. But now, if we invert that, this, go over here, this is the NAND. All right, so now if we just invert Z, whatever Z is, then we're going to get 1, 1, 1, 0. So if X and Y are both 0, you're going to get a 1. If it's 0, 1, you're going to get a 1. If it's 1, 0, you're going to get a 1. If it's 1, 1, you're going to get a 0. So see, the NAND is the exact opposite of the AND. So here's what the AND does, but the NAND is completely opposite, all right? So let's do the OR. So here's the OR gate. Same thing, we make a truth table. All right, so we got 0, 0, 0, 1, 1, 0, 1, 1. All right, so OR means if either of them are 1 or both of them are 1. All right, so 0, 0, nope. 0, 1, yep. 1, 0, yep. 1, 1, yep. So only when at least one of them is high, or both of them can be high, you'll get an output high. So that's OR, right? Now let's do NOR. So NOR, and let's get another variable here. If we were to invert this Z, let's just invert it. So that's 1, 0, and let's do it in red, just like the other one. So we got 1, 0, 0, 0. 1, 0, 0, 0. And so now, look at this. It almost looks like you're like, well, aren't they the same? No, they're not. So look at the AND. So here's the AND. It's 0, 0, 0, 1. This one is 0, 1, 1, 1, 1. This one is 1, 1, 1, 0. This one is 1, 0, 0, 0. So none of them are the same. All right, they may seem it, but they're not. All right, so a normal OR is if either of them are 1 or both are 1, you get an output high. So it's OR, either or, right? The NOR inverts that, so the only time you get a 1 out is if both are 0. All right, so the circuits that we're going to build are going to end up being, naturally, they're going to end up being NAND and NOR because we're using this common emitter amplifier, which ends up inverting the signal. So if we want to turn these things into AND and OR, we need to put another inverter after it. All right, we need to put another inverter after it. All right, so let's take a look. Let's try and do the AND. Let's start with an AND. All right, so we're actually going to design an AND gate. All right, so let's see if we can fit it right here. All right, so let's draw our first transistor here. All right. All right, and of course this goes to V sub CC, which is 5 volts. All right, and then these resistors are again the same thing. So this is going to be 100 ohm, and this is going to be 2.2K. All right, now let's draw another one right here. And this is really fun. Now, when you do, there's a whole nother part of this, which is circuit design, VLSI, or actually designing chips or IC design, where you draw transistors with P and N material, right? So that's a lot of fun. So we're kind of doing something like that. We're drawing things at this very basic level, all right? And this is 2.2K. So basically, this thing right here is like our little simple cell. So this little thing right here is our basic inverter. And with this, we're going to be able to build everything. So this is our building block, right? And we just copied it here twice. All right. Now what we're going to do is we're going to just take this emitter and we're going to connect it right to the collector right there. And we're going to take the output right here just like we usually do. All right. So here we go. Let's draw these things in here. All right, so do I have everything? All right, and so what's this? This is X, this is Y, and this is Z. All right, so the question is, what is this? And I'm telling you that this is going to be a NOR gate. All right, it's going to be a NOR gate. All right, so, and we also need to add our little pull down here. All right, so let's add our pull down. So we kind of want to know the state of these things when we don't have an input. So we'll put that 100K there, and we'll put that 100K there. All right. Okay, so let's go back over to this truth table here, and let's assume that zeros mean 0 volts and ones mean 5 volts. All right. So with this NOR gate, so this is what we're getting out right here. So this is going to actually be a NOR gate the way as drawn. So let's see if we can do a couple of these. All right, so if both of these are 0, both of these are 0, it's telling us that we're going to get a 1 out here. All right, so let's see if that works. Let's give it a try. What do you want to do? All right, so we'll put a 0 in here and a 0 in here, which really equals 0 volts, right? 0 volts, right? So we got a 0 here and a 0 here. That means that this transistor is off and this transistor is off, right? And of course, it's got its 100K pull down, so it's off anyway, all right? So both transistors are off. If both transistors are off, then that means that this right here is not even connected. The impedance looking down into there is megohms, right? Megohms. So as far as this circuit is concerned, all it sees is a 100 ohm resistor connected to this output right here, and we already know that's going to give us a current like that, and we're going to get a plus 5 volts out here. And then we're only going to be pulling 40 microamps per input of device, so we're going to get a high out. So we put in a 0, 0, and we got a high out, right? So 0, 0 gave us a high out, and that's exactly what it should do. Now it says that any other combination gives a 0 out. Any other combination gives a 0 out. All right. So now let's see what happens here. All right. Okay. So we just made a mistake. What was I thinking? This is the NAND gate. This is the NAND gate. So we're good. So that's funny that I just did that, and I just realized this is the NAND gate when they're connected in series like this. So we're doing the NAND gate. So we actually just did this one. So notice this case right here. When they're both 0, you get a 1 out of the NAND. When they're both 0, you get a 1 out of the NOR. All right, so this is the NAND. So let's write this down. Okay, NAND. So, all right, so we're okay. So we're doing analysis. We're doing NAND. This is a NAND, not a NOR. And you see, this is confusing. NAND, NOR, AND, OR, inversion. It'll make you crazy. It's kind of hard to keep up, but we're okay. All right. So now we're doing the NAND gate. So now what it says is no matter what, until both of them are 1, you're going to get a 0 out, all right? So let's do one more. So why don't we do 0 and 1? So we'll do 0 and 1. So let's make Y a 1 here, all right? And then you'll be able to see why this is true. So if Y is 1 and X is 0, so this transistor is completely off. This transistor is completely on. So this transistor acts like, just think of this, it's just a short, right? So this one's on. But this one is off still with 0, so it's still completely open, right? So what it looks like, again, is like that. So again, we got this circuit here, and we're just going to get another 1 out, right? This is all we got here, so we're going to get a 1 out. So no matter what, we're going to get a 1, we're going to get a 1. Now, if we turn, the only time we're going to get a 0 out is if we turn both of these transistors on. Now we turn both of these transistors on. So this transistor turns on, this transistor turns on, so now what's going to happen? Basically, this is going to act like a short, this is going to act like a short, right? And so now this is going to look like it's connected to ground. So now we've got a circuit from V sub CC to ground, right? And now we're going to see a 0 volt out here, all right? So we're going to see a 0 volt out there, and that's exactly what we're going to get is the 0. So this configuration is the NAND, all right? So now you say, well, how do I get an AND out of that? All right, so let's do it. So let's do this again in orange. So all we need to do is copy the circuit again. So let's copy it right here. Plus 5, here's our 100 ohm. Here's going to be our output right here. All right, so this is Z. All right, and then here's our 2.2K, and then here's our little pull down to keep this thing honest if there's no input on it, 100K. And there's our little emitter. Let's draw that a little bit nicer. Okay, and let's put some little nodes here. That there, nice, nice. Okay, and then now what we're going to do is we're going to take this Z and we're just going to connect this right here, just like that. So if this is Z and this is an inverter, what's this going to be? This is going to be Z bar, all right? So if Z was the NAND gate, then Z bar will end up being the AND gate. All right, so we know that this right here is a NAND as drawn. This is a NAND. So if we take that and invert it, then we're going to get back the AND. So in this particular design architecture, you get a NAND, right? And then if you invert it, you get a AND. Okay, and then so the OR is the exact same thing. All right. So let's go ahead and let's do the OR gate now. All right, so let's do the OR analysis. All right, so let's see. Can we cheat here and save ourselves any room? So what I'm going to do is I'm going to erase this for now. So we got another inverter here. All right, and then what I'm going to do is I'm going to break this off here. Okay. Now what I'm going to do is I'm going to put these two things in parallel. All right, and let's get rid of this 1 and 1 here for a second. All right, so now what I'm going to do is I'm going to take this emitter here, and this is, let's draw this in our correct color. All right. Okay, so both the emitters are going to ground. All right, so basically we've got two inverters. But now what I'm going to do is I'm going to tie this collector up to this collector, just with one resistor, and I'm going to take that, and that's going to be my output Z. All right, so basically we've got two inverters in parallel, all right, with just one resistor up here, and then we're going to take that output and we're going to take this and we're going to put it in here. All right, so first let's figure it out up to this point, and then we just know this inverts it. All right, so here we go. Let's see if I can do this right this time. Okay, so this is supposedly, I'm telling you that this now, in this configuration, let's erase this. I'm telling you that this is a NOR gate. This is a NOR gate, and then over here, this will end up being an OR gate down through here. All right, let's give it a try. All right, so, okay, so here's our truth table. So if we put in a 0, 0, we get out a 1. All right, let's give that a try. 0, 0. So 0, 0 means 0, 0 volt. Both of these are off. If both of these are off, then there's infinite impedance looking into both collectors. So the only thing that we're going to see is the 5-volt supply connected through this 100 ohm resistor. So let's be more specific. So this looks like this now. With both of these off, it's like these transistors aren't even here. So all we have is a 100 going into the base of this transistor right here. So basically we've got 5 volts, right? So this thing is going to flow. So how much current is going to flow through here? All right. So if we turn this thing on, right? If we turn this thing on, we're going to drop about 0.6, 0.7 volts. So this is going to be sitting at about 0.6 volts from here to here. So what's the current that's going to be going through here? What's the current that's going to be going through here? So it's going to be 100 ohm plus 2.2K across this voltage here, which is going to be 5 minus the 0.6. So it's 4.4 volts divided by 2.3K, 2.3K, all right? And it's approximately 1.9 milliamps, all right? So we're going to drag, 1.9 milliamps through here. We're going to drag 1.9 milliamps through here, okay? So if we drag 1.9 milliamps through here, what's the voltage going to drop to, right here? This is our output. So what's the voltage dropping to? What are we dropping it to? Well, so we take 1.9 milliamp times our 100 ohm, all right, and we've dropped 0.19 volts, 0.19, call it 0.2. So right here, we've only dropped to 4.8 volts. So that's still a high, right? So that's exactly what we want. So when we put a 0 and a 0, even with our own little crude logic that's really power hungry, right? We still get a 1 out. We got our 1 out, right? And then this will get inverted over here, and we'll get a 0 out, so we'll get an actual OR gate. But we're only dropping this to 4.8. So we're loading it a little bit. We're dropping it down to 4.8 volts, but it actually works, right? So with our own logic system and our own inverter, we're getting what we expect here. So 0, 0 gave us a 1 out, which is a 5 volts, and then if we invert that, we would get a 0 and get an actual OR gate. Okay, let's do another case. So let's do another case here. And so that's not going to let me undo what we erased. So let's put this collector back and put this back up here. Okay, so that's our circuit. Okay, so now let's do another case here. So now it says that anything else, any combination of 1 or 2 ones is going to make a 0. Any combination of 1 or 2 ones. So let's think about that. So let's make either of these a 1 now and see what happens. All right. So if we make this one a 1, if this one's a 0, it's not even in the circuit. So let's just forget about it. It's not even in the circuit. So this collector's got infinite impedance. It's not even in the circuit. And I hope you can see if we flip this and made this 1, 0, this one wouldn't be in the circuit. So this one is now the only one in the circuit. It's 1. We're turning it on. If we're turning it on, then this collector emitter junction acts like a short to ground. So what does this look like right here? It just looks like to ground. So we're going to get 5 volts over the 100 ohm right to ground. So this is going to be 0 volts right here, right? 0 volts. We're going to get a 0 volt right here. So now what? We're turning this one is going to be off. This transistor is off. So if this transistor is off, then what's going to happen over here? Now we're going to get our 5 volts out, right? Or we're going to get our 1. All right. So in the case of either of them, if either of them is on, right? If either of them is on, no matter what, we're going to still get a 0 out here, right? And then we can invert it and get a 1. If both of them are on, so if both of them are on, right, then both of them are short and it's still to ground, right? And we still get the 0 volts here. So that's why we get 0, 0, 0, 0. Then if you were to invert that over here with this inverter, now you get 1, 1, 1, 1. So there's the NOR. So naturally it's a NOR up to this point, right? And then if you invert it by taking that signal into another inverter, then we get the OR. Okay, that's it. So that's how you build digital circuits out of transistors. All right. So let's stop here, and we'll come back in the next lecture, and we will continue with this coverage of this material. All right. So I'll see you in the next lecture. All right, welcome back. And so now what we're going to do is build these circuits. So we're going to build the inverter, we're going to build the NAND gate, and we're going to build the NOR gate. So again, inside of the document here, the book, you can take a look at these and just kind of review them. But we'll start off with the inverter because that's kind of the basis of everything. So once we have this inverter circuit, where did it go? Once we have this, we can just put 2 of those in parallel and we can do the NOR gate, and then we can put 2 of those in series and we can do the NAND gate. All right, and then again, we can take a look here at our document we've been kind of marking up here on the blackboard. So we're going to change what's in the book a little bit, and we're going to use a 2.2K in the base resistor here to drive it, and then we're going to use a 100K pull down to just make sure there's some signal, and then 100 ohms up in the collector. All right, so that's kind of our basis. So this is our little building block, all right, and we're just going to use PN2222 transistors. All right, so let's go to the bench and let's build these things. Okay, so I am pretty excited. You know I like building stuff, so let's get right to it. So first we're going to build the inverter. So hopefully you have that up on your screen so you can kind of figure out what we're going to do, but we're just going to start off here with a 2222 transistor, which is NPN. And why don't we, as a matter of fact, what we'll do is we'll put the inverter over here, and that way we'll create either a NOR or a NAND gate here, and then we'll use this inverter to invert the signal at the end. So we'll put 1 inverter here, which we'll leave, and then we're going to add 2 more inverters to make a NOR and a NAND gate. All right, so we start off, and remember it's emitter, base, collector. All right, so we're going to take the emitter and we're going to put that right to ground. And we're going to do this with a 5-volt system. So we're going to put our power supply at 5 volts and run that in those rails there. All right, and now we need the collector is going to go up to the power rail through a 100 ohm. So we're going to find that. I've got all my resistors here. And I'm going to try and make these fairly small. As a matter of fact, let me zoom in just a little bit for you. I'm going to try and make these fairly small so that these little blocks, we can replicate them and they're not going to use up too much space. All right, now what else do we need? We need the base. We need the base, and that's going to be fed through a 2.2 K resistor, and that's going to be the signal, either high or low logic. So let's get a 2.2, which is a red, 2.2 K. And we'll go ahead and put that right there. And then also, off the base, we're going to take that base and we're going to put it to ground through a 100K resistor, and that's just going to keep it with a stable signal, so it's not floating. All right, you'd be surprised. These circuits can kind of float, and you can touch them, and you can get them to a changed state. So we're going to put a resistor there, 100K, and that's going to give us a steady signal. Okay, so now we've got our inverter. That's it. I mean, that's pretty cool. So that's all there is to it. So now let's get something to put a signal in here. So what I'll do is I'll just take this wire, just this wire, and then what we'll do is we'll connect the wire to either ground or +5, and then that will be the signal in, and then the signal out is going to come out here. So let's get that for now, and then we may change this a little bit. So here's the output. So here's the logic output right here. All right. And then what I want to do is I want to put that through an LED so we can see it. So let's just get a green LED here. And then let's use about a 220. Here's a 330. I'm just looking for what I kind of like. Let's use a 330 ohm resistor here. I don't want to pull too much current, so that's orange brown. And then we're going to go to ground. And remember, on these LEDs, the flat spot is ground. Oops. The flat spot is ground. Let's go on the zoomed in camera again. So if you look at this, you can see there's that flat spot. Let me get it so you can see it. Green's not the best color. The flat spot is there, all right? And then it happens to be, you can see that big post there, big flat post. That's ground, all right? Okay, so that's going to go to ground. All right, so there's our circuit. All right, so when there's a high, we're going to get the LED is going to be on, and when there's a low, the LED will be off. All right, now remember, this is an inverter. All right, so let's go ahead and let's power this thing up. Let's see what happens. So I've got 5 volts going in. Now, right now, we've got this weak low on here, right? So that's why we're getting a high out. All right, so now let's actually put a low. So now we've got a low and we got a high out. That's good. All right, and then we'll put a high and we get a low. All right, so when we put a 1, we get a 0, 0, we get a 1. Perfect. All right, now let's go and measure, and there's our little red LED to let us know that our power is on. Now let's measure the voltage here. So let's measure the voltage because we want to see what's going on with that. So what I'm going to do is I'm going to get one of our handy meters here, and a bunch of stuff is going to drop off the table. All right, so I've got a meter, and I'm going to get one of our little probe connectors here. And what I'm going to do is I'm going to connect it right here before the resistor, because I just want the voltage at that node. All right, so that red lead is going to the output, and then I'm going to take this yellow lead to ground. All right, so we need a ground reference. Let's do that. And the power is still on, but I'm not going to short anything, so I think we'll be okay. All right. So now I'm going to connect up the meter. All right, so the meter's connected. You can see it there. And let's get it a little bit out of our way there. Okay, and now let's get the actual meter in the picture. Zoom out. Alrighty. And there we go. Okay, let's turn our voltmeter on. Okay, so right now we've got a 0 for our output, and we're showing 106 millivolts or 0.1 volts. All right, so that's good. So that's almost at ground. Now let's put a 0 in, which will get us a 1 out, and then notice we're at 4.33 volts. 4.33. Let's get rid of this LED. When we get rid of the LED, now notice now what happens, because we're dropping no current, or we're pulling no current through the LED to ground, we get the entire 5 volts out of the system, all right? So, but remember, the moment we put this LED, now we've got a load, and this LED is about, 10, 15 milliamps, so that current then drops over our collector resistor, which is at 100 ohm there, all right? So that's why you got to be careful. You want a really small collector resistor, so as you pull a lot of current, not a lot of voltage drops there, and you still get your full voltage out. But the point is that even with our LED in the circuit there, we're still getting 4.33, and that's well over the minimum for a 1, which is 2 volts, right, in the TTL system. All right, so that's an inverter, so that works, all right, so we're done. All right, now what we're going to do is we're going to copy this circuit, and we're going to copy it 2 times. We're going to put it here, and we're going to put it here, and then we're going to make a NOR gate, and then we're going to make a NAND gate, or a NAND gate and a NOR gate, whichever one. And then we'll take the output of that through this inverter here, so we get a proper OR gate, or an AND gate. And I know it's hard every time I say a NAND gate or a AND gate, right? You gotta be careful. So anyway, let's do that. All right, so let's turn the power off. Let's zoom back in. All right, let's go ahead and build this. I'm going to move this meter here, and I'm going to get rid of this line right here. All right, so let's copy this circuit right now 2 times here and give ourselves some room. All right, so I've got these 2 other transistors, 2 other 222s, and they're all of the same manufacturer because I want them to, I want them to be semi-matched. So that's important. If you're going to do things, you might as well use the same manufacturer. All right, so let's put the ground leads from each of our emitters. Let's get that in. So all our emitters go to ground. So we've got 2 of them here. So there's one. And then here's the other one. Okay, looking good. All right, then what else do we need? We need our, let's work with the base right now. So at the base, we need a 100K to ground in both of these. So let's do our 100K to ground. There we go. And 100K is brown, black, yellow. Brown, black, yellow. All right, brown, black, yellow. So there we go. Good. All right, and then before we go put the collector resistor, we're going to, let's continue finish base circuit. So we need 2.2 Ks coming out of the base. That's what's going to feed each one of the bases. That's where our inputs are going to go. So there's one of them that's red, 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 right? Red, red, red. And another red, red, red. All right, so there's our circuit there. Okay. So, and then we'll just use wires to connect both of these. Okay, so now let's go back to the blackboard on the computer there, all right? Okay, so here on the screen, this configuration right here, when we have the 2 transistors in parallel like this, and we have just 1 collector resistor, this is going to be the NOR gate. So when they're in parallel, it's going to be the NOR gate, all right? So let's do that first. So we're just going to use 1 collector resistor, and we're going to tie both of the collectors together, and that'll be a NOR gate, all right? All right, so we just need 1 collector resistor. So we're going to take it, and we're going to put it right here. That'll be our final output. All right, and then we're going to tie both of the collectors together. All right, that's going to take both of our gates and just tie them together. All right, so there they are. You know what, let's use a little bit shorter wire there. So that ties both the collectors together. All right, and then now we need our output, which is also at that collector.